Welcome to the Italy-Taiwan Bilateral Meeting on Emergent Crystalline Materials, co-organized by University of L'Aquila, the Ministry of Science and Technology of Taiwan, the Taiwan Consortium of Emergent Crystalline Materials, the Representative Office of Taipei in Rome, the Italian Economic Trade and Cultural Promotion Office in Taipei, and the Italy-Taiwan Scientific Exchange Association. It is a big pleasure for me, on behalf of the whole organizing committee, to open these 2 days of scientific talks, which will be held on the Cisco WebEx meeting platform. There is a live YouTube broadcast of the whole event. Moreover, we have prepared a virtual interactive showroom with supporting materials on this event on the Padlet platform, with 25 virtual stands from 20 institutions, with over 200 posts with videos, posters, scientific papers, link to websites, and even a podcast contribution. Please visit the Padlet wall and post comments or questions for the various delegates of this bilateral meeting. Thanks to the capabilities of the Padlet app, a new form of communication in scientific meetings can be explored, also with your help. This virtual meeting aims at providing a forum on new trends in material science from the Italian and Taiwanese scientific communities. The scope is to gather physicists, chemists, engineers, and material scientists working on innovative materials and their application in both countries. The scientific program will feature selected talks related to topics covering advanced materials and related applications in photonics and optoelectronics, energy conversion, water treatment, green technologies for sustainable growth, surface science, semiconductor industry, and nanotechnology, with the participation of invited speakers of highly reputed institutions of both countries, leaders in their respective scientific field. We hope that this event could further stimulate bilateral cooperation with new collaboration and international projects. Enjoy this meeting on WebEx, YouTube, and Padlet. But let's start now with the opening session with Chairman Maurizio Peruzzini from CNR in Florence. Maurizio, the stage is yours.
Thank you, Antonio. Thank you for your words. And good morning, ladies and gentlemen, Magnifico Rettore of the University of L'Aquila, ambassadors, colleagues. So it's really a pleasure for me to introduce the first talks, the first speech of the morning, which will be delivered by ambassadors Andrea Sing-Ying Lee, that is the representative of Taiwan in Italy. Please, Dr. Sing-Ying Lee, the stage is yours.
Thank you. Good morning and good afternoon to you all. It is a great pleasure for me to join Deputy Minister Dr. Minn-Tsong of Science and Technology of Taiwan. I'd like to say my greetings to my counterpart, Minister Davide Giglio of Italian Economic Trade and Cultural Promotion Office in Taipei, Rector Magnific Edoardo Alesse of University of L'Aquila, distinguished guests, professors and researchers of all participants at the Taiwan-Italy Bilateral Workshop of Emergent Crystalline Materials. As a representative of Taiwan in Italy, it is really a great honor for me to be invited to deliver the opening remarks of this two-day online workshop. The bilateral relations between Italy and Taiwan has always been very dynamic. Our representation, which celebrates its 30th anniversary this year, has continued to work on promoting ever closer ties between our two countries in commercial, agriculture, academic exchanges, and collaboration in a diversity of fields. In fact, we have recently created the Culture Division in Taipei Representative Office in Italy, 1 year ago exactly, to further expand the horizon of culture exchanges with direct support from the Taiwan's Ministry of Culture And as chief of the mission in Italy, I look forward to working harder to try to get also in the future technology division in our representative office in Rome. And that will be very important and instrumental in the future science and technology exchanges. Trade-wise, Taiwan is currently Taiwan's 5th trade partner in Europe, with the main Italy products ranging from machinery, cars, food, and fashion being highly appreciated in Taiwan market. At the same time, Taiwan is also among Italy's top 5 trade partners in Asia. As many of you should have been aware of, Taiwan's economy has continued to thrive throughout the COVID pandemics and enjoys an economic growth rate of approximately 8% in the first half of 2021. The importance of Taiwan as indispensable trade partner to Italy and to the world has also been widely recognized when car manufacturing industry around the world turns to Taiwan's world-leading semiconductor industry in the hope of solving the crisis of the shortage of microchips, which the shortage problem is still patent and is lingering, and we don't see an immediate solution. So the crisis and the challenge is still there. So without doubt, the powerhouse behind Taiwan, Italy's highly advanced industry and technology is our shared tradition of quality higher education and investment in research and development. In these couple of years, I have personally witnessed the dedication of academics and the researchers during my visit to universities and research centers from north to south of Italy, from Turin to Milan, from Rome to Naples. It was indeed a delightful surprise to discover that besides the research projects under the frame of the National Research Council of Italy, the CNAI, and the Ministry of Science and Technology of Taiwan, which has already led to many successful joint research projects, there are many more scientific exchange and research collaborations going on, like this one of today's workshop. This phenomenon has inspired my team to further seek to establish bilateral cooperation framework for agriculture technology research, for example, and to support the founding of a newly reality in Italy, the Italian-Taiwan Scientific Research Association, with the help of Professor Stefano Pelaggi from La Sapienza University of Rome, in order to provide more resources and enhance networking among scientists in both countries. I believe with the joint efforts of governmental and the research institutions, together with the strong will and professionalism of research personnel, I'm confident that Italy and Taiwan's pursuit of excellence will not only contribute to the industry of our two countries, but will further benefit the human beings as a whole. The Taipei Representative Office in Italy, as the government representative office of Taiwan, Italy, will continue to offer our support whenever and wherever needed. So before concluding, I would like to express my gratitude to the chairman of today's workshop, especially Professor Antonio Politano, for your effort in coordination. My sincere wishes for a very successful event and best welcome to each one of you. Thank you very much.
Thank you, Ambassador, for your speech and for your good words. And let's say good afternoon, I correct myself, because the time difference is still operating. Well, so I give the stage now to Ambassador Davide Giglio, that is the representative of Italy in Taiwan. Please, Ambassador.
Thank you, Professor Peruzzini. I'm very grateful for the invitation that I've received to participate in today's virtual meeting. Grateful especially to Professor Politano for his efforts in coordinating the preparation of this today's event. I would like to extend my greetings from Taipei to Ministry of Science and Technology here in Taipei, and to my counterpart, Andrea Lee, at the Taipei Representative Office in Rome. As he has rightly pointed out, Italy and Taiwan do entertain a robust relationship, especially in trade and culture and human people-to-people exchanges. I believe that there is an ample ample latitude for improvement in the area of scientific cooperation. Both Italy and Taiwan are endowed with a lot of potential in this field, and they have until now punched below their weight, I should say. It is, of course, in our mutual interest to increase the contact surface between the mutual scientific communities. And I believe that today's and tomorrow's event goes in the right direction. Despite the pandemic, the frequency of the interaction can be further heightened. And when conditions will be such that traveling between Italy and Taiwan can be again safely entertained, I believe that there will be a rebound in many areas, certainly in trade and cultural exchanges, but also, I hope, in scientific and technological exchanges. In this regard, I would like to offer my congratulations to Professor Pelaggi and of the University of La Sapienza, because with this initiative of creating a permanent platform for exchanges, academic exchanges, ITASEA, he is doing a very good service for the promotion of interaction between the two scientific communities. As Italy and Taiwan, I think I believe we have a challenge. We are perceived as a country of mechanical excellence, not necessarily as a country of technological excellence. This is probably due to an imperfect knowledge of all the areas where Italy does excel. And the fact that this year the country has been awarded the Nobel Prize in Physics is actually a very positive news for Italy, not only in Taiwan, but I should say worldwide. It showcases the eminent position that Italy has in some scientific areas. It has been pointed out that there is a framework for cooperation that's provided by the interaction between the Italian National Research Council, Consiglio Nazionale di Ricerche, and its Taiwanese counterpart, National Science Council of Taiwan. In 2011, a memorandum of understanding was signed between the two parts, and some areas of cooperations were identified, such as biomedicine, smart cities, cybersecurity, green energy, precise agriculture. And some activities have taken place in this past 10 years, and many more, I think, should be in the pipeline with the support of the institutions that oversee this type of cooperation. I believe that the scope, the subject matter of the seminar that will take place tomorrow, today and tomorrow, deals with an area where Italy and Taiwan can do concrete cooperations. Materials, especially high value and high technological materials, are used in high-end production lines. And one of them is, for instance, that of the semiconductors. So I think that by highlighting the potential links between Italian and Taiwanese technologies and the industrial supply chains, we will take an important step in the common effort in the redefinition, in the reshaping of global supply chains that are undergoing a monumental change in these times. So all I can say is that I think that the conversations that will take place between academics and scholars of Italy and Taiwan today and tomorrow online will certainly be instrumental to the further goal of bringing together Italy and Taiwan, who have already taken together important steps, but they can do a lot more by joining forces and resources in the scientific and the technological realm. And as my counterpart has highlighted, also my office stands by offering any support that can be useful to promote and facilitate exchange between Italian institutions and local counterparts. So even after today's and tomorrow's event, please do not hesitate to contact this office for exploring potential cooperations between Italy and Taiwan. Thank you very much.
Thank you, Ambassador David Giglio, for the nice words and for the presentation of the many possibilities existing to strengthen the relationships between the two countries. Now, I give the stage to the to the ministry, Minn-Tsong Lin, that is the Deputy Minister of the Ministry of Science and Technology of Taiwan. Please, Ministry.
Good morning and good afternoon. Our honorable guest, Minister Plenipotentiary Davide Giglio, Professor Alesse, and Ambassador Andrea Sing-Ying Lee. Dear fellow scholars, it's my honor to give an opening message for this meaningful workshop. In the event of the current epidemic, we have to adapt an online symposium, and I thank you very much for your participation. Ministry of Science and Technology of Taiwan, MOST, in the past decades, continued to support and connect academic and industry research. It's our responsibility to formulate policy to reinforce the frontier technology, such as emerging materials, and also to help address environmental, social, and economic issues. Italy and Taiwan have a long history of good economic and trade relations. The cultural connections, political relations, and the general friendship between Italy and Taiwan have grown closer. Scientific and technological cooperation and exchange activities provide opportunities to promote a better level of partnership. Through the symposium, we look forward to enhance the network between the Italian and the Taiwanese researchers, both in academic and the industry institutions, and to enhance the synergies between the two countries in the scientific and the technological field to an excellency. As the Deputy Minister of MOST and the condensed matter physics, I acknowledge the committee for achieving this workshop during the pandemic and hope the fruitful cooperation between Italian and the Taiwanese science communities. I wish you all a wonderful day. Thank you.
Thank you so much, Ministry. We move to the magnificent Rector of the University of L'Aquila, Professor Edoardo Alesse. Please, Rettore.
Thank you. Good morning
with us today.
Everyone, and many thanks for inviting me. It's a great pleasure for me to bring the greetings of L'Aquila University, my personal one, on the occasion of this first Italia-Taiwan meeting, bilateral symposium on innovative crystalline materials and their application. It's a very important topic and a truly interdisciplinary field of study to which physicists, chemists, engineers, biologists, and biotechnologists can contribute and meet each other, interact with each other. This type of study could be very useful for modern societies and could have an important economic as well as scientific impact in photonics, in nanotechnologies, in particle physics, but also in the field of semiconductor and sensor, and finally in diagnostic and therapeutic medicine, improving the discovery and treatment of important diseases such as cancer. Now I want to address special greetings to Andrea Sing-Ying Sing-Ying Lee, Ambassador of Taiwan Rome, Davide Giglio, Chair of Economic, Trade and Cultural Promotion Office of Taipei, and Minn-Tsong Lin. I don't know if the minister can hear me, but I want greetings to Minister, Deputy Minister of Ministry of Science and Technology of Taiwan. I will not be able to stay as long as I would like with you during this meeting, but because of previous commitment, but I'm sure that an excellent job will be done, thereby promoting the advancement of this area of research and the interaction and the collaboration between Italy and Taiwan. And this is very nice, very good result for all of us. So now I stop my presentation and just wish good job to all of you for this beautiful meeting. And I want finally thank Antonio Politano for organizing in L'Aquila this important scientific meeting. Thank you very much.
Grazie, magnifico Rettore. Thank you very much for your kind words and greetings. And so after this first round of presentation, we continue the morning ceremony, moving to Professor Hing Hier Cao from the National Taiwan University, who is director of the Center for Emerging Materials of that university. Please, Professor Cao.
Can you see my screen?
Perfectly. Please go ahead.
Yes, yes.
Okay. Good morning, good afternoon, everybody. So my name is Hing Hier Cao, and I'm actually a condensed matter theorist, but I'm here as a convener of condensed matter section of physics panel and the director of TCECM. To give you some, to give the Italian friends some short introduction to the condensed matter physics research in Taiwan. First of all, I would like to show you a pie chart, which is to give you a roughly idea of the funding for physics for basic research. And as you can see from this chart, so there's more than half of the research funding for physics are going to a broad range of condensed matter physics. And in particular, there's a big portion of the funding going to, say, semiconductor physics, magnetism, optoelectronics, and surface science. I apologize that I didn't convert this in euro, but basically just divide by 3, you'll get the number. So in terms of condensed matter physics, so the total budget for personal grant is about 60 million euro, and those are distributed among 340 principal investigators in about 30 to 40 universities and government labs. So as you can see, we are a relatively small community compared to Europe. In addition to these personal grants, there are special programs. One of them is this TCECM. So basically, I'll explain what the acronym means. So annually, we have about 2 million euro budget. Recently, because of the trying to go beyond the Moore's law, the government initiated a Angstrom Semiconductor Initiative, which is the annual budget is roughly 4.5 million euro. So I'll give you some background of these 2 special programs. I have to emphasize that the personal grants are for freestyle exploratory kind of research, but these special programs, we have missions. So these are mission-oriented research. So the first one is a TCCM. It's an acronym for Taiwan Consortium of Emergent Crystalline Materials. It was established more than a decade ago. So basically, it's recognized Taiwan needs the ability to grow our own crystals, and basically we integrate the studies in different material science centers and try to emphasize the single crystal and thin film epitaxy. Okay, and we want to use this platform to cultivate next generation research and design talents and train senior technical personnel for these solid state materials. And we want to be able to produce special high quality single crystals and new materials for both basic and applied research. We also want to strengthen Taiwan's technique to fabricate cutting-edge materials and facilitate Taiwan's specialty development of single crystal growth. On the application side, we want to assist the company to increase their international market share through patent licensing and technology transfer. And we want to have our own single crystal growth capability. And as you will see, many of the invited speakers from Taiwan are part of this program. So the most important message for the mission for this program is we want to make materials from Taiwan a well-known brand, and we want to set up the world-class academic research programs, and we want to support the develop a new material needed by the Taiwanese industry. So this TCCM, you can think of it as a platform for material innovation from Taiwan. So there are several goals we want to achieve. We want to encourage through material growth. We want to encourage cutting-edge crystalline material growth. We want to develop internationally competitive academic research programs. And we want to also establish close links to industrial applications in order to create added value economy for Taiwan. So let me move on to the second initiative. So this initiative is called the N-Strong Semiconductor Initiative. Basically, this is due to a recognition of if you keep shrinking the size of your transistors, then at some point you're going to reach the atomic limit, and a lot of important quantum physics will enter. So there are several thrusts, and the physics part, the physics part focus on the atomic detection technology, detection technology at the atomic level, and the new material development. So this atomic scale metrology and inspection basically want to leverage the cutting edge metrology inspection techniques such that we can develop some N-Strong scale resolution in academia, and potentially they can have applications for this semiconductor industry. And the emphasis here is we want to have an inline techniques such that ready for the manufacturers to use. And the thrust two is we want to develop key materials for future devices. And so, for example, this how to apply, how to grow large-scale 2D materials, how to put them into devices is a very hard research topics in this thrust. So I want to share with you some statistics from this TCCM program. So TCCM program has been here for more than 10 years, and from the past 6 years, we see that there's a very good publication record. For example, there's in top 10 journals, we have out of all the publication, more than half are in the top 10 first-tier journals, and 12% are in the top 1% journal. And importantly, more than 60% of these publications are done through international collaboration. And this will be the focus of the next phase of TCCM. We want to strengthen the existing international collaboration and try to bring it to another level. And as I posted on this palette, there are certain areas that the Taiwanese researchers have some advantages. For example, the 2D materials, graphene related, and also this energy materials, and semiconductor quantum dots, for example, and some battery materials. So these are currently the strength of the PI in this program. And from the key phrase analysis, we see that we see a lot of these like perovskite and topological insulators, monolayer materials, and heterojunctions. So this is, as you can see, this indicates what kind of research the PIs are in this program are interested in. Also, there's a strong link between the industry and this TCCM program. Since 2019, the Taiwan Semiconductor Manufacturing Company, the largest foundry in the world, they provided a type of research fundings to fund the researchers, research scholars to promote the next generation's semiconductor research. Due to this chip shortage, and the TSMC actually is expanding this R&D team to more than 8,000 people, and they're going beyond just optimizing the manufacture processes. They will also fund mission-oriented basic research in order to meet the future challenges. So I'll quickly go through some of the highlights from this TCCM program. So one key component is to produce high-quality single crystals. So currently, there's a lot of crystal has been grown at the various labs funded by this program. For example, one of the single crystal has been become a candidate scintillation crystals for the next generation LHC. So there are materials for quantum storage and fluorescence materials for car lamp. So this is one of the material area that we focus on. Another focus is this two-dimensional 2D materials for electronic and optoelectronic applications. For example, there's the 2D material has been applied to hydrogen energy generation. It has been applied to soft electronic components, and there's some research in the solar cell materials. The graphene is also applied to this solar cell research. Another highlight is that this by designing a special mica materials one can put the oxides on this mica material to achieve some very soft, very flexible electronic devices. To highlight the industry and academic collaboration, one of the wafer level boron nitride was grown through the collaboration between the researcher from this TCECM program and TSMC. So with this, I will like to conclude. In the next few years, we want to hope to strengthen our international collaboration through this TCECM platform. And we want to change the slogan from materials from Taiwan and to material from Taiwan to the world. And I hope that through this meeting, more collaboration can be established and more joint research will be started. And with that, I thank you for your attention.
Thank you so much, Professor Hing-Her Kao, for this, let's say, great overview of the potentialities and the realities of what Taiwan scientists are doing in the area of condensed matter. So I think that there is time for questions or curiosities raised by the audience, and so I encourage people to raise questions to Professor Kao. Please. Is there any questions? Maybe Antonio can help me looking if some questions are present. I just started with a curiosity. I am personally working in an area related to what we are presented, that is 2D black phosphorus, exfoliated black phosphorus. And I am wondering if this kind of, let's say, intriguing 2D materials has been object of studies in Taiwan, and there are group of scientists in Taiwan working on this fantastic material.
I'm not sure I know anybody who's working on black phosphide, but I can be wrong because as a theorist, I roughly know who works on 2D materials, but specific platforms,
that could be of interest, just to let's say in a separated time, just to talk about this, because that could be interesting, just also for start collaborations.
Yeah, I think that material, from what I know, is very hard to grow.
Yeah, the problem is the stability of the material, indeed.
Yeah.
But
that's what I recall.
The electronic properties are really spectacular. Well, is there any other curiosity or question? Please do not hesitate. In the audience? Okay.
Hello?
No? If
you hear me?
Yes, I can hear you.
Okay.
Please introduce yourself when doing the question, or raise the question. Professor Carlo Rizza, please.
Sì, from University of L'Aquila. Good morning or good afternoon, everybody. Okay. I see in one...
Can you speak loudly, please?
Sì.
Grazie.
In one of your slides, I see some word, metamaterial. I am a researcher on this field. Can you give some details about your activity in this field, please? Do you understand my question?
I didn't catch the last part, the last sentence. Could you repeat?
Can you give some detail about your activity on metamaterials? Do you
metamaterials
them, or there are some activities about this field? Are there?
Yes, as far as I know, there's a couple of researchers doing metamaterials. I think one of my former colleagues was doing it, and there are some people from the engineering side that they're also doing it. Yeah, so actually, I think there's probably 5 to 10 PIs are doing metamaterial research. But I think I have to get back to you on the exact numbers and the context.
Okay.
Thank you.
Thank you.
Is there any other question? I don't see anything in the chat. Okay. If this is not the case, I would like to thank Professor Xin-Kier Tao again, and to move to the next speaker with Stefano Pelaggi, Professor Stefano Pelaggi from the University of La Sapienza in Rome. Professor Pelaggi will talk about the ITASEA, that is the Italy-Taiwan Scientific Exchange Association, and we are very eager to know something more about this project. Please, Stefano.
Thank you, Professor Peruzzini, and good morning and good afternoon to the honored guest. I'm really glad to be speaking here today. I am a political scientist, so for one time it's really nice to be in between real scientists. And I am here to present this newborn association, which is ITASEA, stands for Italy-Taiwan Scientific Exchange Association. I'll try to show you some slide. I think you will be you seeing them now, right?
Yet? Apparently it doesn't work for the moment. Okay.
So the association is a newborn association which aims to connect the world of academia, between Taiwan and Italy in the technological and scientific sector. So basically, we aim to connect, to enhance, to develop the cooperation between the two countries. The main objective is an circulation of intellectual human resource and talents, deepening the excellence in the field of science and technology. So particularly, we are focusing on medicine, information technology, natural and mathematical science, and engineering. We did the association will be structured as so. We did choose a president, which will be Professor Roberto Verna, which is a full professor of clinical pathology at Sapienza University of Rome. There will be a board, and there will be a scientific committee. Until now, we already have 50 person inside the scientific committee, and while doing so, we started to recollect all the already existing relationship between Italy and Taiwan. and it was really fascinating because we did find that there are a lot of universities which have been cooperating in so many different fields. One of the most remarkable example is the conference we are here today, and the relationship with the University of L'Aquila as established with Taiwanese University.
Stefano,
so we did.
Stefano,
Yes.
sorry, but we don't see anymore your presentation.
Oh yeah. I just took it out. Just wanted to show you the logo and so on. So it's.
Okay.
I thought that it was. It would be a little bit more communicative if we don't have. So we did find a lot of synergy, a lot of cooperation between the two countries, and this is exactly what the association aims to do. So to use this ITASEA as a framework, to use ITASEA as a tool to promote cooperation. We all know that the past 2 years have been difficult for everybody, and even for the academia. And international exchanges have become more and more difficult. This is even more true in the case of the Asia Pacific. Countries like People's Republic of China, Taiwan, Japan, South Korea did choose a way to face the pandemic, which kind of closed those countries to the outside world. So, for example, we in Sapienza we did add several agreements and cooperation framework with Taiwanese university signed in 2018 and 2019, but none of them has been really implemented because everything stopped for those 2 years. So exactly, this is one of the place where ITASEA could really work. So try to revive, try to give back life to all those agreements which were done, which are already in place, but are somehow suffering from all the consequences from the pandemic. And we did receive the support from the Taiwanese representative office in Italy and the Italian representative office in Taiwan. I would really like to thank Ambassador Andrea Sing-Ying Lee and Ambassador Davide Giglio for the words that they spent today for the association. We did receive the support from the Italy-Taiwan Interparliamentary Friendship Group, which is the main organization which is trying to support the so-called Taiwan cause in the Italian politics. It's a group which can count on more than 100 between deputy and senator in the Italian politics. We received support from ECCT, which is the European Chamber of Commerce in Taiwan. And we can count on the several members of the Italian community residing in Taiwan, which mostly operate in the field of technological and scientific research, most of them in information technology, but lots of them are even professors in different Taiwanese universities. So it's exactly what Ambassador Giglio meant for people-to-people cooperation. We are, with ITASEA, we will be trying to use all those dots which sometimes are connected with Taiwanese and Italian reality, with Taiwanese and Italian research center and academia. We would like to put all those dots together to create a big network, which could be a really useful tool for the scientific and technological cooperation between the two countries. In the near future, we will be registering the association in the next week. In the near future, we are planning to open and to create a similar association under Taiwanese law. So it will be really important to have a counterpart with the same exact scientific committee which can operate in Taiwan. At the same time, we are trying to create a database of all the academic exchange and cooperation between Italy and Taiwan. And again, I would like to stress out how many of them there are. And so it's really important to know, to have a precise knowledge of what those agreements are and how they are implemented. There are a lot of agreements, there are a lot of student exchange, there are a lot of joint projects and executive protocols. We did find that there are at least 3 double degree courses already existing between the two countries. So ITASEA will try to build a structure which is capable of connecting research center, university, single researcher of the two countries to facilitate joint projects. But we do even try to put inside this framework companies. For example, until now, we did find a lot of interest from biomedical and pharmaceutical company in Italy and information technology company in Taiwan. So we do strongly think that an association like ITASEA could be an important actor to develop this cooperation. And more than everything, we would like to create a condition to encourage student exchange between the two countries. We do all know how exchange works. If we do have a flow of Italian student to Taiwan and Taiwanese student in Italy, everything grows. Everything gets better. It's the people, getting to know each other. Today there are students, PhD students. Tomorrow they might be a faculty member. There might be professor and researcher traveling back and forth in the two countries. There are a lot of agreements and memorandum of understanding. We did find that sometimes some of them are kind of hard to implement. And the last, one of the last, but probably the most important thing that we will be trying to do is to create a newsletter and, of course, a website in which we will write all the information on professor and student exchange opportunity, all the deadline for founding from institution of the two countries, the deadline in for participating in individual and collective calls. There are so many ways to promote and so many ways to finance student professor exchange, joint research. A lot of times, academia and professor in both countries doesn't know about that. So we will be really trying to do this, and the support of the Taiwan office in Italy, under which the same idea of ITASEA came out during a meeting with Ambassador Andrea Sing-Ying Lee. It's so the support of the Taiwan office in Italy is really important, as is the counterpart in Taipei. So we will be we do really hope that we will be able to give a new push to the already lively relationship between Italy and Taiwan in the scientific and cooperation field. You all have my email, and I do remain available for any kind of comment. Of course, you are all invited to participate in the association, and I would like to thank Professor Politano for showing us how to do things, because this is exactly the kind of activities that we would like to support, we would like to promote, and we would like to create in the next month and in the next year. Thank you very much.
Thank you, Professor Pelaggi, for your very brilliant presentation of what ITASEA is doing and what ITASEA would like to do in the next time, that I think is even much more important. To strengthen the relationships between Taiwan and Italy will be your goal, and I guess that you will have success in doing this. Okay, let's see also if there is some curiosities about the activities that you have presented and the perspectives of your activity in the audience. And so I ask people to raise questions, writing in the chat. I see there is something maybe in the chat. No?
I have okay.
Just to add some comments.
Ambassador, please.
Just to say,
you want comment?
no, just want to say my gratitude to Professor Stefano Pelaggi in accepting my proposal, together with also the good blessing from my counterpart, Davide Giglio. We look forward to your good job, and I promise to organize a party to celebrate the creation of the ITASEA. So don't let me wait too much. I know you have been working very hard. So good job, and see you soon on this particular endeavor, the success of it. Thank you.
Thank you, Ambassador.
Thank you, Ambassador, for this nice, let's say, words. And maybe Antonio would like to comment or say something about?
Yes, just a comment. A good initiative to promote the Italian-Taiwanese cooperation could be the constitution of virtual joint labs. And this workshop is also designed. I hope that at the end of this symposium we could present an agreement for a virtual joint lab on advanced semiconductors. And I have also curiosity for Stefano, if he could spend more words regarding the panel of the ITASEA association in order to illustrate the Italian and Taiwanese institutions which are already involved in this important initiative.
Yes, thank you, Antonio. Yeah, well, as I said, the support of the both representative office is essential. The same idea ITASEA came during a meeting with Ambassador Andrea Sing-Ying Lee and some professor of Sapienza. So this is an association which start directly under, allow me the word, the umbrella of the two office. We are based in Italy, so it's this part, the ITASEA will be working a lot with Italian Academy, and I think that the work that we have done collecting all the existing agreement between Italian university and Taiwanese university is really important, because some of them started from people to people. So there were some professor which met other professor at a conference. They started a very lively and a very long-standing cooperation. So what is the aim of ITASEA is to bring those work, those cooperation in broad daylight, and try to use those connection, those synergy, that cooperation in order to promote more and more cooperation like this. So I think it's a really it could be a really important situation, because having the support of the Taiwan representative office in Italy, of the Italian representative office in Taiwan, the Italy-Taiwan Parliamentary Friendship Group, the European Chamber of Commerce in Taiwan, we could be able to have a powerful tool which sometimes could help even in redefining, in shaping the law and the legal framework which regulate the academics exchange and the scientific cooperation between Italy and Taiwan. We do now have a new law, a new legal framework for Taiwanese students in Italy, which can receive a grant thanks to the work of the Taiwanese representative office in Rome, and so everything. All those structures need to be implemented, and this is exactly what can implement this. So meeting, cooperation, having more and more students, more and more researchers and professors to be in contact and to be ready when in a few months we do hope that there will be a renewed possibility to travel between Taiwan and in Italy, and at that point we do hope that we will have a really complete framework to start a really solid scientific and technological relationship between the two countries.
Okay, thank you. Quite exhaustive. Is there any other question?
Just another comment. Congratulations for the nice virtual stand prepared by Stefano on the platform. So I invite you to visit it. There are very interesting news also regarding the story of Taiwan with a very nice podcast.
Yeah, I confirm. That's quite interesting indeed. Okay.
Thank
So
you.
let's
Thank you very much.
Please, who is speaking?
No. I was thanking Professor Politano.
Okay. We thank Professor Pelaggi then for his brilliant presentation, his enthusiasm in strengthening the relationships between Italy and Taiwan. And we think that something more will happen in the future following the guidelines that you have presented, and following also the important cooperation with the two representatives of Italy in Taiwan and Taiwan in Italy. Well, let's move to the next speaker, which is Professor Antonio Politano from the University of L'Aquila. Antonio, I know Antonio since, let's say, 5 or 6 years, and I have seen the last part of his brilliant career, and he's really an eclectic scientist. And let's see what he's presenting today. Italy-Taiwan cooperation on science and technology on advanced material. Focus on surface science with layered materials and novel topological phases of matter. Antonio, please, the stage is yours. We are perfect in time. Let's try to keep the schedule correct. Please.
Thank you, Maurizio. I'm Antonio Politano, and I will present some milestones of the Italy-Taiwan cooperation on science and technology with advanced materials, with a focus on surface science with layered materials, mostly van der Waals semiconductors, and novel topological phases of matter. In the last years, the number of co-authored papers on material science by Italian and Taiwanese partners is increasing so much. And after the advent of topological materials and two-dimensional materials, this collaboration had a boost. A good contribution in this collaboration comes from surface science, which is an interdisciplinary research field at the boundary between physical chemistry, condensed matter physics, and material science. From the study of chemical reaction at surfaces and interfaces, it is possible to discover the physico-chemical mechanism ruling the surface processes at the basis of gas sensing, photocatalysis, electrocatalysis, and so on. Surface science also studies collective electronic excitation at the surfaces, such as surface plasmons, and I will present some example of plasmonic devices with Dirac materials. The Italian-Taiwanese collaboration, with a particular contribution from Shan Lue and his group at the National Cheng Kung University, starts in its activities from the growth of single crystals and their exfoliation in nanosheets by means of liquid phase exfoliation. Materials are usually topological phases of matter or van der Waals semiconductors. Their electronic properties are investigated by means of spin and angle resolved photoemission spectroscopy at Elettrasynchrotron in Trieste. And today we will have a talk by Ivana Vobornik, beamline scientist at Elettrasynchrotron. Plasmonic excitation and surface chemical reactivity are investigated by means of high-resolution electron energy loss spectroscopy, HRELS, and core levels are investigated by X-ray photoelectron spectroscopy, also with synchrotron radiation. All experiments are complemented by density functional theory. This platform combines growth characterization, but also application in the field of catalysis and gas sensing, optoelectronics, and plasmonic applications such as plasma wave Terahertz photodetectors, and thermoplasmonics, also with the implementation of new applications such as photothermal membrane distillation for seawater desalination. Tomorrow we will have a talk on this activity. These are the most recent highlights of this collaboration, and I will start discussing the main features of physicochemical properties of surface of advanced materials, and then I will discuss regarding application in the fields of catalysis, gas sensing, ambient stable optoelectronic devices, and finally plasmonics. The materials which are investigated in this collaboration often display topological electronic states, as for the case of Dirac semimetals. The presence of massless Dirac fermions comes from the presence of linearly dispersing electronic bands. And this has been revealed for the first time for graphene, which is a monolayer of graphite, and for surface states of topological insulators. But both graphene and topological insulators are not particularly suitable for large-scale industrial exploitation, because graphene is just a single layer of graphite. And it is difficult to think to a large-scale industrial application of a single layer of carbon atoms. On the other hand, topological insulators only show surface states in highly crystalline surfaces. So it is very difficult to get industrial application with topological insulators. Accordingly, a three-dimensional analog of graphene will be highly desired, and this is the case of Dirac semimetals, which have been experimentally realized only in 2014 for systems showing high chemical instability, such as sodium-free bismuth. So materials with linearly dispersing electronic states already in the bulk are highly desirable. And three-dimensional Dirac fermions will be naturally robust against in situ surface doping, such as environmental contamination, because of their bulk nature. Moreover, usually these materials display ultra-high mobility of charge carriers and giant values of the magnetoresistance. So they are particularly suitable for application. Currently, the interest from the scientific community is moving from type 1 to type 2 Dirac semimetals with tilted Dirac cone. Platinum ditelluride has type 2 Dirac cone, which is located around 0.7 electron volt below the Fermi level, so it is a good system for infrared application, but not for terahertz photodetectors. Currently, we are engaged in the cast of new materials with topological states around the Fermi level. And this is the case of nickel ditelluride, which has a bulk-derived Dirac cone around the Fermi level. And it is naturally a candidate for terahertz technology. By means of angle-resolved photoemission, we discovered the presence of low-energy type 2 Dirac fermions in nickel ditelluride. And we also demonstrated that surface states in nickel ditelluride have a strong spin polarization, reaching around 50%. So it is a good candidate for spintronics. Nickel ditelluride is also a material showing an outstanding ambient stability. As you can see, the morphology of a nickel ditelluride flake does not change even after 10 days in air. in contrast with the case of black phosphorus, which is completely degraded even after a few hours in air. By combining X-ray photoelectron spectroscopy with low-energy photons with density functional theory, we are also able to follow the chemical reactivity of the system. For the case of nickel ditelluride, we discovered that the surface gets an oxide skin which remains subnanometric even after 1 year in air, because the tellurium oxide skin reaches just a passivation layer of 0.8 nanometer. The surface of these materials are also directly exposed to small molecules in vacuum condition in order to understand the main features of their catalytic properties. In particular, for nickel ditelluride, we demonstrated that the surface does not react towards carbon monoxide, so the surface is not affected by the problem of carbon monoxide poisoning, which is commonly affecting each nickel and platinum-derived alloys. So nickel ditelluride and related materials are suitable for catalysis, and combining information from density functional theory, we are able to tailor the catalytic activity, which is also tested by electrocatalytic experiments in hydrogen evolution reaction, so the production of hydrogen, and oxygen evolution reaction. We are also able to put in evidence the real physicochemical mechanism ruling catalysis with these materials. As an example, for platinum tin 4, we discovered that the Tafel slope is very similar to the case of pristine platinum foil, in spite of the replacement of platinum atoms with a cheap tin atoms, with a big advantage for large-scale exploitation because of the reduced cost of the electrode. The main reason of the enhanced electrocatalytic activity of platinum tin 4 comes from the formation of a tin oxide skin revealed by means of X-ray photoelectron spectroscopy. The formation of a metal oxide skin also occurs for the case of metal chalcogenides. In particular, gallium selenide and indium selenide, once exfoliated in nanosheets, display a superior electrocatalytic activity in hydrogen evolution reaction. The formation of this metal oxide van der Waals semiconductor heterostructure is a good platform for gas sensing, as we demonstrated for the case of tin diselenide, which has been also tested for gas sensing for both oxidizing and reducing agents. We've also implemented devices based on topological materials and van der Waals semiconductors. We fabricated the simple microwave receivers, and already in the first implementation, we found that palladium ditelluride has a superior performance compared to similar devices based on black phosphorus and graphene. You can see that the photocurrent is 1 order of magnitude higher than the other materials. And moreover, the stability of these devices is really outstanding. Even after 1 month in air, the photocurrent does not show any noticeable changes. We also implemented the Terrace photodetector based on topological materials. Very briefly, Terrace is a narrow window between the microwaves and the infrared, and we have not good detectors or sources of Terrace light. However, Terrace is particularly relevant for application. Many organic molecules have Terrace resonances. Terrace light can pass through the clothes and detect the presence of hidden metals. And so it is particularly relevant for application for body scanner, for the protection of homeland, so in airports, for biomedical application, and for cultural heritage. We carried out Terrace imaging experiments with novel topological materials, finding that it is possible to detect the presence of a metal nut inside an envelope, which is invisible at naked eye, in just 30 milliseconds with a source of 0.12 terahertz, and similarly for a source of 0.3 terahertz, just 20 milliseconds were sufficient to detect a knife. Finally, we are also interested in plasmonics to find new candidates for plasmonics. Historically, plasmonics has developed with silver, gold, and alkali metals, which display resonances in the ultraviolet. But now we are searching materials with resonances in the infrared, in the visible range of the electromagnetic spectrum, with the highest carrier mobility as possible. We found that platinum ditelluride as a new kind of plasmon modes, three-dimensional Dirac plasmons, which occur in the near infrared with an energy of 0.5 electron volt, with other interband plasmons at 1 and 1.5 electron volt. Moreover, we also discovered that tilted type 2 Dirac semimetals also display a new mode due to the out-of-plane oscillation of the density deviation in electron and hole pockets. And this is a gapless and undamped plasmon, which only exists in these materials. In conclusion, thanks to the collaboration of Italian and Taiwanese partners, we discovered that type 2 Dirac fermions exist in platinum ditelluride and related material, which are transition metal digital cogenites, hosting spin polarized surface states. So they are good candidates for spintronics. The surfaces of these materials are stable in air with just sub-nanometric oxide skin, even after 1 year in air, and the surface is not affected by carbon monoxide poisoning. So it is a good candidate for catalysis. We found good performances for hydrogen evolution reaction and oxygen evolution reaction. And we also implemented microwave receivers and Terrace photodetectors, finding state-of-the-art performances already in the first implementation. And finally, we explored the plasmonics with novel topological Dirac semimetals, finding the occurrence of new excitation, in particular three-dimensional Dirac plasmon in the near infrared, which are suitable for applications such as night vision devices. And we also predicted a novel undamped plasmon, which only exists in type 2 Dirac semimetals. So thank you for your attention and enjoy this bilateral meeting. Maurizio.
Okay, sorry. Thank you so much. I was saying, Antonio, for this brilliant presentation, which tell us something about a success story of true, real collaboration between Chinese institution in Taiwan and Italian universities. Well, questions? Time for questions or curiosities? Please, Ambassador.
Yeah, just to say the two words in congratulatory message for the excellent presentation. So I look forward to seeing all of you in presence, maybe in a Taiwanese restaurant, because we believe that this is a very exciting moment when we initiate. For me, this is the first time I can witness such a successful scientific and technological and academic exchange. So I look forward in mingling with you to learn in person and more closely with you in the future. So because of my agenda, I regret I need to leave the floor, but I wish of you the conference, a very successful one again. So I will be in contact, and I look forward to seeing you very soon in the future also. And also, I just take this opportunity to say hello to my counterpart, my good friend, Minister Davide Giglio, for your excellent job in Taiwan. So look forward to seeing you all soon, and have a very nice day.
Thank you, Andrea.
Thank you, Ambassador and Andrea. And
Ambassador, I look forward to come in Rome to the Taiwanese restaurant.
Yes, I wait for you.
Okay. So
if I may also say something.
Disagreement, yeah? We all are witnesses of disagreement. Well done. Well done. Well, some technical question for Antonio?
Professor Peruzzini, I would like also to say goodbye to Ambassador Lee, and I will also have to take my leave. I will put up a Facebook post on the Italian office website about the event that is taking place. And whenever it would be possible, and this is a question addressed to Professor Politano, if you will have us have maybe a resume of the outcomes, because I will certainly share it with in my contacts here with Ministry of Science, which is present, of course, but also with other Taiwanese institutions, as evidence of the potential that Italy and Taiwan have in this area. So it will have to be something short, but that I can use for in my activity. I believe maybe this would be also useful for Ambassador Lee.
Certainly.
For sure.
Sure.
Arrivederci, a presto.
Grazie. Thank you so much.
Thank you.
Time and good luck for everything.
Grazie ancora professor Peruzzini e professor Politano e a tutti i partecipanti italiani.
Grazie.
È veramente un piacere, ho imparato molto anche.
Thank you so much for your kindness, for being with us. We appreciated a lot of your time and your participation with, let's say, ideas and perspectives to this meeting.
Please do count on my office for any follow-up and for future similar initiatives like this one, which I highly commend. Thank you very much, professors.
Surely.
Thank you so much.
Keep in contact.
Arrivederci.
Arrivederci. So, Antonio,
can make a question?
Yes.
Yes.
Hello,
Do you want to raise a question?
Yeah.
Great.
Thank you, Antonio, for the excellent, impressive presentation. Just a very small question. Concerning the oxygen and the hydrogen evolution reaction, what is the scale-up potential of these materials?
For hydrogenation reaction, we have studied mainly the physicochemical mechanism ruling the catalysis. We find that, for example, platinum tin 4 has a very good potential for technology transfer, and thanks to the capability of the group of Professor Shan Lue, I believe that there are all possibilities to a large-scale industrial exploitation, because already in the first implementation, the performance for hydrogen production, so hydrogenation reaction, is already competitive with platinum foil, with cost reduced by 70%. So the direction is that.
That's
Thank
clear.
you. Grazie, Antonio.
Is any other questions?
Yeah, I have.
Yes, please, Alessandro. Nice to see you.
Ciao to everybody. See you. It's a pleasure. So, Antonio, I have a technical question just to wrap up actually and go quickly. So, about the Valsem method that you mentioned in the type 2 form. So, what do you think actually is the temperature range of operation? So, are they operated at low temperature, or they can be available at room temperature?
In all our experiments, we use room temperature. One of the main advantage of Dirac semimetals that we have exploited as an example for terahertz photodetectors and is just that topological states exist at room temperature. And another advantage is that we do not use any capping layer, so any encapsulation strategy is required. And this is a big advantage for nanofabrication with the possibility of large-scale industrial exploitation.
And do you think that the topological character still remains at low thickness, so just to have a thin film with the topological characters in the vial semi-metal form?
No, we are investigating bulk form because for Dirac semimetals the topological states come from the bulk, because bulk valence and conduction band of the bulk form linearly dispersing bands. Moreover, this system also displays topological surface states with spin polarization. Concerning the exfoliation in nanosheets, one important issue is that the topological states only emerge for 3-4 layers. So the single layer is actually not topological material. It is definitely a semiconductor, a trivial semiconductor.
Or at least or a metal if it is in a 1T prime form. Yeah, but this is exactly what I wanted to know actually, because it's so you need to actually increase the thickness to
Yes.
to impart some topological character. And I would be pleased actually to know that the Taiwanese guys actually would be interested in this kind of materials for establishing collaborations, something like that.
I'm sure that Taiwanese speakers of this workshop are expert in growth and synthesis. So also the expertise is complementary to yours, because you are an expert of epitaxial growth, while as an example the next speaker, Shan Lue, is an expert of the growth of bulk crystals. So I think that we can move in a joint direction with Shan and you.
Thank you.
Thank you, Alessandro, for this question, and thank you, Antonio, for your answer. I think that we are in time for going ahead with the presentations. Let's thank Antonio, and let's move to the next speaker, who has been already mentioned. There is Professor Shan Lue from the National Cheng Kung University.
One of the chairmen of the bilateral workshop.
Okay. That's important as well. And he will talk about the Italy-Taiwan cooperation on advanced materials, and we will speak about the contribution from the National Cheng-Kung University, indeed. Please, Professor Lue.
Yes. Can you see my screen?
Please. We can see.
Yes.
Okay.
Your presentation.
Okay. Okay. Thank you.
You can go to the presentation mode.
Okay. Good morning, Italian friends, and good afternoon, Taiwan. In this presentation, I will share my experience with the cooperation between Taiwan and Italy on our single crystals. Dr. Jianong Guo is the key person who grew these crystals, and my name is Shan Lue. I teach in Physics Department of National Cheng Kung University, and I recently joined the program on key materials in Academy of Innovative Semiconductor. I'm also a member of TCEC, and this was supported by Ministry of Science and Technology, MOST. First, allow me to briefly introduce to National Cheng Kung University. Okay, like this, the map of Taiwan, and the National Cheng Kung University is a public research university located in Tainan. Tainan means southern Taiwan, and the capital Taipei means the northern Taiwan. And this university was founded in 1931. It was 90 years old, and last month there was a 90 years anniversary. And the Physics Department of NCKU was founded in 1956. It's 65 years old, and this is a big banyan tree in one of the campus. It's so big, so beautiful, and it became a logo of an insurance company. The Crystal Growth Lab was established in 2012, about 9 years ago. We have 10 furnaces of different kinds, including box furnaces, vertical furnaces, tube furnaces, and two-zone furnaces. And this is the photo picture of Dr. Guo Jianong. Jianong used 3 different methods to grow the single crystals. The first one is the flash growth method, and here I show 9 representative pictures of the crystals. Each individual has its own interesting physical properties. For example, MbTe4, this is a needle-like crystal, is a one-dimensional charge density wave material. And CuTe is a novel CDW material. PTTE2 is a Dirac semi-metal. PDSE2 is a 2D semi-metal. And these 2 are superconductors. The second one is called the CVT growth method. Jianong already grew many 2D materials using this way. And for this one, MBP is a wire semi-metal with a very high fast mobility of the carriers. And this one, CRPS4, MMPS3, MMPSE3, they are van der Waals materials with anti-ferromagnetic ordering. And these are materials, so-called ferroelectric materials. The third one is called the Bridgman growth method. And for example, tin arsenide is an important superconductor, and tin selenide is an important thermoelectric material. This material has a very low thermal conductivity. In the very beginning, we focused on so-called 4 3, 4, 13 systems. These materials show very important interplay between lattice distortion and superconducting ground states and or magnetic ground states. Up to now, we already published more than 10 papers based on these materials, and most papers are published on Physical Review B. About 5 years ago, Jianlong Group start to grow transition metal dichirurgianized. Okay, Jianlong can grow the very large and high quality TMD materials, and each material, each material shows very sharp spots from the Raoult diffraction patterns. It confirms the good crystallization of these crystals. For TMD materials, in addition to their topological surface states, each shows interesting physics properties. For example, PDT2 is a superconductor. PDSE2, PTS2 are 2D semiconductors, and the VSE2 is a CDW material with transition temperature of about 110 K. Okay, about 5 years ago, we started to cooperate with Professor Politano of University of L'Aquila. Okay, we quickly have published 2 papers on top journals based on PTTE2. This one was published on Physical Review Letters. Physical Review Letters is the best journal in physics. Up to now, this article has been cited by 50 times. Another was published on Advanced Functional Materials. This is a high impact journal in material science. So this article has been cited by 40 times now. We then extended the cooperation with more Italian groups. So these institutes are scattered all over the country of Italy, from North Milano to South Calabria. So these are very, we have very wide cooperation with the Italian institutes. So our cooperation involves very rich research topics. So these are papers related to the optoelectronics. They are published only within 3 years. These results demonstrate these crystals can be used to fabricate terahertz antenna and terahertz detectors. So our crystals can also be applied to the field of catalysis. So these are the presented papers about the issue of the catalysis published in within 2 years. Okay. So those crystals are correspond to the materials for the catalysis application. So these are papers related to the issues of gas sensing, and so these are papers related to the issues about plasmonics. These are the presented papers that relate to the issue of about the science, surface science, and the topological physics. So overall, we have delivered more than 20 papers in 3 years. Most were published on top journals like Physical Review Letters, Nature Communications, Science Advances, and the ASCS Narrow. Recently, Jianlong grew a variety of 2D semiconductors for the transition metal based compounds. people are more interested in their magnetic properties because they belong to the so-called 2D van der Waals ferromagnets. In addition to their important properties in magnetism, I think I propose to study the possible applications on photoelectronics because of their semiconducting behavior. For example, these materials are direct band gap semiconductors, and they should be good candidates for application in light emitters and lasers. Okay, and for this one, one shows the ferroelectric ordering above room temperature, and would be a good candidate for ferroelectric applications. So finally, I think the great contribution from Professor Politano on the promotion of the cooperation between Italy and Taiwan, and I expect to see a more extensive cooperation between these two countries after this symposium. And finally, I think that I need support from NCKU, TCECM, and MOST. Okay, I think I start here. Thank you.
Ogni volta Peruzzini accende.
Thank you so much, Professor Shan Lue, for your presentation and for let's say the collection of beautiful examples of great materials that are being growth in your laboratory, and the many publications that are resulted from them. If there are questions or comments or suggestions for possible collaborations, please, they are welcome.
I have just a question regarding the possibility to a large scale production of platinum tin 4 as an example. If we identify a material which could be suitable for hydrogen production as an example, the need of a large quantity supply to industries will be challenging. Can you comment on it?
And Antonio, I don't quite understand
I'm asking if it is possible to produce a large quantity of platinum tin 4 or similar materials for industrial application to increase the quantity of crystals.
We will try. We will try. It might be possible. Yeah, we will try. Yeah.
Yeah. To go from grams to kilograms. I think that it will be demanding. This is the goal.
There will be different techniques and.
Do you think that it is the scalability? Do you think that it is feasible?
Yeah, it's possible. Yeah.
Okay. If there are no any other questions, let's thank Professor Shan Lue. Thank you so much for your presentation, for staying with us. And by the way, I've seen that you have a collaboration with my institute, ICCOM in Florence. I'm very happy of that.
Yes,
reaction, I guess. Yeah.
Andrea Marchionni, Francesco
Marchionni, and the people of Francesco Vizza as well. Quite good. Well, let's move then to the next speaker. She comes from CNR, the Institute Officina dei Materiali in Trieste, and there is a double affiliation with Elettra Synchrotron, also in Trieste. The speaker is, I guess, Dr. Ivana Vobornik from Croatian in origin, and she's currently working in Trieste, I guess. Please, Ivana, you will present your lecture about direct insight into the electronic band structure and spin properties of novel topological materials. Please, go ahead. And try to stay for 20 minutes. We are a little bit in.
Yes, I will try to do my best. Good morning and good afternoon to all colleagues. It's a great pleasure to participate in this.
Can you move to the full screen presentation?
I guess I did so, but let's then try to. Just one moment.
Otherwise, it's okay anyway.
You are not seeing the full screen?
We see your comments.
You're seeing the one with the notes. Okay, okay, let's get out of this. Just 1 second.
And then
From
down.
slide and show. Okay.
Yes, yes, yes.
Okay.
I did that, but I don't know why you are. Okay, let's do one thing. I do this.
Just a few seconds, I guess. Okay. No.
Is it now better?
Yes, yes, okay.
Okay, excellent. Thank you. So then again, good morning and good afternoon to all colleagues, all collaborators, all participants to this workshop. It's a great pleasure to take part in this initiative, and I would like to thank the organizers for inviting me to participate in this workshop. Thank you, Chairman, that you pronounced nicely my name. Yes, indeed, it's not Ivana, it's Ivana. I'm Ivana Vobornik. I'm a scientist at the National Research Council of Italy in the Istituto Officina dei Materiali, that is here in Trieste, in Italy. So our previous Professor Liu previously showed the map. So we are at the very north of Italy. You can see here also the very north part of Mediterranean, where Trieste is placed. But Trieste is also having the image of scientific city, so a number of important campuses and a number of important facilities are placed in Trieste. You see my affiliation is CNR-IOM, but in fact IOM is also managing a number of beamlines at Elettra Synchrotron, so I'm beamline scientist at one of them, at APE beamline. This kind of little vehicle here in Italian is called APE. So you will be, this is a sort of a symbol of our beamline, but APE is also operating not only within Elettra facility, but also within NFFA Trieste facility, which I think can be also quite appealing for future collaboration with Taiwanese partners. The outline of my talk is the following. Is already introduced by a previous speaker, and in fact, our recent collaborator. I will be speaking about novel topological materials. These are typically two-dimensional materials where strong spin-orbit interaction induces spin momentum locking. And they are also hosting the first solid materials that are hosting relativistic quasi-particles, such as Dirac, Weil, Majorana fermions, and so on. Our collaboration, in fact, we were involved in collaboration through Professor Politano. We got involved in 2019, and from that moment on, we published 6 papers, and it's important to say also that we are working in a difficult time of pandemic restrictions. 4 of these papers in very high impact journals. So we have 1 Nature Communication, 2 Advanced Functional Materials, 1 ACS Nanos, as already listed also by the previous speaker. And the case study that I will be mentioning here are related to these 3 materials: nickel ditelluride, nickel tellurium selenide, and platinum 3 tellurium 4. In all this, the facilities that are here based in Trieste were strongly involved, mainly by angle resolved photo emission with also spin resolution, but I will also briefly introduce other possibilities that are available here for eventual future collaborations. Among the collaborators, of course, these are our Taiwanese partners. We have Antonio at Aquila. We are here at Trieste, and of course, important partner is also Indian partner who supported us with theoretical calculations. Let me introduce my laboratory. Up a beamline, we say beamline, but in fact these are two beamlines. This is unique such configuration at Elettra synchrotron. These are two canted beamlines. They can operate contemporarily, and we make this division between low energy and high energy based on the photon energy range that we cover. Low energy branch is dedicated to high resolution angular resolution photo emission with spin resolution from recently. And at high energy, it's possible to do XPS, XAS, XMCD, XMLD spectroscopies, and from recently also the spectroscopy in Arando and at ambient pressure. But the core of our business is basically here, which is zoomed on the right-hand side of my slide. We indeed have two powerful spectrometers that receive radiation from Elettra, but as you see, they are connected in situ, and we have a number of offline facilities to prepare or to characterize our samples. We have also the growth possibility, so we can grow our own samples by in situ pulse laser deposition. We have STM, which is operating with atomic resolution, and then any sample can travel between all of these possible facilities here that are operating within NFFA Trieste. The core of our business, especially on the ARPES side, is the spin resolution. Spin resolution is crucial for the kind of materials that we are studying nowadays. Our spin detector is called VESPA, which stands for Very Efficient Spin Polarization Analysis. The scheme is here. We can analyze the photo-emitted electrons in terms of their energy and momentum. And get the energy dispersion, and then we can also get it in a spin resolved mode, and these are an examples of spin polarized states in two different systems. Our experimental chamber was in fact in the time that we introduced the spin detectors also presented in the Journal of Synchrotron Radiation, and this is the scheme of how it looks like, and I hope that our colleagues, also through the programs of exchange that were introduced today, will be able to come and to see how and where we are working. So topological materials, let's introduce briefly. Some words were already spent on those. These are typically two-dimensional materials. So if you speak about two-dimensional materials, the easiest two-dimensional case is a surface of a metal. On a surface of a metal, you can often find the surface states, which basically behave like free electron states on the surfaces. Their dispersion is parabolic, like this. But then if you introduce spin-orbit coupling in heavy metals, for instance, like gold, Rashba interaction will split this parabola, free electron parabola, in two, each for a certain spin direction. If spin-orbit interaction increases further, the two parabola are further shifted, and you end up with a sort of a linear dispersion, and each branch of this dispersion is of certain spin polarization. So this is what we speak about when we speak about Dirac electrons and spin momentum locking, for instance, in topological insulators. Relevant quantities here are, as you see, electron, momentum, and spin. And the only technique that allows the direct access to all of them is spin and angle resolved photo emission. This is, of course, based on the photoelectric effect. The outgoing electrons, when photoexcited, are bringing the information about their energy, about their momentum, and about their spin inside the material. And then, indeed, it was possible to measure the spin polarized states, surface states of gold when commissioning our instrument, when commissioning VESPA, but also we did the work on topological insulators that were grown in our PLD system. So this is bismuth selenide, famous topological insulator with two spin polarized branches of the Dirac cone. As I said, topological materials are hosting relativistic quasi-particles such as Dirac, while Majorana, and then now there is all new classification of materials like Dirac semi-metals of type 1, of type 2, while semi-metals type 1, type 2. In our talk, I will stick to Dirac ones. So we will be looking either I would say, straight or tilted Dirac cones, and we will try to see how they can exploit it in applications. Fortunately, some of these applicative aspects were already handled by Antonio in his previous talk. Transition metal dechalcogenides, as the name said, these are materials formed by transition metals surrounded by chalcogenide atoms, such as sulfur, selenium, or tellurium. They are layered materials. They have a strong intralayer covalent bonding and weak van der Waals interlayer coupling, which allows them then to be exfoliated similarly to graphene. And depending on the filling of the transition metal d electrons, their ground state can be either semi-metallic, metallic, semiconducting, or superconducting even. And despite the fact that we always push for their two-dimensional properties, properties are in any case conditioned by the number of layers. So for instance, famous example is molybdenum disulfide, which is indirect band semiconductor, but becomes direct gap semiconductor in a monolayer form. Independent on that, many of them host very strong spin-orbit interaction, and this spin-orbit interaction in one way or another produces strongly spin-polarized states. And therefore, they are very suitable and very much investigated candidate materials for future spintronic applications. So yes, this is what I basically said. They are in fact also candidate materials for this kind of architectures of two-dimensional van der Waals heterostructures. But in order to implement them into future devices, it's important to get knowledge and control of their electronic and spin properties. So in our work, in our collaboration, we in particular concentrated on group 10 transition metal dechalcogenides, where for the first time type 2 Dirac fermions were spotted. So type 2 means that this Dirac cone is not anymore along the energy axis, but it's tilted due to Lorentz violation. And what this implicates is that the Fermi surface is then formed by open electron and hole pockets. And this can result in phenomena such as magnetoresistive effect, where the material conducts electricity only for a certain alignment of electric and magnetic fields. Our collaborators and colleagues from the UK were the pioneers who investigated palladium and platinum-based dechalcogenides, and in fact, they, with very careful analysis, understood that the chalcogen p electrons, through interplay between crystal field splitting, spin-orbit interaction, and bonding anti-bonding splitting, result both in the bulk Dirac states and in the topological, in a numerous topological surface states, which they call the ladders in this material. But the point for both platinum and palladium based materials, this bulk Dirac point, which we were mentioning, is quite low in the occupied states. So it's not suitable for the real applications of these materials. Typically in topological physics, the heavier is the better. So maybe for this reason, nickel counterpart, which is the lightest here, was neglected, but there was a recent work that was predicting that the bulk Dirac point in nickel ditelluride would be very close to the Fermi energy. So this is the material that our Taiwanese colleagues produced, and we studied the electronic properties and indeed found that bulk Dirac point is very close to the Fermi energy, slightly above the Fermi energy though in this particular case. But besides that, this material was also found to host a number of spin-polarized states, both deep at higher binding energies, but also very close to the Fermi energy. And in fact, the proximity of the spin-polarized surface states to the Fermi energy was successfully implemented in the realization of high-frequency rectifiers. We then move to a similar compound. So here, some tellurium was substituted with selenium. So this is nickel tellurium selenide. And indeed, this small play, I would say, with the structure or with the constituent atoms, allowed us to bring the Dirac point below the Fermi energy. Now the Dirac point in this particular case is at 250 milli-electron volt below the Fermi energy. In fact, well, I'm not showing you here, also in this particular case, there are a number of spin polarized surface states. But what was interesting, the fact that this tilted Dirac cone was below the Fermi energy, is that it was possible to implement this material in a microwave receiver, which was earlier also presented by Antonio. What remains of my time, I will just dedicate to present the facility that we have in Trieste, which is NFFA Trieste. This is a facility, meaning open to anyone, open to scientists worldwide. They can, of course, check our website, they can check our catalog and decide the experiment they would like to do and apply for doing their experiments. Just a little bit of hint of what kind of approach, of what is the advantage of the approach that we can offer. This is an example of the study that we did on platinum 3 tellurium 4. This is not dichalcogenide, but the structure is a little bit more complicated. We have alternating layers of platinum ditelluride and platinum 2 tellurium 2. And with the three sets of techniques here, we were able to identify different surface termination that this material can offer. So it can terminate either at platinum 2 tellurium 2 or platinum tellurium 2, as seen by scanning tunneling microscopy, and seen also by XPS. Further, we extended the study also to angles of photoemission. Both of these terminations are hosting, in fact, distinguishable electronic states, which then we could link to the determined termination, but also both of them are hosting different spin polarized states. And in fact, this kind of configuration of different spin polarized states at the surface of the same material is quite appealing for spintronics applications. So I hope that with this, I gave you a hint of a case studies of the materials that we've studied so far in collaboration with Taiwanese counterparts. And I also am inviting you to join us in Trieste. Hopefully times will be better and we will be able to extend our collaboration in person. I'm now not mentioning here, but there are many new materials that we plan to investigate in the framework of this collaboration, and I hope that we will be able to present in future new results regarding the continuation of this collaboration. Thank you very much for your attention.
Thank you, Ivana, for your very exciting presentations, very complete, very exhaustive. And I hope that you have raised curiosities in people on the other part of the screen. And so time is for questions. Please, curiosities as well, or technical questions are welcome. Let's see, somebody will present some, will raise his hands.
I have a curiosity on the feasibility of spintronics with these materials. Can you comment on it?
Of course I can. We have wonderful collaborators such as Antonio, who is taking care, in fact, of these applicative aspects, because I myself am doing fundamental research, basically dealing with electronic band structures and spin structures. So once we identify the candidates, it's very important to have a collaborator who is able to pick up the candidate material and try to build a real device. And this, I think, is a very big advantage of the collaboration that we are currently having, because the applicative aspect is often not treated adequately, because these are new materials and, of course, quite challenging. So one has to really invest the time and the vision as well in exploring their properties. So I think in this collaboration, this is being done quite successfully, and I hope we will continue in the same direction. Hopefully also with Taiwanese food and maybe Italian wine put together.
Surely. I'm not sure about Taiwanese wine, but for Taiwanese food, I can confirm that is really an excellent Chinese cuisine. Very, very peculiar and very good. So I have
I agree.
Okay, thanks. So
thank you.
Just another question or curiosity, let's say more curiosity than question. Many years ago, as I was young, I was working in homogeneous chemistry, and I published 3 or 4 papers describing metal complexes containing nickel, palladium, and rhodium containing ditellurium unit as a ligand. I mean, complex in which, for example, 2 nickel atoms are sandwiched by a ditellurium unit, nickel, tellurium, tellurium, nickel, forming a sort of microclusters stabilized by additional phosphine ligands on the 2 metals. So I am wondering if this kind of, let's say, molecular materials could be used as precursor to synthesize, let's say, nickel ditelluride, for example, rhodium ditelluride, or similar compounds. Do you have idea that this kind of molecular compounds have been ever used for approaching this synthetic chemistry?
Well, from my point of view, intuitively, I could say yes. I think this would be more of a question for Professor Luo and collaborators who are really doing the growth and the synthesis of materials. I typically, you know, when we are interested in a material, we express our wish list, and then a good grower picks up the wish list and produces the material. Yes,
that's correct.
But as I said, we are also having. Okay, I haven't introduced much maybe in this particular case, but we have in situ pulse laser deposition. So I guess in view of the pulse laser growth, it could be possible also to discuss the issue maybe a little bit in more detail. Certainly, we can do it also after the completion of the workshop.
Yeah. Okay, thank you, Ivan. It was just a curiosity. Other questions?
I have a sort of like a general question. So, actually, Taiwan is developing some laser RPS and time-resolved RPS. I think Professor Chih-Wei Luo is in charge of that development. So I wonder if there's some collaboration between your institute and, say, the Synchrotron Radiation Research Center in Taiwan.
In fact, at the moment, not yet. I was taking carefully notes from the presentation of Stefano Pelaggi earlier. I think this kind of collaboration and exchange of students and scientists as well would be crucial to deepen our knowledge. I think we could profit immensely, both counterparts, from this kind of exchange. So I'm in fact looking forward to strengthen this kind of this aspect, particular aspect of collaboration. We are always in search of young and talented students or postdocs who could join this research and also be trained in the techniques that we can offer here, bring their knowledge back to their home laboratories, and bring also to us the knowledge that they have from the training at their home laboratories. So that is an excellent aspect of the collaboration, which I hope will be further extended in near future. So we will definitely keep in touch, and I think
so I think one of the important result of this meeting is mission of this meeting is Antonio and Chin-san need to like list give us a list of the expertise on both sides, and maybe you can do some matchmaking, and it'll be wonderful.
Exactly.
Thank you.
That's
exactly.
a good idea indeed.
Yes.
Okay. Is there any other question for Ivana?
No.
If not, we thank Dr. Vobornik, Ivana, and we move to the next speaker. Thank you, Ivana.
Thank you.
The next speaker is Professor Alfredo Davide Ferella. He comes from the University of L'Aquila, from the Department of Physical and Chemical Science, but at the same time is, let's say, working also at the Gran Sasso National Laboratory, one of the most important, let's say, center for nuclear physics in Italy, and I would like to say in Europe, at least. And we are a little bit in delay, but you have all the time that you need. It is about 20 minutes for your presentation, including some questions. Please, Professor Ferella.
Thank you very much, Pierre, for the nice introduction. And thanks. I would like to thank Antonio and Carlo for giving me the possibility to present you some exotic topic. But I think since you are looking for applications to
Alfredo, may you speak a little bit loudly, please?
Yes, I'm trying to. Is it better now?
A little bit.
Yeah, okay. So I will try to shout.
Yeah. Thanks.
Okay. So yeah, I'm trying. So we in our field, which is more fundamental physics research, we still have the need to find some new materials for the detection of dark matter, and so I, together with my colleagues that I'm listed here, have started some work still at Stockholm University, but I still keep my involvement or interest in this kind of researches, and I will try to done so far. So yeah, so here is the content of my presentation. I will give introduction of most of you motivated from the field of dark matter, so I need to. This is important for motivation. Then I will tell you how we detect the dark matter. I will tell you how dark matter detection. So as an introduction, I need to convince you that dark matter exists in the universe, in the sense that we see it in its impact in gravitational at different scales from the galactic scale. See my mouse, right? And so you when you base your observation on the rotation speed of stars in the galaxies and also on gas in the interstellar medium as a function of the position within the galaxy. If you use only the luminous matter from the galaxy, then you expect in an exponentially falling type of behavior. However, what we see is instead observations is a flat rotational curve, and this is an indication that there is some other matter that we don't account for with that curve, that is there, and then it produces in the galaxy a halo. Then we have also other type of observations at different scales. When we put together all the information, then we get a picture that tells us that only 5% of the matter in the universe is ordinary matter, mainly what we have been discussing so far in this symposium. The rest is something that is called dark matter, and something that is even more obscure, that is called dark energy. So now I don't think I need to convince you that dark matter exists.
but it's still it's a puzzle that remains because we know that dark matter is matter. It leads to the formation of structure and galaxies in our universe, and this comes from observations, from current observations, and also from cosmic microwave background observations of the small fluctuation in the temperature, and also we know that we have a model that is called the cold dark matter model that gives us some precision measurement or precision predictions on the composition of the universe and on dark matter existence. However, what we measure escapes our understanding, and because we know that there is 81% of matter in the universe that is of unknown nature. We want to understand what is the nature of this dark matter. So let's recap what we know about dark matter or what we don't know. So what we can exclude, it cannot be. So as we said, it exists, and if we want to, if we look at the structure formation, so at the large scale structure, so-called, in the universe, in the current universe, then this dark matter has to exist since the early universe. We have constraints from astrophysics and for searches for new particles. So what we know that it is the particle, the dark matter particle has to be massive because it has some gravitational interaction. It is long-lived because it comes from the Big Bang, and in the Big Bang it was already there. It is electrically neutral, otherwise we would have electromagnetic interaction. It is non-baryonic. When we talk about baryons in our field, are mainly nucleons, neutrons, and protons, which make the mass of our atoms, or makes the vast majority of the mass in our atoms. It has to be collisionless, and it has to be cold, that is non-relativistic. None of the standard model particles, so the standard particles that we know, can make this dark matter. So we look for something that goes beyond our standard model. There are many theories. There's a plethora of particles that have been predicted by our colleagues, our theory colleagues, that span over this large parameter space of interaction probability, interaction cross-section versus mass of the dark matter particle. What the community has focused so far is this small green region, which is called the WIMP, which is weakly interacting massive particles, and more recently the community is moving towards lighter dark matter particles, so in the region between the kilo electron volts to those over c squared mass. So just to give you an idea why we have believed so far that the WIMP paradigm is the right one, is that if you look at the universe as it so if you look at the evolution of particles in the universe, so let's say the number density as a function of the temperature of the universe. So temperature is of course means energy, and so when the universe in the early universe the energy was very high, so particles would annihilate with each other and be in thermal equilibrium. So dark matter particles would annihilate into standard model particles, and standard model particles would annihilate into dark matter particles. At some point, when the temperature was below the rest mass energy of the dark matter, then the standard model particles wouldn't have enough energy to generate dark energy, dark matter particles. But so in this so a suppression of the dark matter production, particle production, until a time that is still valid today, when the standard model particles also don't have enough, cannot meet because the universe is expanding, so that the standard model particles wouldn't interact so easily with each other because they are kind of far away, and so we are left with a number density, so a density of these particles up to today, and this, if we plug in what we observe from, for example, cosmic microwave background as the density of these dark matter particles, then we end up in with a, let's say, a cross section, okay, that is in the same order of the weak scale, and magically, and this is what is what is called a WIMP miracle. Magically, also from supersymmetry, we also have a prediction of a standard model, of a non-standard model particle that is called the neutralino, that has a very similar properties. So somehow there are something. So we don't believe that was just a coincidence that these two things come together, somehow predicting the same type of particle. And so far we have been looking for WIMPs. However, now the WIMP is kind of escaping our detection, and we are really getting into a region where the WIMP paradigm is not so well motivated. So we are going towards lighter dark matter particles, and this lighter, so it is, can ask ourselves, is there some kind of new force? But what is the connection between the, let's say, dark matter and the new force? Well, the answer is that dark matter is neutral would be neutral under the standard model forces, but it's charged under a new so-called hidden force, which is hidden in the sense that we don't see it, and because of some paradigm. So now the question is, can we see it experimentally? Well, of course, it's a good question. We don't know exactly, but based on good symmetry arguments and also on cosmological motivations, given the dark matter abundance, we think that there might be some so-called portal interaction between the hidden sector dark matter and the standard model particles, and so we look for dark matter detection. How do we look for dark matter detection? We are immersed in a halo, as we said before, and these are also the dark matter. These are stellar angular circular velocity of stars within our galaxy. So we see that there is a shift between what we expect from luminous matter and what we observe, and so we know that there is a dark matter halo also in our galaxy. In this dark matter halo, the dark matter particles have a certain Maxwellian distribution. Also, the sun is moving around the sun with a certain velocity, and the Earth is moving around the sun. Sorry, the sun is moving around the center of the galaxy, and the Earth is moving around the sun. And so, by looking at this mutual exploiting this mutual movement, we expect that dark matter particles have some speed coming against our detector, so that we can see their scattering on our detector materials. And also the fact that the Earth is moving around the sun gives us also a so-called annual flux modulation, which is a 3% effect, but there is also another effect that is a diurnal modulation in direction that is a larger effect of about 30%. And in this sense, well, I don't know if we have time to discuss this, but the Dirac material would be a very good material for looking for this directional preference. So the current status is this what is shown here. We have the cross section of the WIMP particle as a function of the mass of the WIMP, but we are, as I said, we are going with towards lower threshold towards lower mass WIMPs, and so if you look at the kinematic of the process, so you see that the kinetic energy of a particle is if the particle has GeV or above GeV scale, then the kinetic energy is in the order of keV. But if the lower we go with the mass, the lower the energy is going to be, the kinetic energy is going to be, and also the lower the momentum transfer. So at some point, the current WIMP paradigm predicts interaction of WIMPs with the nuclei, but once we go to lower masses, the particle to which the dark matter will interact are the electrons, and so we have to take into account all the electronic structure of our system, of our detector, and we need sub-electron volt thresholds. So far we have been looking at this range of mass, but we are going towards this mass range, so between keV and GeV over square mass, and here you see the type of energy that we are looking for. And so, well, this meme is an interesting way of the mood within a particle physics field, so in which any material could be a good candidate for dark matter detection. So this is just to tell you that there have been already, because it's a challenge to go to such low energy, to see such low energy deposits, but there have been already reported the detection of single electrons escaping or passing from band to band in some solid state detectors. So we believe that this is a possibility, and so we proposed the Dirac materials for dark matter detection, and here you see that this is the recoil spectrum. So here you see that the recoil spectrum as a function of the Fermi velocity. Of course, the interaction of dark matter would be kinematically forbidden if the velocity of the dark matter particle is lower than the Fermi velocity. So you see, and this is something that is also expressed here in this spectrum. This is somehow the spectrum, the interaction, the spectrum that you would see in your detector as a function of the Fermi velocity, of course, considering some fixed detector. And so you see that the main, the most important, or one of the most important parameters here in this search is what is written here as delta, is the band gap. So with the band gap, with the lower the band gap, the higher, let's say, the sensitivity. Here is reported the cross section as a function of the mass. And you see that already TDLS, I think, has a 10 milli-electron volt threshold, and this one has 25, I guess. So you see that with the lowering the threshold, you increase your sensitivity, both to lower masses, but also to lower cross sections. And so, well, I don't know if I need to go so much into the details of the interaction of dark matter, but we have two types of interaction. Can be direct scattering, but can also be a so-called kinematic mixing, in which the dark matter particle is absorbed within your material, it produces a photon, and this photon then makes an electron in the valence band to jump into the conduction band. And this is the reason why also the optical properties of the materials are important. And you can see that in this plot, the interaction cross section as a function of the WIMP of the dark matter mass is reported compared to conductor, for example, and also to semiconductors. And so you see that the Dirac material is very good potentials. So what we want, since we want to detect small energy deposits, we want, if possible, to have some directional sensitivity. If possible, our materials have some magnetic properties in these fractions, but it's not good applications that we're discussing right now. So the boundary condition for a material that is suitable for our detector is it has to be affordable, in the sense that it has to realize, to grow. It has to have chemical properties, good chemical properties. Also, well, we need to look at the readout, how the way to read out the single or few electrons that are excited to the from the valence to the conduction band. So what we have done is this kind of exercise. So we have put together somehow the expertise from different fields, from dark matter and also solid state theories that have a big to have a big database of Dirac materials, especially. We have looked at the organic Dirac materials, but of course this is extended because to this. So we have put together dark matter or particle physics, material science, and also data science, because what we have a big set. Have a big set of materials. Back then, when we did this publication, was 7,000 stored in the database. Yesterday I checked, and now they are at 40,000 materials. So what we do is an advanced data mining by querying the database for specific requirements. The requirements are that we first look at the band gap, and the band gap has to be as low as possible, as we said. So we narrowed this gap, and we identified 220 materials. Then we require that this material is magnetic. So we didn't want to have magnetic moments, and so we came out with somehow the selection restricted to these materials, and then we that have a band gap in the order of 40 milli-electron volts, and so we have also investigated the band structure of this material that has also another advantage, that when you turn on the spin orbit coupling, this material, I mean, a small gap opens around the Dirac cone, and this is extremely good for us because we don't want this spontaneous transition of electrons from valence to conduction band. So the existence of a band is of importance for us. So don't know if I took. I guess I took most of the time here, but I hope I gave you an idea of what our needs are and what our idea is to exploit the Dirac materials. I was saying that Dirac material is also directional sensitivity. Antonio has explained before that the Dirac cone in some materials is also tilted. This tilting of the Dirac cone would be a perfect property to exploit if we want to, for example, look for directional interaction of dark matter. So knowing the direction of the cone, so we would make like a day-night modulation analysis and see which is the most there is any signature for this day-night modulation, and this would be a clear signature of existing darkness. So, of course, we could use machine learning also to train our machine with the database, and then we can probably ask the machine to come up with some possible materials that maybe are synthesized yet, but this is a heuristic approach, but it's something that. So I think I don't need to. Thank you for listening.
Thank you, Alfredo, for your presentation that put us in a very, let's say, for us, I think for most of the people, exotic area. But at the very end, it's important that just real material is necessary to detect and to get the final confirmation of dark material. Well, so the argument is really exciting, and maybe that it raises the curiosity of some people in the audience. And so I raise questions or comments or curiosities. I have just, let's say, comments, a curiosity.
Carlo, you can do it.
Okay.
We would like to provide a question.
Yes.
Please.
Do you hear me? Okay.
Introduce yourself, Carlo. Okay, Carlo Rizza.
Okay, Carlo. Yes. From University of L'Aquila. Okay. Now, Mike, I understand. Thank you. First of all, thank you for your nice talk, Alfredo. I understand that you focus on organic material. It's right?
Yes.
Why do you choose these materials?
There is no.
They are better than. Okay.
No, I don't think there is a specific reason why we. It's just that our colleague at Nordita, they maintain this organic material database that are all Dirac materials. So they maintain this database. So we only use their database to test, let's say, our method or our approach, which doesn't mean that it has to be only organic material. We only identified 2 or 3 materials that are interesting for our applications, but from the organic materials, of course, there are also many other Dirac materials that we know they are not organic, and they still may have exactly the right properties. So there was no specific reason rather than the fact that we already had this. And
okay. Thank you for your reply.
Okay. Is there any other question or curiosity?
No, that's good.
Not, we can just say stop the first morning session. I would like to thank the distinguished guest that opened the meeting, the institutional guest, and then the technical scientists that provide interesting lectures about different aspects which arise a strong importance of cooperation between Italy and Taiwanese institutions. It's time now for the virtual coffee break. We have a little bit in delay, but I guess that 10 minutes break is necessary. And so I convene all the people here in 10 minutes, more or less. That is 11:30 time in Italy, and the corresponding time in Taiwan, that is 18:30 p.m., or probably, if I'm right. And so let's thank all the speakers of this morning session. Thank you so much.
Maurizio, thank you very much for.
It's been a pleasure. Very interesting talks. Very interesting, just to enter in a world that is not very familiar for Italian scientists, that of Taiwanese universities. I think there is a lot of points that can be developed, a lot of common interest, and let's say I would like just to talk with you in a separate time about CNR and how CNR can better improve the relationships with Taiwan. That would be important as well. So let's go to take this virtual coffee, not virtual coffee, and we'll convene here in 10 minutes, more or less. Carlo Rizza will be the next chairperson of the session.
Yes.
Thank you, Carlo.
Thank you very much, Maurizio. It is a very big pleasure for us.
No, it's a pleasure for me. I will phone you later. Ciao, Antonio.
Ciao.
Ciao.
Good morning, everybody, and good evening for Taiwan. And I am Carlo Rizza. I am the chair of this second part of workshop. The first speaker of this second part is Professor Yu-Lun from National Tsinghua University, Department of Material Science and Engineering. In his lab, the research is focused on new materials technologies for nanoelectronics and energy-aversing applications. He received several awards and is editor-in-chief for nanoscale research letters. He published more than 360 papers. Today, the title of his presentation is 2D layered materials toward phase engineered hybrid films for innovative nanoelectronics. I leave the floor to the speaker, Professor Yu-Lun.
Good afternoon from all the professors from Taiwan side. Good morning from all the professors from the Italy side. It's very honored to be here to introduce my research activities. My name is Yu-Lun. I'm from a Department of Material Science and Engineering, National Tsinghua University. Let me see. Okay, so before my talk, I would like to quickly to go through about where is the Tsinghua University. Since you are in Italy, so I would like to introduce the position of our university. We are located in northwest of the Taiwan. Here is Taipei, and in our departments, we have the 5 buildings. We are the first material science and engineering in Taiwan. We established 1972, and then our research normally is in this building, material science and technical buildings, about 45 years old. Now this is Delta building for all the faculties. We have the 2 laboratories. One is for the so-called material science laboratories for all the facility inside, and also we have a low laboratory for all the metallic processing. We also have new laboratories in the rear side of our campus. And in terms of our research field, we have the accessory research field. So from the biomaterials for all the materials, you can see this is a typical material science and engineering research work. And in terms of the students and alumni, the number of students in our department around about 800 to 900. 50% belongs to undergraduate student. 50% belong to PhD and master students. So students graduate from our department around about 6,000, more than 6,500 students. And in terms of academia performance, we are ranking 47 in terms of the material science. Okay, so I would like to go to my research activities because I spent a couple of years on growth of the 2D materials. So because several speakers, including Taiwan side and the Italian side, talking about the 2D material here, just mention about the advantage of the 2D material because very high electrical conductivity and also controllable mobility depends on what kind of material you select from your side. Another important part here is 2D material can have very high service to volume ratio and also very high flexibility. If you look at these slides, you can know about the 2D and the graphene can have very high strengths, limitations without any deformation. This is why a lot of research activities utilize those 2D for all the applications, including photo detector, solar cell, a gas sensor, and a CO2 reduction and hydrogen reactions. So before I introduce my research work, I will just quickly go through about why the 2D is so amazing because it's a kind of the polymorphic materials. It means that as long as we control the staking sequence, we can control the physical property from the mechanical transfer behavior to semiconductor behavior. For them, hexagonal anomalous semiconductor, tetrahedral symmetry anomalous mechanical behavior. So the way to synthesize 2D basically can be categorized two directions. One we call it top-down. So we use a Scotch tape to mechanically exfoliate our 2D counterpart to 2D sheet. But the problem here, we cannot control the number of layers and also the size of the those 2D is quite small. So it's why people think for the other way called chemical or electrochemical exfoliation process. What they are doing here just introduce the metal cation or hydrogen cation to become atom to do the mechanical electrochemical exfoliation process so that we can get about mass production of the 2D sheet in the solution base. But however, during the mechanical or electrochemical exfoliation, they have some damages happen. So this is why it's not good for the electrical properties applications. So the other way here we call the bottom-up method. So the typical we call the chemical vapor deposition process. So what we should do here, we just prepare the metal oxide precursor and the chalcocite precursors and then high temperatures. Two precursors become vapor, then it will be through the so-called condensation process to form a triangle shape, which is a single crystal 2D materials on the low temperature regions depends on substrate used to have different quality of the 2D materials. But however, the temperatures to gross those 2D materials quite high, normally it's more than high 500 Celsius. And also if you want to have the further electrical and functional device applications, you need about transfer processing. Let's talk about a transfer process. This is a typical way, no matter we use a graphene or 2D material, you should use a PMMA to transfer, to aging transfer how 2D to the signal substrate or any other substrate you want. But it's difficult to transfer those 2D material on the nanostructural surface because if the surface have very high surface to volume ratios, the coverage somehow is not good enough. So the goal in our lab is try to grow the 2D without any transfer and also want to form the 2D at low temperatures. So our idea is from as long as we we want to have the precise layer controllability. If we can also have the controller phase, for example, metal oxide and the metal dichroconide, that will be much better to have the more functional device applications. So we start to deposit metal oxide and followed by the so-called poster annealing process. For example, if you use a selenium, we call poster selection process. If you sulfur, we call poster sulfation process. If you use a telluride, we call telluriation process. We can form a metal telluride, metal ditelluride, metal disulfide, or metal dicyanide layer structures. So we start based on this idea to demonstrate the idea so-called laser radiation assisted selection process. What we are doing here, we use selenium powders in the glass tube and then put the deposit tungsten oxide on the silicon oxide thin substrate in the near side of the tube and nearly at about 250 to vaporize. Our powder becomes a vapor. Vapor will be pushed to the other side. As long as we need a metal oxide, such as the tungsten oxide, we can form the tungsten dicyanide directly. This is the first time to demonstrate the formation of the tungsten dicyanide at low temperature. And although the device somehow is not good, mobility is always below 1. So furthermore, we just demonstrate the other way. Can we form the tungsten other sulfur base? The answer will be yes. So we also use thinking the other way. For example, use a solution base by sleep cold. Some sulfur atom in some solvents, we're still able to combine metal oxide, such as tungsten oxide and monoxide, reacting with sulfur atom to become tungsten disulfide, ammonium disulfide. This is a result from our side. As you can see, we can successfully demonstrate the formation of tungsten disulfide, ammonium disulfide by so-called laser annealing processing. So basically, this is transfer-free. So, and also this is a fast acceleration process. You just in about 10 to 15 minutes, you form about the thing you want. And the other thing, we also think about can we control the stability. So as we know about, basically, if you just nearly at very rapid temperatures, we can make sure the formation of the 2D material will be the staking consequence will be changed from the horizontal to vertical staking. So idea here, we just use so-called micro resistance selection process. What we are doing here, we just use a silicon oxide deposit the tungsten oxide on silicon oxide substrate. Then nearby the arsenic vapors, then we use silicon carbide as a solvers to then use micro to dry to heat arsenic powder and also substrate directly. We can form about tungsten dicyanide directly. So as long as we control the tungsten oxide with more than about 20 nanometer, we find out the staking sequence of tungsten dicyanide normally vertical staking. If you reduce the thickness of tungsten oxide below about 20 nanometer after microwave treatment, the staking sequence normally parallel horizontal staking. So the different staking somehow can create different functional application. For example, we can use this for the gas sensor application. This is the red dot will be the horizontal staking. The vertical the square symbol represent the vertical staking of the tungsten dicyanide for the gas sensor applications. So, but even we use a laser and also the microwave treatments, we can have a larger scale. So we are thinking about the other way to have the mass production and precise layer controllability. So we just develop the other way called the plasma assisted chemical vapor reaction, so-called PSVR. So the idea will be based on the laser annealing and microwave treatment. So we start from the deposition of the metal oxide first. So then we just use this is a homemade facility in our laboratory. So we have the cylinder tank behind the main chamber. So as soon as you heat the cylinder tank, you can make a cylinder powder become cylinder vapor, then carried by the channel to the main channel. At the same time, you use the ICD coil to analyze your cylinder atom becomes cylinder radical, so that you can form about the 2D material at very low temperatures. For example, without plasma treatment, the lowest temperature to form a tungsten dicyanide is about 500 Celsius, confirmed by the Raman spectrum. If you look at the A1G peak, if you apply the plasma assistant process, the lowest temperature for the formation of the tungsten dicyanide alone can be down to about 250 Celsius. If you look at the microstructures, although the grain size is still very small, as long as you increase the formation temperature from 250 to 500 Celsius, you can achieve about tungsten dicyanide with large grain size, normally about 50 to 100 nanometers. So they have a lot of research in my group regarding fundamental material science, electrical functional devices, energy harvesting storage applications have been published in our group already. So if you're interested, you can go through this from our website. And also, we also find the lower temperature compared with conventional CVD process. So, for example, for tungsten dicyanide, for ammonium dicyanide, tin dicyanide, platinum dicyanide, tungsten disulfide, around about 5 to 700 Celsius. By utilizing our PCVR, we can reduce temperatures at least around about 3 to 400 Celsius. And this is a demonstration of how we utilize PSCVR to grow the tungsten dicyanide. As you can see, if you deposit tungsten oxide about 5 to 7 nanometers at the desalination process, we can achieve about tungsten dicyanide about 6 to 8 layers by reduce the thickness of the tungsten oxide into about 2 nanometers. At the desalination process, we can achieve about more layer of triple layers tungsten dicyanide. This is called the layer controllabilities. And this layer controllability had a lot of optical property applications. At the same time, as long as we patent tungsten oxide, at the desalinations, we still can patent tungsten dicyanide. So, and then we also try our best to measure the mobility. Unfortunately, the mobility is still not good at all. At 250 and even for the 500 Celsius, always below about 1. So we still try our best to optimize conditions to make sure this process can be suitable for electronic applications. Okay, and another part here, this is a scalable process. As long as we enlarge the size of our chamber, we can demonstrate the 4-inch wafer growth. So, and we also can utilize this process to fabricate a 2D material, for example, tungsten dicyanide on the low flexible substrate. This is a demonstration of a growth of tungsten dicyanide on the PI substrate, because temperatures normally should be below about 300 Celsius. And now we extend the size of our growth chamber to about 30 to 40 centimeters square, because we want seeking for industrial application based on our technique. The idea we can have such low formation temperature because the selenium, because we just make the selenium vapor become selenium radical. For the selenium vapor is a trigonal phase, and it will be a larger cluster. After we just create the bondings, so we call it crack selenium. So the size of this selenium cluster is quite small, so we can have much higher chemical reactivity. This is why we can form the metal dicyanide low temperature. And one very important feature from our facility, as long as we control the different ambient gas, for example, hydrogen and nitrogen with different ratio, we can also control the conversion rate between metal oxide, metal cyanide, and metal oxide, for example, tungsten dicyanide, tungsten oxide. So if you just have the high concentration of hydrogen and a too low concentration of hydrogen, the ratio, the conversion ratio between tungsten dicyanide and tungsten oxide will be changed. And the result also can be confirmed by our TM result. For example, if you had the pure hydrogens at the same conditions, almost 90% tungsten oxide can be converted into tungsten dicyanide. If you just reduce the hydrogens to the nitrogen about 1:1, about 50%. So at the same conditions, we can have the mixing between tungsten oxide and the tungsten dicyanide. If you further to increase the concentration of nitrogens, it's difficult to convert tungsten oxide to the tungsten dicyanide. So why we want to do this? Because we can create a heterojunction. Such a solution somehow can enhance the sensitivity for the gas sensor. This is for example, if you do the 70% tungsten oxide and 30% tungsten dicyanide, we can have the much better chemical, can be act as a chemical resistor for gases application. For example, NUX is one of our example for this case. So for example, we can have about poly 3 ppb, sorry, to be 3 ppb, to be 30 ppbs with an upper ratio of more than 10. This is the smallest chemical sensor in the world so far, due to the formation of a heterojunction between tungsten oxide and tungsten dicyanide. At the same time, we also working on a Grayson co-development system, because we want to create a 3-dimensional structure, because after this, we can do the PSCVR to create a 2D surface on 3-dimensional structure. So this is a so-called Grayson co-development system. What we are doing here, we just control the rotation angle of the substrate and also control the incident vapor flux. We can grow different hierarchical structure. This is so-called shear shutting effect. Okay, so because it's a timing atom somehow will be the mask to block the following formation of our following division of the fin, so that we can create different hierarchical structures. For example, we can have the so-called VBA structure, near rod structure, near rod with a tilting structure. In our lab, we have successfully to demonstrate the growth of the nano helix, nano screw, and the nano rod on different metal oxide systems. And for this part, we further to demonstrate the tungsten diacetyl 2D, 3D nanostructures. What we are doing here is a grazing cultivation system to deposit tungsten oxide nanoscrew, and followed by the plasma selection process to form a tungsten diacetyl tungsten oxide. So this is a typical excellent result from my slides. So, and this is a very so-called industrial application, because we can scale up the overall size to about 4-inch wafers. So we also figure out very interesting phenomenon that by control the different plasma power and also temperature, we can control the phase. We figure out the 1P phase will be dominant at low temperatures and high power, while the 2H phase somehow will be dominant at the higher formation temperatures and lower plasma power. So we also convert by SPS and also the TM result, as you can see from my slide here. And such, the 1P and 2H phase somehow can create the other interesting shocking very high to enhance the gas sensor application. So this is why we optimize the formation temperatures. We figure out at the 150 watt plasma powers, then the gross temperature about 450, we can have the maximum performance utilize this material as a NOx gas sensor. So we also further to calculate the ratio between the 1T to 2H phase with the optimal condition, which is about 46 by SPS result. So the idea here, we can have such better performance due to the formation should be very high between the 1T and the 2H phase due to the difference on the fermentable and work function between the two phases. And we also further to optimize the height of our hierarchical structures. We figure out if you increase about 60 nanometers, we have the best performance. This is why we can have the best performance of our material for the sensing, especially NOx, about 50 ppb, which is the lowest record in the world so far. And furthermore, we also work on the energy storage applications, and the other will be energy harvesting applications, such as hydrogen fusion reaction applications. So people think about what formation 1T will be the way to enhance the hydrogen fusion reaction. So we want to combine the other two ideas. One, we can have the more active sites, and we also have the so-called electronics conductivity engineering. And then this is why we want to create so-called 2D, 3D feature structures to enhance our water splitting applications. So idea here, we use a great single division to deposit molybdenum first, so we can grow nanostructures, followed by the plasma system selection process to form the molybdenum core and the molybdenum diacetyl as a shared nanostructures. This is a typical picture show my slide here. And if you look at the TM result, you can see that at the 400 Celsius, we can form about the molybdenum diacetyl as a shear layer, where the molybdenum as a core inside these nanostructures. And the overall result can be scaled up to about entire 4-inch wafer. If you detect about from 0.9 to 0.1 to 0.9, they have the same behaviors. Low result be confirmed by the Raman spectroscope. And we further to confirm that whether we can have the 1T or 2T phase. The answer will be yes. If you do the annealing temperatures from the low temperature to high temperatures, we figure out 1T phase that still be dominant at low temperatures as long as increase temperature to high temperatures, say about 550 Celsius, the 2H phase dominate. So this is why we just optimize the condition. We figure out the 400 Celsius will have the best result, so that we can have the toughest load about 34.7 millivolts per decade, and it's very stable. As long as we do the 1,000 cycle, the performance doesn't change too much. So such excellent hydrogen resolution reactions due to the very high density of active site and all with a 1T phase in our molybdenum dicyanide. And on the other hand, molybdenum coal also play important role as a channel material. The channel material, so that electron can be transferred through molybdenum to the surface of the molybdenum dicyanide to have the much better hydrogen resolution reactions result. If you want to go through the detail, please go through the paper we published 5 years ago. Then we also, last year, we also used a similar structure for the batteries. So we figured out this is also good for the battery because people think about 2D metal also very good as a catalyst or material for the battery. So what we're doing here, we just use a 2H phase. We just do the PACVR at high temperature to form about molybdenum dicyanide and molybdenum coal structure. But at this moment, we want to make sure this molybdenum dicyanide will be 2H phase. So result be confirmed by the our SPS is indeed a 2H phase at high temperature. So then, and based on this, we can have a very high capacity performance of battery. The capacity can be around about 380 mAh per gram at the charge rate about 1 milliamp per gram. If you just increase the charge rate about 5 milliamp per gram, we still can have the 1 milliamp hour per gram, and also current efficiency still can maintain about 100. And furthermore, we also demonstrate a flexible and structurable behaviors because our nanostructure can bear with some tolerance. So this is why we want to demonstrate flexibility of our 2D material for the aluminum-ion batteries. And I want to take a small time, short time to introduce about the other research activities on growth of high quality 2D material. We call it chemical vapor deposition system. In our lab, we can specify to grow different kinds of 2D material, such as molybdenum disulfide, tungsten disulfide, molybdenum dicyanide, tungsten dicyanide, and so the best result so far for the molybdenum dicyanides, we can have the mobility around about 20 to 15 centimeters square per second, and we can the maximum size we can about 1 centimeter square. So we also develop the other way called a position controllable transfer, so we can precisely transfer 2D with different twist angle. So we want to looking for the very interesting physical property on those twist 2D materials. So this year we also developed the other way called a wave transfer process, so that we can have a wrinkle-free transfer process to transfer our molybdenum disulfide to the silicon oxide substrate without any formation of wrinkle. So mobility can up to about 13 centimeters per second, and the result will be published in advanced functional materials. And here I just want to say, because this new material is very important, so that based on the PACVR and the CVD, we can combine two ideas together to have the so-called Jones structure, because this is a non-symmetry behavior on the molybdenum disulfide on the molybdenum dicyanide. For example, we are successful to demonstrate the growth of the molybdenum disulfide cyanide by modifying the plasma power and the saturation temperatures. We can replace the single layer molybdenum disulfide into the molybdenum disulfide cyanide. This is called Jones structure. At the same time, we also combined the GLD and the PACVR to have other very interesting materials. For example, semiconductor 2D, metal 2D, superconductor 2D, ferroelectric 2D, and alloy 2D, and hyper and nanowires. Okay, so thank you very much. I wish through my very quick introductions, you can understand what I have done before. If you want to more detail, please scan the QR code to know about what my research is. And I wish through this introduction, I can find a collaborator to have a proposal together from this bilateral conference. Thank you very much. So anyway, so I want to, this is final slides. Welcome to Taiwan. This is a lot of fascinating place. If you come to town, I'm very happy to bring you to those places and have fun together. Thank you.
Okay. Thank you. We thank the speaker, Professor Chih-Wei. It's now the time for a couple of questions. from audience. You can raise your hand, or if you want, you can write on the chat. Please.
I'm apologize. The reasons background has some noise because I attended a conference. As I mentioned to Professor Lee already, because they have the same conference holder in Taiwan. This is why I attend conference on the same time. I attend this bilateral workshop. Okay. If you want to know more detail my research, I'll be happy to have the other website meeting together. Okay.
Okay. Any questions from audience?
Alessandro.
Yes, I have one.
Alessandro.
Time. I'm just curious to know actually what is the difference from the two different methodology for the growth of materials. So on one side is the plasma assisted growth, and on the other side is the CVD, is the chemical vapor deposition.
Yes.
So what is actually the main pro and cons of the two approaches? What you can find best in one that's it's missing in the other, and vice versa.
Yes, thank you. So reasons I want to explore two kind of directions here, because normally for high temperature ones, you can grow high quantity 2D, but they cannot have a scale up to about wafer scale. But the PACV are here. We want because for the back end process, we need about fabrication temperature less than 400 to 500 Celsius. So the typical CVD process now it should be impossible if you want to have a direct growth. This is why I want to try to think about the other way. Can we grow the 2D at very low temperature, saying about below about 400 to 500 Celsius? So plasma assistant process can help can help us to grow such 2D at very low temperature. So we can grow 2D on a wafer scale device directly. At the same time, we are seeking for, because those 2D somehow have some defects. Those defects not good for transistor, not good for electronics, but good for the functional device such as the fault detector, gas sensor. We still have a chance to find those things for following device applications such as more and more. Okay. So the other feature here, just say we can grow different hierarchical structures based on our new so-called gray-single defense system. So we can grow different metal oxide following by the plasma selection process to form a 2D surface on 3D structures for the different device applications. Okay.
Okay.
I'm very apologize because there's something wrong with my headset. This is why I cannot use this at all. So this some noise behind me because I'm in some hotel. We just finished
okay.
the conference. Yeah.
Don't worry. Okay. Okay. Any questions from audience? No. Okay. It's now the time for the second speaker.
Thank you very much. Appreciate it.
Thank you again very much for your very intriguing talk, Professor Chih-Wei. Thank you. Okay, now it's the moment for the second speaker. The second speaker is Dr. Alessandro Molle. He is a researcher of CNR. Sorry, one moment. Okay, from Institute for Microelectronics and Microsystem, a graduate unit, and to take his talk is two-dimensional scenes and related material by epitaxy. I leave the floor to the speaker. Alessandro?
The microphone.
The microphone, please.
Okay. I'm sorry because can you hear me right now?
Yes, I can.
Okay, because when I shared the sharing, stopped the microphone on.
Okay.
Okay, I'm gonna try to be stick to the time scheduling, and just to briefly comment, briefly, talk about the two-dimensional X-scene related materials by epoxy. This is the kind of materials that we develop in our unit, and it's only a part actually of the two-dimensional materials growth and production involving all these collaborators. In particular, me mention Christian Martella, who will be the speaker on tomorrow's session about the TMD's production and and scale engineering. But for what regards the introduction of the two-dimensional X-scenes, let me make some historical overview starting from graphene and from the other 2D materials related, in the sense that graphene is a semi-metal, so that it's open to be complemented by other materials that are metallic in character, semiconducting in character. This is the case of the HBN, it is insulating. And TNDs, as recently exposed, are a perfect candidate for semiconductors. Actually, they are not actually semiconductors only because they encompass a lot of phase inside, and they displays also topological topological features, but also other non-trivial quantum states such as the charge density waves and so on. But in all this overview, so today I would like to focus on the X-scenes because they are basically the natural followers for graphene, because they are monoelemental in character, even if they are not structurally similar to graphene, in the sense that the graphene is a perfectly planar, it's an hexagonal lattice that is flat, but the X-scenes are not so flat actually. They conserve actually the hexagonal character, but they are buckled in the sense that they should be vertically displaced in order to keep all the items together. Okay, let me say that the first generation of X-scene, started from the group 4, the same group of carbon in graphene, but included the silicon, germanium, up to lead, very recently. And nowadays, actually, the family has flourished and enlarged so much, just in comprising the boron group with the paraffin, with the galanine, but also the pentagen. And for the pentagens, there is a particular interest because I know that in this symposium, this workshop, so there will be actually some attention paid to the phosphorin, to the black phosphorus. Black phosphorus is not the only allotropic form actually to be present in the 2D materials framework, but of course it was actually so much interesting for a lot of applications in mind. But on the same group of phosphorin, there is also arsenine, antimonine, and bismuthine. And recently also there was an interest increasing on the chalcogens, on the two-dimensional chalcogens, including selenine and tellurine. Okay. I'm going to try actually to talk about the X-scene evolution, just in order to give you a roadmap of how we started and where we are directed to, which are our horizons, starting from the single layer and going down to the multi-layer, and to the possibility to put to mix, to pile up X-scene layers together in a heater structure, and also talking about actually stand stabilization issues, because one of the main issues of these materials is that they are not stable under environmental conditions, so they should be stabilized, encapsulated, and so on, just in order to further up practical application. Okay, let me say something about actually the epoxy. Okay, epoxy is not the only methodology to produce X-scenes, but it's a more popular one, it's the more used one. And nowadays, actually, there are some chemists, claiming for the topotactical exfoliation of X-scenes, so a chemical methodology that is very, very interesting. But let me say that with the epoxy, we are able to control the atomistic structure, the atomistic details. Especially, my focus will be on the deposition, so that is the easier way actually to think about epoxy, because we are talking about the deposition of materials on the substrates. But this is not the only one actually, because people around the world actually was talking about the segregation from the substrates just in order to create an X-scene on top of a buffer layer. But also the intercalation approach is pretty much interesting, just in order to produce a so-called zintal phase, where the X-scene, especially silicon, silicon, and germanium, are intercalated in a zintal compound. Okay, my focus will be on the deposition. So I'm a grower in a sense, and so I will be talking about actually how to deposit some scenes in a portfolio on a different substrates. Let me say that one of the big advantage of the epitaxy is to have a large scale, large area deposition. So this is a tool to be used actually for the epitaxial methodology. It's an MBE machine. And of course, another advantage is that you can make an in situ monitoring of the properties of the structure, basically the structure and the electronic properties. Here you can see actually a large scale deposition of silicon on top of a 1-1 terminated silver. So the larger area production is one of the big advantages I told you, but it is counterfaced by the fact that the MBE and generally the UHV methodologies are pretty much pretty much expensive. So the cost is a big cone of this kind of methodology. Let me say that according to the silicon, so what we have to emphasize is also the structure variability, in the sense that the silicon is polymorphic according to the different growth parameters to be used in the process. Here you can see actually different phases, and the phases means that it's a structural arrangement of the silicon layer on top of the 1-1 terminated silver that differs according to the temperature. As long as you are changing the temperature, you can find actually different periodicities. But what is important is that each periodicity is associated with a specific electronic phase, so that you can modulate the semiconducting phase from the semi-metallic phase. Another case in point that I would like to mention is the epitaxial phosphorin. This is not black phosphorus, and I tell it actually for people working on the black phosphorus matter, such as Maurizio and so on. But the epitaxial phosphorin is pretty much interesting because it's one approach to make a large-scale deposition of phosphorus at a two-dimensional level. And the methodology is pretty much similar to the X-scenes like silicon in Germany and so on, because you have to make an epitaxial deposition on a crystallographically matched substrate, such as gold with a 1-1 termination. So the epitaxial flow is made of P4 molecules that decompose on the system on the surface, just to self-organize in a two-dimensional layer. Okay, let me just pass over to the possibility to make it multi-layer. This is the case for the silicon multi-layer, and starting from the silicon monolayer on top of the 1-1 terminated silver, you can pile up layers. But there is a disadvantage in this method because it's not clear if we are able to make a layer-by-layer growth, because there are some domains growing three-dimensionally. By the way, actually, we tried actually to integrate to make this kind of growth. We were able actually to discriminate two different regimes according to the temperature. In a certain temperature that is in between 200 degrees and 230 degrees C, so we were able to identify the multi-layer silicon according to the Raman spectroscopy and to differentiate it from the diamond cubic electropic phase that is more common for the silicon bulk. Okay, let me now turn to something that is pretty much recent in our research developments, and this is the heater scratcher. So you know that Van der Waal heater scratcher is pretty much popular in the framework in the field of 2D materials, because they enable us actually to put 2D materials such as the TMDs, graphenes, and so on together, just to expand its functionality. And so the question is here: are we able to make an epitaxial building, an epitaxial production of a Higgs-in heater scratcher? This was not actually so given for granted, because the Higgs-in interacts with one another, and so it's not actually trivial to decouple the Higgs-ins from one another. But this was the case for the heater scratcher made of silicon and tin, just to have a T-SNN silicon heater scratcher. So starting from the substrate, we in situ monitor the lead pattern, just in order to have a structural monitoring of the layer grown, and we were able to deposit the stanine according to a method that was previously reported by Yuhara and co-workers in Japan. And on top of which, we were able also to find out the difference of the structure. It is pretty much compatible with the silicon deposition, with the silicon layout. So that is why actually we try actually to conceptualize thin heater structure based on this kind of background, on structural background, so on the lead measurements taken in situ. But even from the Auger spectroscopy, we were able to define that there is a layer by layer discrimination inside the growth sequences, so that it was a case actually to talk about a pile-up of chemically distinct X-ray layers. And that fashion was even possible to be reversed in the sense that we are able actually to put first the silicon and on top the stanine. Okay, this was also grounded by some theoretical ab initio calculation, but what I would like actually to focus here is that, okay, we have actually this kind of portfolio of materials, starting from the X-ine with several, flavors, the silicon, the germanine, but other people in the world are able to produce the brophine, the tellurine, and antimonine, and so on. But are this stable in air? Because if you want to apply that in in technologies, so you need actually durable materials for durable devices, for instance. And so our idea was to cap them with an encapsulation layer, such as the aluminum oxide. The aluminum oxide is pretty much popular in nanoelectronics because it's a typical, insulating gate insulator. Okay, in electronics, it's not the only one for sure, but it's somehow replacing the silicon oxide actually. And as a sequential growth step after the silicon or the X-ine deposition, so we found out that the aluminum oxide deposition at a relatively low temperature, I'm talking about the room temperature or a little bit more, so was effective in encapsulating the layer without affecting the chemistry, so that the X-ine layer was preserved and the encapsulation layer protects the layer from extraction and transfer in environmental condition. And this is pretty much demonstrated by this kind of Raman peak taken actually from the encapsulated silicon here. Also, the chemistry is pretty much demonstrated by this X-ray photoelectron spectroscopy here. Okay, what is the meaning actually to let you know something about the flavors of this kind of work and this kind of efforts to encapsulate the layer, to graph the layers, and so on. So the driving idea is to make use of these X-ines for any kind of possible application. So this is one of a possible representation about the bendable, about the synthesis of bendable membranes. But let me start actually from the first approach here, the synthesis, the delamination, because most of the time actually it's not useful to take to utilize the silver substrates, because it's not actually practical for a feasible application, for electronic application, and so on. So that we need to have a membranes. And the membranes is this sandwich where the silicon or any other X-ine is encapsulated between a silver layer that is basically playing the role of the templates and aluminum oxide on top. So we are able to manipulate this layer, and also we are able also to scratch this layer up and down and from left to the right. So in order to create wrinkles and in order to see that there are actually distortion in the vibrational modes. But I'm afraid I have no time to get into this part. So please believe me when I say that these kind of layers can be stretched in order to deform the vibrational spectrum of this layer or the material itself. Another application that I would like to mention here is that we can keep on processing the layer and then manipulating the membranes just in order to deposit them on a target substrate, on a device substrate, let me say, just in order to make a transistor, for instance, or any kind of possible device that you have in mind. And this was the case for the single layer silicon transistor, but also for the multi-layer silicon transistor, where we first evidenced the fact that the silicon behaves as a semi-metal, or at least a certain phase of the silicon, in the sense that there is a pretty much graphene-like behavior that is corresponding to a Dirac point here with the linearly dispersed bands. The case of the multi-layer silicon is a little bit different, because in this case actually the curve is not so sharp, but there is still a semi-metal behavior because there is no gap appearing in the electronic characteristics here. Okay, I'm quite at the end on my talk, and let me also mention the other possibility to make a manipulation, processing of this kind of external layers, because previously in this, in this process flow, I was talking about a dry transfer, but there is also the possibility to make a wet transfer by the chemistry, and the wet transfer is basically made of a chemical action bath where the external layers is practically, decoupled from the substrate, so just in order to have a fission of the membranes that can be, translated and transferred to any kind of other substrates by, quite usual methodologies. And this was actually the background allowing us to transfer the silicon on top of the ITO or on top of the moly disulfide, just in order to create several new fashions of a heater scratcher or hybrid heater scratcher, where the silicon can be put wherever we like to pose it for any kind of applications that we have in mind. So this is an enabling technologies to be developed more, just in order to create the more feasible configuration for technology deployment, but it's a starting step. And let me conclude by telling you something about actually the overall, picture, the overall framework that I have the pleasure to show you today, starting from the synthesis. And the synthesis is pretty much, complicated by itself, because it may include mono, multi-layer heater scratcher, but also ending up in bendable membranes. And the idea is to make a processing just to have these kind of materials ready to use for applications, and also a final products for the testing in a relevant technology. And this processing is open to the whole portfolio of vaccines, because they are basically mined by the same disadvantages, for instance, the instability and so on. But the key point is that in the Ixin family, you can find a lot of electronic flavor, in the sense that you can span from the semi-metal, characters to the semiconducting to the topological insulator. And even if you increase the thickness, so there are pretty much interesting cases in which, for instance, some kind of a heavy Ixin may present some non-trivial topological phases. Okay, let me mention actually the founding agency, especially foundations in the Milan region, but also the European Research Council for the granting of my ERC projects. Okay, let me thank you for your attention. I'm here ready to answer your questions and comments. Thank you.
Okay, thank you, Alessandro, for his very intriguing talk about this new possibility, these new materials, an alternative strategy of graphene and standard materials. It's now the time for question. If you want, you can raise your hand. Okay, maybe we have a question from Federico. Federico, please, your microphone. Microphone is okay. Federico, do you hear me?
Let's skip to the next question.
Okay. See, yes. Other question?
Anyway, I'm here actually to answer by chat also, so that so feel free actually to post questions whenever you like.
Okay. I have a question. Is it possible? I am not an expert about the fabrication techniques. I am a theoretical physics, but I have a curiosity. Is it possible to obtain a chiral structure where we have a tilt? No.
What do you mean by chiral structure? So because okay,
so when the two layers show a tilt,
okay,
an angle.
You mean a Moiré pattern? You mean twisted layer?
Yes, crystal layer. Yes, yes.
Okay, the twisted layer, a very interesting topic actually, indeed, for as an evolution of the Van Brug's hydrostructure. So making a twisted layer means that you have to put one layer first, and then you can move, you can tilt the second layer on top with a kind of tuning of so-called magic angles in order to unleash several properties that came out from the particular arrangement of the two layers coupling. Okay, in this case, for the epoxy, it's a little bit more difficult because you have to grow materials, and so it's difficult. So the driving force for the growth is the crystallographic matching, so that you can force the nature to make a tilt. This is possible actually in the Van der Waals structure because basically you make an exfoliation, and so the exfoliation can be mechanically distorted as much as you like. But in the case of the growth, it's pretty much difficult to create an arrangement of this kind. What you may have actually is some kind of a natural, coupling between two layers, so that you can grow one and another one on top. Of course, you can basically tune the growth parameters so that you may change the structure in a temperature window that allows you to have this kind of materials growth. And in that case, you can find actually that there is a moire pattern taking place. But it's not possible to tune it because they are not actually basically decoupled from the in the mechanical exfoliation processing. Okay.
I understand. Thank you. Yes, you are very clear. We try again with Federico.
Yes, can you hear me now?
Yes, I can. Okay.
Sorry. Okay. So great talk, and just a question about tailoring. I can read it there. So is it a surface that you can actually grow? Have you ever grown?
Okay, thank you for the acknowledgement. Yeah, tailoring is one of the possible materials to be grown. For the direct questions, so I can say yes completely, but we are into.
Okay, cool.
Okay. So the only point for issue that I can find on the tailoring is that I don't really know if we are able actually to bring it into the very two-dimensional layer, because it's very new actually, and so there is no report about the stability of the tailoring. But I think that the tailoring can be even easier to be grown from other materials because it can be also synthesized by CVD, so that there's a quite good expectation for it. But as I told you, I'm into.
Okay. Thanks.
Thanks again, Alessandro, for your very nice talk. And now we move to the third talk. Now we have Gianluca Fiori. He's a full professor of University of Pisa. And his research concern on nano device based on novel materials, and the title of his talk is Electronic Application Enabled by 2D Materials.
So I hope that you can see my screen and that you can hear me.
Yes, we can. Okay.
Yes. Okay. So thank you for
the floor is yours.
Thank you. Okay. So thank you for the introduction. Thank you for giving me the opportunity to present my research today. So indeed, what I'm going to do is to try to show an overview of what could be the potentials of two-dimensional materials for electronic application. Talking about two-dimensional materials for this kind of application, I mean, it's really can open really wide scenarios. Today, I'm going to focus my attention on flexible and wearable application. So the motivation and the visions of exploiting two-dimensional materials for wearable and portable application is coming from this motivation. I mean, today's the technology and all the products are rigid and not customizable, and we would like instead to have, hopefully in a near future, something that indeed is flexible, foldable, and also customizable by the user. So two-dimensional materials from this point of view can be the enabling technology because they have better performance in terms of mechanical properties as well as electrical properties as compared to what is as compared to the current technology where I mean, exploiting organic semiconductors and so on that they indeed have in principle worse performance as compared to the two-dimensional materials. And the other aspect is that it's indeed an added value is that the fact that you have a lot of plethora of material that you can pick up with different properties, semiconducting, conducting, insulating, and last but not least, that you can even think of or arranging in heterostructures. So the idea is to exploit two-dimensional material-based inks provided by Manchester University, in particular from the group of Professor Shinzakazi Hiragi, and to try to develop a kind of an electronic device toolbox when one would like to obtain the different devices and parts that are important for the electronic application. So, I mean, I'm talking about passive components like capacitors, and then nonlinear and active devices like field effect transistors. One is able to obtain this, so the target is to combine them in more complex circuits, like, just here to give some example, a CMOS amplifier or even memory. And once you have that, to move further and try to develop an integrated circuits like the one that we are trying to develop here in the WASP project, where the integrated circuits can be put on top of an appendage, for example, and then is able to detect some and to analyze some important information like temperature, the pH levels, as well as glucose level, and then to deliver this information to a simple reader that can be, for example, a cell phone. So not only this technology wouldn't open, let's say, new scenario, not only in the portable healthcare application, but also, for example, in anti-counterfeiting, as well as the other application like in the food market, in order to detect product freshness and to deliver directly information about the food that is packed in some packages. So where are we now, and what do we need? For sure, the ones that are enlisted here are the main ingredients that need to be solved, and you need to start with in order to to cook your device and circuits. First of all, you need good resolution. So what does it mean, good resolution? So if you go back in the 1970s and you look at the Intel, one of the first microprocessors, the Intel 8008, the resolution, the lateral resolution of these devices, this chip was around 10 micrometer. And this was done on top of rigid substrates, the silicon. And this is nice. The nice thing is that now we can obtain the very same lateral resolution, but on top of flexible substrates like paper. This is something that, for example, we are trying to achieve and we go beyond this resolution with a prototype that we are developing these days, that is able to go beyond the 10 micrometer lateral resolution, so to obtain these kind of structures on flexible substrates like paper, and this, for example, would represent the source and the drain. So you deposit the semiconductor on top, and you can have scaled, really micro scale devices. This, in this case, is an example of a 3 micrometer channel device. Then you need obviously good electrics, and you need to good electrics in terms of also the possibility to work at the low voltage application, because when you are talking about wearable application, would like to have low voltage in order to spare the energy of your batteries. So this is, for example, one devices that we put on top of paper that is probably this is the first fully printed graphene FETs printed on top of paper, so fully printed, where everything is printed, starting from the source and drain contacts, the channel, the electric, as well as the top contact. And we managed to demonstrate a flavor of, let's say, modulation of the current. But this is not due to the process by itself, but this is due to the fact that indeed the graphene is a semi-metal, so and not a semiconductor, so it doesn't have a band gap, so it's completely impossible to switch off the device. So rather than graphene, it's better. It will be better to use good semiconductor, real semiconductors. Obviously, the first semiconductor I choice come to mind is MOS2. The problem is that printing of MOS2 is not that trivial, as it was, I mean, clear from the very beginning. Indeed, I mean, from this work by Michael Ossi and Max Lemme, it has been shown that the current cannot be modulated, and most probably because of the large numbers of defects that are present in the network of MOS2 flake. A really nice example of a solution processed deposited MOS2 channel is this one by Professor Duan. The only problem is that the post-processing, like for example the annealing and all the chemical process that has been used, are not compatible, for example, with flexible substrates like paper, that is our target substrates. So it came to our mind to use this approach. So to start from CVD MOS2 and then transfer CVD MOS2 on top of flexible substrates like paper, and then define all the other component of the device only through inkjet printing. So the process is, I mean, it can be summarized here. This is a collaboration between us, Manchester, IIT, and Vienna. So there's a transfer of CVD MOS2 stripes on top of paper, and then all the other components, as I was saying, so the contacts, the dielectric, as well as the top contacts are defined through inkjet printing. So here is just I mean, a sum up of the process for the transfer. So the MOS2 is grown on top of sapphire, then is patterned, and then is the transfer to paper. Just put, I mean, it's a wet transfer either in water, or in the worst case in the KOH. And then the paper as well is fished on top of the paper, the target substrates, and then the polystyrene is removed. And this is a micrograph picture of the transfer device, and this instead of the picture from a microscope, optical microscope of the source and drain, the defined source and drain, the boron nitride, as well as the top contact. These devices are working great in the sense that we have really large current modulations with a limited gate voltage applied below 2 volts. So these, I mean, I would refer this to low voltage application. Indeed, good saturation of the current in the output characteristics, and the really high performance in terms of mobility with respect to ion-IOF ratio, and already comparable as compared to more mature technology like IXO or carbon nanotubes and organic semiconductors. If banded, the IV characteristics does not change at all, or I mean, or really few. That is indeed a really good point in favor of this technology. We have tried also to define, instead of silver contacts, graphene contacts, printed graphene contacts, but the problem is that we have large Schottky contacts, as shown here in the Brurzinic signature in the output characteristics of the device. Then we have played a little bit with these transistors, defining NOT port, NAND port, as well as current mirror, that work great, especially the gain is really large. Obviously, we would like to move farther and to obtain something as the same complexity as the one that we obtained in this joint collaboration with the group of Thomas Müller. This research is led by Thomas at Vienna, where indeed an operational amplifier has been fabricated and measured with a complexity of around 12 transistors, and it has been demonstrated to work great as let's say a building block for electronics, like for example trying to use this for inverter amplifier integrators and other let's say main building block for analog application. This is non-rigid. We would like then to move to flexible. One thing that I want to underline is that in the previous cases, all the technology was a resistor transistor logic, while in order to obtain really good performance, you would like to have a CMOS technology. So the missing piece is the PMOS transistors. What we have done, what we're trying to do is to integrate the technology that we have shown before with the carbon nanotube technology. So the NMOS by nature, the NMOS by nature behave like an N-type transistors, while carbon nanotubes by nature behaves like P-type. So we have integrated these two different technology together. So everything is printed again, except the NMOS2 that is transferred. And indeed, likely, we managed to obtain really good matching between the N-type and the P-type that indeed has led to large gain. Again, we have tried to integrate this technology in order to attain really simple circuits, CMOS circuits, like, I mean, the most simple indeed is the inverter, CMOS inverter. This is the NAND port that has shown really good performance. And then we have moved through more complex structure, like for example, this is a D-latch integrated the CMOS technology as well as the pass transistors. So from the functional point of view, everything works great. The only problem indeed that still have to be solved is the fact that these devices for the moment are slow. So we need to improve the speed, as I was going to mention in a couple of slides. So obtain, as you've seen, the complexity of this simple chip are around tens of transistors. But obviously, if you want to implement the device that I was showing at the very beginning, the one delivering information for healthcare application, you need to go for really complex structure. So obtaining a fully printed device probably is not at reach yet. But in order to get some results in the short time, probably the hybrid approach is the best one. For hybrid, I mean that you are integrating, let's say, mainstream rigid the technology, silicon technology, but for example, put on top of flexible PCB together with printed technology as the one that I was mentioned. So for example, here in the case of the paper substrates, where everything is printed except these two circuits here. You have the printed antenna, the connection that are printed. Here in this case, you have a graphene sensor that is printed. The IC obviously is not printed, but it's on flexible substrates. And this, for example, is a perovskite solar cell, again, glue on top, but it's flexible as well. So we have tried to develop a proof of concept device. I'm going to show you to describe briefly the functionality. So when the light is off, we have a single strain value that is sampled, and then this is read and delivered back to the cell phone that is interrogating the systems. When the light is on, instead, this works as a multiple strains value log that are sampled and saved on a memory that is placed on the chip. And then these information are delivered back when the cell phone interrogates the chip. So this is a video that is summarizing demonstrating the proof of concept. So again, so when the light is off, we are making a simple read. The simple read is seen here. So you see the runtime, the counter. This is the counter is equal to 1, and we are reading, for example, 1 value. While the light is on, instead, we have multiple reading, and we see here that indeed the counter, whenever you put interrogate the system, so you put the cell phone on top, is increasing, and then you are reading here the multiple values. Okay, so again, the last thing that we need, the last ingredients that we need is the speed, and there are lots of problems with these. I mean, not only with printable, but also with MOS2 or two-dimensional material in general. One of the main problems that indeed we need to address, and for example, we are trying to address within the flagship, is to reduce the hysteresis. That is due most of to the fact that you have lots of traps, for example, either in the oxide, but also in the two-dimensional materials that are leading to really large problems in long charging time, as well as in huge problems in the hysteresis that need compulsory to be solved in order to obtain a really functional device. So this brings me to the conclusion. I should be in time, and okay, and obviously let's acknowledge my main collaborators as well as the funding for that has allowed us to do this research. So thank you for your attention.
Thank you, Professor Fiori, for his very nice talk. It's now the time for question. If you want, you can raise your hand for questions. Okay, no question from the audience. I have only a Federico.
Yes, can you hear me now?
Yes, yes,
okay, so cool.
We can.
Okay, so wearable, so just a commercial question, would say. So you show us devices on paper. So how about texture or clothes? Have you tried to put something on clothes?
No, this indeed it's an alternative substrate to paper. We haven't done this yet, but there are groups that indeed have worked a lot on this. For example, Felice Torrisi has worked a lot on this when he was in Cambridge, and also now that is in London has done a lot of research on that. I mean, and there are lots of groups that indeed are trying to develop this, so integrate these devices on top of texture, because yeah, indeed you can integrate directly on your clothes, and this could have a huge market. Yeah, that's
okay. That's cool.
Okay, good. I have another question, a curiosity about the transistor, MOS2 based transistor. No, you consider as four electrodes.
Okay.
You consider, Antonio? Okay.
Yes.
Okay. Sorry. Okay. You can consider an ink based on graphene. Okay, I understand. Yes. That you use this a mix of graphene for electrodes. It's right. Yes.
Yeah, we have tried both indeed. We have tried.
Okay, my question is a good choice or is only a cheaper solution?
No. So for graphene, we have tried to use, graphene as a channel for the FETs, it's a bad choice in the sense that it's not going to work as a semiconductor. So you cannot switch the channel off. As a contact, it can be an option. In this particular case, printed graphene contacts are not extremely good. Because we have shown that indeed we have large the formation of a Schottky barrier at the interface that is detrimental for the transport and is leading to large contact resistance. But for example, this is for printing. In case of let's say CVD, MOS2 and CVD graphene, then indeed graphene has been demonstrated to work in the other way around. I mean, if you use graphene to contact MOS2, this is reducing the contact resistance. I believe because, I mean, morphologically, inkjet printed devices are made of networks of flakes, rather in the other case, it's just one flake. And so you are changing the interaction between the interfaces that indeed are really fundamental for even from an electrical point of view.
Okay, thank you.
Just a curiosity regarding the concentration of the functional links, concentration of the flakes of two-dimensional materials. And another question, if you are interested in exploring new van der Waals semiconductors as those presented in this workshop.
So the concentration here is around milligrams per milliliter. So and so around 1 or 2 at most in the case for some cases. I don't know that for sure. I mean there are lots of. So the nice things about two-dimensional materials indeed is that you have really a plethora of different materials with really different electronic properties. So indeed now it is just a matter of finding the right one for your application. So
yes.
Yes. So you have in mind an application, then then you have in mind some electrical requirements, and then it's a matter of finding the right material. I mean, and if indeed you can find the correct one, then you are done.
Thank you very much.
Thank you.
Thank you, Professor Fiori. And now we move to the next speaker. The next speaker is Professor Vincenzo Galdi. He's a full professor at the University of Sannio, Italy, and he's an expert in metamaterials and photonics. His research interest encompasses analytical and numerical modeling of wave propagation in metamaterials and complex environments. The title of his talk is Metamaterials, Basic Perspective and Lesson Learned. I leave the floor to the speaker.
Thank you very much, Carlo. Can you hear me? Can you see the slides?
Yes, Vincenzo.
Okay. Thanks again. And good afternoon or good evening, depending on your time zone. So, first of all, I want to thank the organizers. It's a real pleasure and honor to be here today. And I come from a different community, so my talk may be a little different from the previous one. So I'm a theorist and I work on metamaterials, mostly electromagnetic metamaterials. So the scope of this presentation, it's in the first part to give you an overview of the basic aspects and also the recent trends in this topic. And then in the second part, I would like to connect it to the some of the topics that may be more of interest in this community. So how these concepts can somehow inspire some new developments in two-dimensional materials, so in terms of planar meta-optics with polaritons, and finally some conclusions. So what is a metamaterials? This term has been mentioned also in one of the earlier talks by Professor Cao. Essentially, a metamaterial is an artificial engineered material made of deeply subwavelength inclusions, and even if these inclusions may be macroscopic, depending on the frequency you're working on, since they're small compared to wavelength, the material can be still seen as a continuum, and so can be described in terms of effective parameters. And the interesting thing is that most of these macroscopic properties are derived by the structure and are not the arrangement, essentially, are not necessarily limited by the chemistry of the constituent, which allows to lift some limitations of natural materials. So look, for instance, of behaviors, exotic behaviors like negative index materials, or attain some properties that are typically not available at the specific frequencies you're working on. Think, for instance, of optical magnetism. And it is a very exciting research field which blends fundamental science, but also has lots of technological application with a market that it's growing very steadily, and ranges from defense to consumer electronic and energy applications. And although it's an inherently multidisciplinary area, and although most of the results that I'm going to show have to do with electromagnetics and optics, this concept have also resonated in other branches of physics like acoustics and thermodynamics, for instance. So just to give you a couple of basic concepts, let's start with the negative refractive index. So during the 60s, it was shown in a seminal paper by Victor Veselago that although there was no instance in nature of materials which could exhibit, simultaneously negative permittivity and permeability, there was no basic physics law that prohibited it. And he speculated that if you allow this behavior, then something very strange may happen. So basically most of the physics laws like Snell, Cherenkov, or Doppler get sort of flipped. And then in 2000, John Pendry showed that this behavior could actually lead to what they call a perfect length, so something that could, in principle, beat the diffraction limit, at least in theory, if you don't consider dissipation. Also, from the practical viewpoint, this negative refractive index has implications in terms of reducing the size of components like waveguides or resonators. You can make it small compared to the wavelength. So this is very interesting in fields like microwave or antennas. And again, material like that was thought impossible to exist in nature. I'll come back a little later on that. And so, in principle, it can be engineered at different frequencies. Another interesting possibility is the hyperbolic dispersion. So, a material with an anisotropic material with opposite sign components. This allows dispersion surfaces that are essentially hyperboloidal. And it enables the propagation of high wave number modes, which allow the transfer of sub-wavelength details to the far field. And there are many applications ranging from imaging to nanolithography. And again, it was thought that these materials were not available in nature, and so it was proposed to synthesize them as metallodielectric multilayers or nanowires. Another key concept in our community that was put forward again by John Pendry in 2006 is the concept of transformation optics that essentially relies on the covariance properties of Maxwell equation, and it allows in principle to shape at will the flux of energy as long as is it possible to control very finely the spatial inhomogeneity and anisotropy of a material. And there are some examples where this can be done approximately. You may have heard of the so-called cloak of invisibility. This is one of the possible applications. However, from the technological viewpoint, it is very hard to manufacture, three-dimensional volumetric metamaterials. So a big leap in terms of practical application has been obtained by, thinking of the two-dimensional equivalent of these metamaterials, the so-called metasurfaces. There was a seminal paper by Federico Capasso's group in 2011, and they showed that it was possible to generalize the Snell reflection and refraction law by imparting abrupt gradients of phase, so create essentially anomalous reflection of refraction. And if I have to look at the historical path and the trends of where this sector is going, we started around 2000 with what they call the first generation materials. They were essentially a periodic structure, and so can give band gap or other type of properties like that. And then about 10 years ago, people started modulating spatially the properties of these materials. This is very interesting applications like antennas, for instance. And now we are in what we call the third generation of metamaterials and metasurfaces. And some of the trends that are, they are actually of interest now is the possibility to control the properties, not only space, but also in time by using tunable or reconfigurable materials. Also to embed sensing and computational capabilities. Also to combine gain and loss by using non-Hermitian concept like parity time symmetry. And finally, since in most engineering application, you don't have only one physical aspect, but you want to control jointly, for instance, the electromagnetic and the thermal response, multifunctional and multiphysics responses are very interesting. I don't have time to go all through these points. I just want to show you a couple of pointers. For instance, there are applications where you can embed sensors in the surfaces so they can also learn from the environment and react to the stimuli of the environment, and so change the response on this basis. Also, for future technologies, for future communication technologies, there is a lot of interest in what are called reconfigurable intelligent surfaces that can create anomalous reflection or refraction. And in principle, you can think of exploiting multiple reflection in the environment at your advantage in order to deal with situations where you don't have line of sight. This is a very hot topic in telecommunication at this time. Also, there is a lot of interest in embedding some computational capability in the metamaterials. In 2014, in collaboration with Andrea Lue and Nader Engeta, we published this paper in Science where we proposed to use a metamaterial to create some, to perform some mathematical operations, for instance, compute derivatives like a second derivative that can be used as a Laplace filter in image processing for edge detection. That was a theoretical paper, but inspired a lot of experimental studies that show the proof of principle. So now there is a lot of interest in performing analog computing using metamaterials. So basically performing on a physical layer some operations that are typically virtualized in terms of software in communication systems, for instance. And recently, Nader Engeta's group proved at microwave frequency, a proof of principle at microwave frequency, that in principle, metamaterials can also be used to solve equations. And they did it with a material that is 3D printable, so it's pretty simple and also easy to scale at different frequencies. So now let me start with the second part of my talk, where I want to, show you how this concept could, in principle, inspire some developments in van der Waals nanomaterials. You know that we heard also in these presentations today that there is a lot of interest in these materials and in the propagation of polaritons, and there are lots of application to sensing and nanoimaging and so on. Now, natural van der Waals materials typically come in the form of monolayers, thin slab, or even a hybrid heterostructure. Some of the concepts that I mentioned before are also permeating this application. So we're seeing some artificially engineered van der Waals materials where you can mimic some typical effects of planar optics, like junction, waveguides, or cavities, or even something more complex like meta-optics. So concept like transformation optics or photonic crystal, metasurfaces, moire bilayers, or line waves that are typical of metamaterials are also being investigated in this framework. So just a quick look at these applications. Well, when you talk about van der Waals materials, you want to look at the in-plane dispersion. And depending on the type of materials, you may have like a circular dispersion that basically provides isotropic propagation of the polaritons, or elliptic, that's another typical behavior. It actually turns out that it is possible to obtain hyperbolic behavior even using natural materials. Some examples are black phosphorus, for instance. And usually when you go from a transition, a topological transition between an elliptical and an hyperbolic regime, you go through a flat band regime that provides a very highly collimated propagation regime. Now, as I said, some of the concepts of planar of refractive optics can be applied in the planar regime by putting together some heterostructure. So, for instance, you see here some examples. These are taken from a nice review paper that came out in Nature a few months ago. And so in principle, you can obtain effects like in-plane lensing or like a prism or even negative refraction by, creating a heterostructure with, graphene or HBN and so on. And in principle, some of these properties can be tunable, for instance, using phase change materials or, graphene by changing the chemical potential. And indeed, in 2011, there was this there was a seminal paper by Nader and Geta that proposed the use of transformation optics on a graphene platform. So control locally the properties of graphene to attain, typical effects that we saw in metamaterials. And some of these concepts are actually been verified also experimentally. I say again, I took this example from this recent review paper. So you see that it is possible to shape, to pattern these materials to obtain like nanocavities, also hyperbolic metasurfaces in a regime where it is not possible to find this behavior in natural materials. So you can do it with nanoribbons, for instance, or you can obtain very anisotropic behavior that leads to canalized propagation on a polariton. You can blend the concept graphene with photonic crystals to obtain effects like defect waveguides, or even apply some of the metasurface concept, like the gradient modulation, spatial modulation on this type of van der Waals materials. Another very interesting concept that was put forward by Andrea Lue's group is the moire engineering. That was inspired by the concept of twisted bilayer graphene. They show that if you put two layers of a metasurface or a natural surface, then you can exploit the interlayer effects to do dispersion engineering. Essentially, by changing this twist angle, you can have a topological transition between elliptic and hyperbolic behavior. And at the intersections, you basically get the analog of the magic angle for twisted bilayer graphene. So they call it photonic magic angle, where you have a high collimated and diffractionless canalized polarization. And interesting, they did the first theoretical study when they considered some artificial metasurfaces made of graphene with nanoribbons. But then for the experimental verification, they actually realized that they could attain those properties, the hyperbolic dispersion from natural materials, in particular molybdenum trioxide. And so they proved this concept experimentally. The last concept that I want to mention is the concept of line wave. That's essentially the one-dimensional analog of surface wave, except that they propagate in plane, so they enjoy both in-plane and out-of-plane confinement, and they can propagate at the junction between two dual metasurfaces, like one capacitive and one inductive. They have very interesting properties, and their existence has been proved experimentally at microwave frequencies, where it's fairly simple to manufacture. For a capacitive metasurface, you can use patches, and for an inductive metasurface, you can use the dual, so essentially holes. There are some theoretical studies or this concept in graphene platforms, although there is no experimental evidence. And it would be very interesting, because with graphene, in principle, it is possible to reconfigure this junction. And so switch, for instance, from like a waveguide to a coupler and so on. Also, there are lots of interesting properties in terms of field enhancement and propagation-dependent polarization, and also some sort of topological, some weak topological robustness. More recently, we showed that this concept can also be extended to non-Hermitian structure by using modulation of gain and loss instead of the reactive part. And there are interesting effects in terms of chiral coupling. In principle, you can obtain a truly one-dimensional lasing and other properties that are typical of non-Hermitian structures, like exceptional points. So I think my time is over. So I just want to draw some conclusions. I hope that you find this this overview interesting, that may inspire some new developments. I believe that cross-fertilization between metamaterial science and material science is crucial, because, on my side, we do a lot of speculative research, but then, metamaterials may give some interesting properties, but then when you go to very small scale, when homogenization breaks down, you cannot apply them. However, some presumed meta properties like negative index, hyperbolic dispersion may actually be present in nature. And actually, just last week, in the last issue of Physical Review Letters, there was this very interesting paper, actually from a group from Taiwan, that showed that another possible implementation in natural materials of the concept of negative refractive index. So you don't necessarily need a metamaterial for these, exotic responses. And so let me finish with, citing this quotation that is usually attributed to George Bernard Shaw. As physicists and engineers, we usually look at things that are, and we ask why. But in our community, in the metamaterial community, sometimes we flip this question. So we think of things that do not exist and ask why not. And sometimes you need a metamaterial, sometimes you don't need a metamaterial. So I think the interaction with the material science community, it's very crucial to distinguish, the wishful thinking from the something that can actually be done. And with that, I conclude my talk, and I thank you for your attention. I'll be glad to take any question.
Thank you for your talk. It's very interesting. Thank you for this broad overview on metamaterials and photonics. Now it's the time for a couple of questions from the audience. Okay, I'm only a curiosity. Line waves, about line waves. Okay, it's possible to obtain line wave with dissipative system, is right?
Of course, you get some damped version. I mean, here I'm assuming the form that was studied at the very beginning is where you have reactive surfaces, one capacitive and one inductive, and there is no closed form solution, contrary to the surface waves. We show that if you have a lossy surface coupled with the gain material, regardless of the capacitive or the inductive behavior, you can obtain localization both in plane and out of plane. Of course, if you have only loss, then you won't have a purely real propagation constant, so you will get attenuation. When you have loss and gain, they can somehow compensate each other, and so you can have actually a real value propagation constant.
Okay, thank you. Another question. Do you know that there are some groups observed this line wave experimentally? Is only a curiosity? With gain or loss? With gain or loss?
No, not with gain or loss. No, so far the only experimental evidence that I'm aware of is at microwave frequency using capacitive and inductive sheets.
Okay. Thank you again for your talk.
Okay, I have a question.
Sure.
Sorry, my question. Okay. Would you show me the slide with the PRO paper published by Taiwanese?
Yes.
Yeah. Okay. I want to know these people, and maybe I can contact these people and learn more about the metamaterials from you.
Yeah, this came out. I saw it like on Friday. It's the last issue of Physical Review letter. It's very recent. I actually only had a chance to give it a glance. It's I haven't read it, with great attention, but it looks very interesting.
Okay, thank you.
You're welcome.
Okay, good. Thank you much for this recent paper on Physical Review letters. We will contact these authors surely.
Yeah, for the next workshop, it will be interesting.
Okay, it's a good idea. Okay, thank you again, Vincenzo. And now we move to the last talk. It's the speaker is Yi-Chun Lee from Institute for Nanoscience, National Chih-Wei University. The title of his talk is Exploring Ultrasensitive van der Waals Materials to Develop Potential Electronics.
Thank you to the committee giving this opportunity to show what I do in the past few years. My name is Yi-Chun from National Zhongxin University in Taiwan. My title is shown here. Today I will explore the ultra-sensitive van der Waals material and try to develop their potential electronics. It's a history of my group. I built my group 8 years ago and in Taichung City. In the first 2 years, I tried to study the two-dimensional electronics, one-dimensional electronics, and organic electronics, as shown here. And the second 2 years, we keep the two-dimensional electronics and also develop 2D PN heterostructure. In the third years, I try to develop all 2D electronics, as you can see the results shown here. And then now we study focus on 2D material and other interesting low-dimensional material. Okay, it's a publication as function of year. as you can see, increase. My group always focus on study the electrical property in low-dimensional electronics. For the system, as I mentioned, I try to focus on one-dimensional electronics, organic electronics, and two-dimensional electronics. For the strategy, we use the temperature-dependent electrical property to understand the charge transport and to study the nano contact. And I also study the low-dimensional fluctuation, as well as develop the interesting nanoscale application. For the structure, in the beginning, when we take the material, we will study the transistor and then go to the floating gate electronics over memory, and then go to the artificial snaps. It's my outline. In the beginning, I will show you how we will use a 2D material for future electronics, and I will discuss the challenge in 2D electronics, and then go to my topic. My topic, I will focus on indium selenide material. And the second part, I will use the several works in my group to understand the fundamental something, and to understand the charge transistor-based application, and understand the artificial biorelated electronics. Finally, I will give you a short conclusion. As you can see, let me understand the electronics revolution 10 or 20 years ago. If you would like to finish one work, maybe you need to prepare the telephone, calculator, typewriter, camera, and so on. But now, you just lie on the sofa and move your finger on the touch panel, and like the potato, you can finish all the functions that you want. As you can see, device size reduced several orders of magnitude. 10 years ago, more than 10 years ago, the device size like this one, you can store several hundred megabyte data, and now you can store several hundred gigabyte, and then it's a very, very big size impact. If you think about the transistor were like people, several years ago, people try to prepare the electronics. They try to put the 2000 transistor onto the 12 millimeter square area. It's like a traditional Munich hole allowed the 2000 people into this Munich hole. And then in 2000, it's like put the all city member into the same area. How about now? Now actually it's more than 1.3 billion transistor into the 10 times of original area. Okay, it's like put the whole China people go into the time, go into the 10 times of original Munich hole. It's very crazy, but we call it's a scale law of it's a scale of Morse law. As you can see, the device size reduces several orders of magnitude, and the packing density increases several orders of magnitude. There is a limit, the physical limit. We will discuss this physical limit later. And if we consider the Morse law, can it be continued? If you think about this question, you need to think about the planar MOSFET structure. As you can see, here source, here is a drain. We use a vertical electric field, this gate structure shown here. We use this vertical electric field to control current on or current off. So for the typical electronics, we want the on-off ratio. We want the high on-off ratio. We want the high on current or low of current. Of course, in order to serve the power, we want a very, very small SS value. Okay, the typical transfer curve shown here is a log scale for the is a left hand side is a log scale, and the right hand side is a linear scale. As you can see, of current shown here, on current shown here, the slope indicate the SS value. So we want the on-off ratio is very big and the off current is very, very small. of course, the anchor length should be very large. But for the typical structure, we just select the right material. We can get the function that we want. But how about the short devices or small devices? Actually, for the small devices, major issue is leakage. For the transistor, actually, it's like a switching, and we can switch on and we can switch off. However, for the small channel devices, the on current is very similar to the long channel, but off current, as you can see, the off current for the short channel will increase significantly. So therefore, no leakage control is no scattering in the future. How to determine the short channel and the long channel? There is a very special lens. As you can see, source, drain, and the gate is a dielectric signature, and this one is a channel signature. And there is a special lens we call the lambda. This special lens relates to the thickness and the dielectric constant for outside layer and the channel layer. If your channel length is similar close to 5 times of lambda, we need to consider the short channel effect. Here, I try to give you a Venn diagram to understand more about this behavior. The y-axis is energy, the x-axis is distance. For the long channel, it's very easy to create a barrier, so charge is not easy to broken this barrier and go to the drain area. But for the short channel, you will meet a very, very large dipole effect. What is a dipole? Which indicates the drain-induced barrier lowering effect. So as you can see, the electron can very easily tunnel from the source to the drain and make a very, very large leakage current. Let's consider the traditional materials such as silicon, germanium, or gallium arsenide. If the channel length is only 5 nanometer, the body thickness should be smaller than 1 nanometer, as you can see, like this one. It's not very easy to realize by using the current nail technology. Therefore, scientists try to overcome this barrier. They think about three methods to overcome this barrier. Something like the more and more. So the scientists believe the size can reduce again. So they try to develop the FinFET, multi-gate devices, and so on. On the other hand, they believe they can more and more, which indicates they try to develop promising applications, something like the power-saving devices, bio devices, or optical electronics, or multifunctional devices. They can combine all the function and into the single electronics and overcome the barrier. On the other hand, they try to use another method called the beyond the CMOS method. The beyond CMOS method, scientists try to find out the new material, new structure, and the new mechanism to overcome this barrier. Therefore, using these 3 methods, the scientists believe they can extend the CMOS or extend the Moore's law. So therefore, maybe using the ultra artificially thin layer material, such as 2D material for the next generation electronics would be a very, very good opportunity. Okay, let's think about the technology node. 7 years ago, people tried to develop the bulk MOSFET, and then they try to reduce the thickness, so they develop the ultra thin body SOI, and then try to get a very nice leakage control, so they try to develop the FinFET structure. And now they try to scientists try to use a 2D material to well control the leakage. In the future, scientists try to staking those 2D material and then become the nanosheet field effect transistor. Let's consider the mobility as function of the body thickness and the substrate as a function of gate length. As you can see, it's for the silicon electron part and the silicon hole part. as you can see, the silicon mobility will reduce because on the surface there are a lot of dangling bonds. So if you reduce the size, the dangling bond effect will damage the mobility in your system. So as you can see, the silicon mobility reduces very fast. But for the 2D, as you can see, most of the 2D, they always keep the very, very high mobility. Even the body thickness is very, very small. But how about the substratial swing? As you can see, the 2D material, they can get a very big substratial swing. Even the gate length is very small. So consider the technology node. As you can see, in the past 6 years, scientists try to use the silicon, and then now maybe scientists can use a 2D material, or use a gate-around structure, or use a nail sheet field effect transistor, or spin, or quantum something. Anyway, the 2D would be a good opportunity to overcome the future technology node. Okay, so actually, let's consider the 2D material family. There are more than 1,000 2D material in the world, and the most of the part is a semiconductor behavior, the band gap between the 1 to 3 electron volt. Some of them are insulator, and then as you can see, the band gap is tunable as function of layer thickness from the mechanical, from the semiconductor, from the to insulator. And then we can select a different material and the staking together become the artificial vertical heterostructure, and then we can realize all functions that we want. So we want the 2D material become the interconnector, become the electrode, become the channel material, and the staking each other. Eventually we want our structure can realize like this one. Use a 2D as a CMOS part, use a 2D for the memory part, use a 2D for the photodetector part, use a 2D for the transmitter part, and the staking together. Okay. Let's consider the challenge for the real 2D material. Actually, there are but a lot of challenges. For the material part, how to grow a very big size, how to dope in your 2D material, how to passivate the surface is a very big problem. For the physical chemistry part, how to functionalization, how to understand the carrier dynamic, how to combine the different dimensions into the same position is also a very big problem. For the engineer part, how to develop the O2D circuit, how to make the contact interface problem, how to stake in the different material into the same position precisely is also a very big problem. In my group, I try to focus on doping issue, I focus on passivation issue, I also focus on dynamic issue to understand the charge transport, and we also try to solve the contact problem for 2D electronics. Let's consider the 2D field effect transistor. What target is very important. It's a cross-section of 2D electronics. As you can see, it's a gate, it's dielectric, it's channel, it's substrate. The main problem for the 2D field effect transistor we need to consider, okay, it's our result. We realize my group is taking the more than 10 material into the same place. For the 2D field effect transistor, there are a lot of problems. Something like this one for one point. How to select a channel is a very big problem. How to select a dielectric is also a big problem. How to overcome the channel substrate interface problem, and how to get a good contact resistance is also very big problem. Okay, I try to give you a table to understand the intermediate, critical, and the long-term target for the 2D transistor. Here, I try to give you a silicon as our reference. Okay, for the silicon, as you can see, the VDD is operation voltage is a 0.65 volt. The subswing, the minimum subswing is on close to the 65 millivolt per decade. The mobility is close to the 100 centimeter square per volt per second. But how about the 2D? For the 2D, actually now, for the 2D, the VDD is too large. The swing can be close to the silicon, but the mobility, actually most of the 2D material mobility is smaller than the silicon. So how to realize the intermediate target and go to the critical target and then realize the long-term target is very important. Okay, let's go to our target, Indian selenide. Actually, Indian selenide is an ultra-sensitive 2D material. The body thickness, the 1 mile layer is a 0.75 nanometer, and its band gap is about 1.3 electron volt from the bulk to the field layer, as you can see, like this one. And because of effective mass is very small, so mobility from the theoretical position, the mobility is very, very high. The history of about this material electronics can track back to the 60 years ago, published on nano later, as you can see, realize the transistor and realize photodetector and realize the electronics on the flexible substrate. But at the last moment, envelope ratio is not very high and the mobility is quite small. How about the challenge for this material? The challenge one is surface oxidation. Okay, as you can see, the surface, the oxide and the oxide or water is very easy to absorb on the surface and make a very, very low performance for Indian selenide electronics. As you can see, it's a foliation flag and the Raman spectrum like this one. Is the green line is foliate flag, but this peak will disappear very, very fast. It's because on the surface they create a lot of Indian oxide on the top, something like this one. Okay, so scientists try to use a lot of methods to overcome this oxidation problem. So they think about maybe the oxidation problem is come from the substrate. So they use a PM membrane on the bottom of the Indian selenide and realize the high mobility devices. Some people use the top surface preservation layer, so they can pin the bond nitride on the top. And then they can reduce his loop. And other group use the hafnium oxide on preservate the top layer and realize the high performance devices. And there is also one group use the Indian oxide safe growth. Indian oxide grows on the top of the Indian selenide to realize the good performance. Okay. The challenge 2 is a metal Indian selenide contact problem. As you can see, it's a band structure of the Indian selenide. It's a work function for other metal. Some people believe they can use an Indian to get the good performance. From the theoretical position, the people believe they can use a cobalt as a good metal for the Indian selenide. Other group use a graphene contact on the as a contact material, contact electrode can get a very good performance. Or there is one group use a very complex the configuration to realize edge contact structure, and they can get a very good device performance. But then this structure is not easy to realize. Okay, so for our first topic, I try to introduce a new method and to realize high performance and low contact resistance Indian selenide transistor. Okay, let's review the history of the mobility in this in this material. 7 years ago, people tried to make the devices and find the device mobility quite low. And as I mentioned, some people use a PMMA to increase the mobility. The same year, they also there is another group use the Hall effect measurement to get the temperature independent mobility. And 5 years ago or 4 years ago, try to use the dry outside method to increase the mobility from the 50 centimeter square per volt per second increase to the 500 centimeter square per volt per second. Okay, we try to use another method. This method is called the surface charge transform doping method, SCTD method. We depart the Indian metal on the top of our channel, and also using this metal as our counter electrode. And this metal layer can dope a lot of electron go to our channel, and then we can get the low contact resistance as well as high mobility devices. It's a Venn diagram, as you can see. It's a Fermi level, and this Fermi level higher than the conduction band of our Indian cyanide, and then dope a lot of electron in this interface. So this method, we can dope the channel, we can reduce the contact resistance, we can passive the channel surface. So the device figure is something like this one. The thickness, we always select the 9 to 10 nanometer. Okay, so as you can see, like this one, in the beginning, if we don't depart any metal on the top, we got a very large hysteresis loop, and the current is not very good. But when we depart the metal, something like this case, we use the 32 nanometer Indian on the top, and then we can get the small hysteresis loop and the high current and also high mobility. And then IV curve is linear. We try to study a temperature independent charge transport, and this charge transport, as you can see, the mobility increase and then saturate, and it has a loop reduce from the 20 volt down to the 0. The threshold voltage will also shift to the positive part. We also try to study the charge fluctuation mechanism, and we also study the steady state and the contact resistance. As you can see, our device can keep the performance more than 1 month. And from the statistical result, the mobility, average mobility is close to the 4,000 centimeter square per volt per second, and the on-off ratio is higher than the 10 to the 7 order of magnitude. It's very, very big. It's a Indian thickness dependent device performance. As you can see, when you increase the Indian thickness, the performance is in the doping concentration increase and the contact resistance reduce. Okay, as you can see, contact resistance reduce. And we use this performance to realize, as you can see, we realize inverter function, we realize not N and not O function, shown here. Finally, in this part, we try to give you a figure. The y-axis is mobility, x-axis is on-off ratio. As you can see, the graphene is shown here because of the zero band gap. So mobility is very large, but the on-off ratio is very small. Organic electronics is shown here. The on-off ratio is very big, but the mobility is quite small. How about our case? Our case is shown here. Our case, we got the high on-off ratio, also high mobility. And this result is much, much better than the ITRS 2.0 low power requirement. Okay, it's the first topic. And the second topic, we try to develop the safe power trouble electronics. We published this result on advanced function material. As you can see, these are our devices. We try to connect the trouble electronics, and we try to use the force, mechanical force, to reduce to create the power and then control our devices. As you can see, the different distance, we show the different power, and this different power can control our devices. Our device control like this one, the different distance for our trouble electronics, and show the different device current. And we also use this force to realize the Morse code, and also use this force to turn on the LED in our devices. Okay, it's a second topic. We try to develop a safe power trouble electronics. The third part, we try to develop the oxidation-induced charge trapping electronics. As I mentioned, the indium selenide is ultra sensitive material, 2D material. So we, in our previous study, we try to put our device into the baking condition. So for the baking condition, the hysteresis loop is very small, like this one. But for the ambient condition, it's because there are a lot of water and oxygen on the surface, so the indium selenide will absorb those oxygen or water and create a very, very big hysteresis loop. And we try to use this hysteresis loop to understand the physical mechanism and develop non-volatile memory devices. Okay, so as you can see, we try to use T-event cross-section to understand what is the reason to get this very big hysteresis loop. It's because there is a indium oxide layer on the top of indium selenide. So this oxide layer, the thickness is about 2 nanometer, and this 2 nanometer oxide layer can trap and release the charge as function of the gate voltage. So therefore, we can control the loop size and realize the non-volatile memory function. So we use the low frequency noise to understand the mechanism. We also use the KPFN to understand the potential variation. And finally, we can give you a cartoon figure like this one. There is an oxide layer, and this oxide layer can trap and detrap the charge in our channel. And then we can control the channel loop, and then we can control the threshold voltage shift value, and then we can realize the retention performance, endurance performance, as well as a multi-state storage function. Okay, so in this part, we try to realize artificial snaps. As you can see, in our previous case, we already realized non-volatile memory, and this non-volatile memory maybe can help us to develop artificial snaps. What is artificial snaps? I will introduce something. As you can see, now we are a lot of electronics in our life, and our electronics calculate a lot of data and put this data and go into the cloud. And in this cloud, calculate those data, and we download our data again. So as you can see, it's an energy forecast as function of year. As you can see, every year the energy we need increase very, very fast. So in the future, if we like to develop or deal with those data, we need to more and more power. So maybe I need to say the big data, maybe it's a big energy challenge. So how to overcome this challenge? So let's think about the computer configuration. In our traditional computer configuration, we have CPU, we also have a memory, and we try to put our data from the memory to the CPU, and from the CPU also back to the memory. We lost a lot of energy in this bus interaction. So it's a serial operation process. Also, we call a non-Newman method. It's a traditional computer configuration. How about our brain? Our brain is like this one. We can it's a parallel operation. We can computing our data. We can storage our data simultaneously. So this structure actually significantly reduce the computing step and the process, and then save the power. So the goal is like this one. We try to use a digital computer to mimic the function in our brain, and maybe we can realize eco-efficiency electronics. As you can see, people try to do that. It's a digital computer with a lot of size and with a lot of power. If we use a silicon to mimic the neural, and we can reduce the power, also reduce the thickness. We also reduce the size. But this scale also much larger than the biological neural. So we try to use our devices. As I mentioned, our device can realize non-volatile memory. So this non-volatile memory structure can connect to the snap. Snaps is a very important component in our brain. So we use the gate voltage as the input spike, and we try to observe the PSC value. So as you can see, the different gate voltage, we can control the PSC value, and the different pulse width, we can realize the EPSC. We also can realize the IPSC, and something like this one. And we also can realize perturbation or depression function, and also realize accessory SNAPs function and PPF function, and then recognition rate we also can realize. Okay, and we also take our device. We also use a light to. We also use a different wavelength light to expose our device, and then we find there is a very obvious precise photocurrent like this one. However, if we change the substrate, the precise photocurrent will reduce significantly, and then we try to use this precision photocurrent to create other interesting SNAPs function. Okay, so what is the reason to make this precision photocurrent? Is also the reason is also very normal. Is because people always know, it is well known, if we put the 2D material on the silicon oxide substrate, there are a lot of electron hole paddle, and then this electron hole paddle can be changed by tuning the potential in the substrate. So as you can see, the backgate voltage is -10, from the -10 tuned to the 55 voltage, and then the potential is totally different. So we try to use the backgate voltage to tune the potential paddle, electron hole paddle, and then we can get the new SNAPs function. As you can see, it's a precision photocurrent under the negative gate voltage, and under the positive gate voltage, the change is totally different. And then we can, this gate voltage is tunable, and we can get the different feature of our precision photocurrent. And the Lun-Yin result may be like this one. And this result is because when you tune the backgate voltage, we can trap electron, we also can release electron, and the trap and the release process, we can get the different precision photocurrent. We also use the low frequency noise to understand the detail, and we try to use the light photo as our pre-spike, and to understand, try to measure the response of our devices to mimic the SNAPs function, so we can realize a short-term short-term persisticity or long-term persisticity, and we try to use different wavelengths to gather the different precision photocurrent. We use the different power to gather the different precision photocurrent. We also use the different pulse width to realize the precision photocurrent. Okay, and then finally we use this gate effect to realize the one key feature for the short-term persisticity is called PPF, pair path precipitation. As you can see, if we give it a true pulse go to our devices, if this pulse difference is very short, and if this pulse the pulse interval is shorter, the second response will be higher. So therefore, in our device, is a pulse the interval is a pulse interval is increase, the response will be decreased. Okay, like this one. But if we tune the gate voltage, this feature will become the featureless and then become the inverse feature. So from this inverse feature, we can tune this PPF behavior. So this PPF behavior, as you can see, we can connect to the older guy and the young guy. For the older guy, the learning efficiency will decrease as a function of the rehearsal interval, something in the older guy. The young guy, they can increase as a function of the rehearsal interval. So we try to create a new function for the snaps. In the final story, we try to use our device to mimic the drug dosage modulation, something like this one. We publish our paper to the MPJ 2D material apply, and also publish it to the advanced function material. So we also use the same backgate voltage to tune the future, to increase the precision photocurrent and the decreasing precision photocurrent, and realize the drug modulation function. So I try to use a very short time to give you a conclusion. We can dope our devices. We can dope our devices. We can understand the mechanism, and we can develop the safe power electronics. We also can realize memory. For the neuromorphic electronics, we can realize artificial snaps. We can realize inverse PPF. We also can realize the drug modulation. If you are interested in our work, you can review our advanced material, advanced function material, natural communication, neural engine, and so on. Okay. Finally, thank you all of the members to work in my group. They are very nice and work very hard, and then we just can get this interesting result. Thank you for your attention.
Okay, thank you, Professor Lin. Just an announcement, I want to push you to visit the Padlet wall and post comments or questions for the various delegates of this bilateral meeting. There are 25 virtual stands with 20 institutions, with over 200 posts with videos, posters, website, scientific papers, podcast contribution. So please visit the Padlet wall and post comments there. We are very late in Taiwan. It is night now, so Carlo, please finish this session.
Okay, I want to thank all speakers and the ambassador of Taiwan in Rome, Davide Giglio, chair of Italian Economic Trade and Cultural Promotion Office in Taipei, the Deputy Minister Minn-Tsong Lin, and our Rector of University of L'Aquila, Edoardo Alesse. Thank you, everybody, and thank you for your attention. Do you want to add other information, Antonio?
Tomorrow we will start at 8 o'clock in Italy, so 7 hours later for the different time zone in Taiwan. So see you tomorrow, and in the meanwhile, visit the Padlet wall. I hope to see your comments.
Bye-bye. Have a nice day. Bye.
Good morning, everybody. I think we are in streaming now. Sorry for the few minutes delay. We are very happy to welcome you to the second day of the Italy-Taiwan Scientific Exchange Association Symposium on Emergent Crystalline Materials. I am Alessandra Guttinenza. I am the Vice Rector for the Teaching and Education Affairs here at University of L'Aquila. The university, of course, is very happy to welcome you in this symposium. So the first speaker of the day, let me introduce you, Dr. Melanie Fang Ying Kuo, Second Secretary of the Taipei Representative Office from the Embassy of Taiwan in Italy. Please, Dr. Melanie.
Right. Okay. Good morning. Hello. This is morning. Hi. Good morning. Thank you very much for your introduction, Ms. Vice Rector. So I'm here this morning to give a small introduction of the scholarship programs we have. First of all, before I start, I would like to thank University of Aquila and especially Antonio for the organization of everything. He's been a great help. So very quickly, I'm putting up the options, just not to take too much time of everybody, to let the students and researchers, professors understand what are the options and grants that we offer to study in Taiwan and vice versa to come to study in Italy. So currently in our office, we have 3 programs going on. 2 are towards students and the other one is towards researchers or postdoctoral students. So the first scholarship option is the Ministry of Education of Taiwan's Taiwan Scholarship. This scholarship is designed for people to do a degree program, either undergraduate or a master's, postgraduate, or a PhD program. The program will, once you're admitted to the program, it will support you throughout the whole study period, which is 4 years for undergraduate, 2 years for master's, and 4 years for PhD. So it is actually a program for those who want to study and carry out a complete research period in Taiwan, for those who want to obtain degrees. And the second page, please. And there is another option that is for us, the Ministry of Education Huayu Enrichment Scholarship. Huayu meaning Chinese language. So here in the Huayu Enrichment Scholarship, the duration can be from 2 months to 12 months. However, I do have to say that in our office, we normally tend to grant this Huayu scholarship for 3 to 6 months, and in some rare cases, 9 months. This is a scholarship designed for everyone who wants to learn Chinese in Taiwan. Especially, many of us know that in Taiwan we still use the traditional Chinese characters, and the Chinese teaching quality in Taiwan is also very much praised by our previous students. So the Huayu Enrichment Scholarships are designed for those who want to carry out Chinese language studies in Taiwan, and this is quite flexible. It is also available for summer months for those who want to study only a summer course for 2 months. And then the other thing, and the third program that I would like to introduce is the Taiwan Fellowship. That is to say, this Taiwan Fellowship is offered by the Ministry of Foreign Affairs. It is, let's say, Taiwan's Fulbright grant. So the Taiwan Fellowship Program grants, is a grant that's designed for researchers to go to Taiwan and carry out a specific research from 3 to 12 months. And the MOFA Taiwan Fellowship is working on a calendar year basis, which is a little bit different from other scholarships. So for the application, you should apply between May to early July, and for the coming calendar year, which is to say in the coming year in 2022, we will accept the application from May on for those who want to study in do a research in Taiwan from 2023. So this is basically one of the best options for people who are here at the symposium who wishes to carry out studies in Taiwan. Of course, apart from these studies, because to be very honest, the Taiwan Fellowship being a fund offered by the Ministry of Foreign Affairs, I think from our past experiences, it is still more towards a social science studies. However, there are also cases for scientific studies, whereas the Ministry of Education Taiwan Scholarship is a lot more diverse. We have actually accepted a lot of Italian students who went to Taiwan to do a PhD in scientific fields. Apart from these, apparently there are a lot of bilateral collaboration going on between universities. So I do encourage that everybody check out our website. This is the website of the Taiwan Scholarships and Fellowships, and all the information will also be updated on our Facebook. The Facebook of my representation is Taiwan in Italia. And then the last program I would like to talk about is the grants offered by the Italian government towards foreign and Italian citizens living abroad. So this is a really good option for Taiwanese students who wish to study in Italy. And the application period normally is between June and July every year. We're very, very grateful, thanks to the help of Minister Giglio and the Ministry of Foreign Affairs of Italy, that for the first time since last year, Taiwan is included in this program, and we strongly encourage students to take a look at this website and find out if this would match your research needs. So these are the scholarships I would like to talk about. If there is any question regarding applying for scholarships or research funds in Taiwan, you're very welcome to write us in our office, in Taipei Representative Office, or visit our website of Taipei Ufficio di Rappresentanza di Taipei in Italia, or also our Facebook, Taiwan in Italia. Thank you very much.
Thank you, Dr. Kuo, for this nice and exhaustive panorama or all the possibilities of exchanges between Italy and Taiwan. I think these are a good basis we can start from to tighten our relationships. Okay, just let me introduce now Professor Bruno Rubino, who is our Vice Rector for the International Affairs at the University of L'Aquila, and so he will talk about our international steps toward opening towards abroad. Please, Bruno.
Thank you, Alessandra, and hello to everybody. I am really happy to be here this morning with all of you and to meet the representative from the embassy of Taipei here in Italy. I hope that we have the opportunity soon to meet each other and to have you as a guest here in our university. This will be really an important step for us. I will try now to show you I will take a couple of minutes to present briefly our, I don't know if, yes, okay. It's working, right? Okay, so let me see if I can share properly. Okay. So, well, the university is, you know that we are in the real center of Italy, and it is a public university where it is included many different research and teaching programs then. Starting from biotechnologies, science, economics, engineering, education, humanities, medicine, psychology, sports sciences. we have 7 departments. The names of the department, I mean, when I'm talking about departments here, please consider like schools, and you can see from the names of the department that we are covering all the ranges that I mentioned before. The university is an average university as a size for in Italy. We have also 3 excellence research excellence centers that are mainly devoted to the to the scientific and technological side of the research, and there are some areas that are more representative of again the scientific and technological side that are considered subject of excellence for us in Italy, but also at the international level, so included in the ARVU ranking. Well, these are mainly the areas where we have also already international programs at master level. I will show you in a minute. Anyway, we have we are covering with these 32 bachelor programs all the areas at the bachelor level, but at master level we have a more broad range of coverage, and then there are 10 PhD programs mixed in the area representative of the different departments that we have, as I mentioned before. I will not enter in this list of bachelors that are in Italian, our bachelors. At master level, some of them are offered in English, and here is the list of the course that we have in English, where we already had in the past also students from Taiwan. So I hope that in the future we can have even more application from for students coming from Taiwan that try to that want to study in L'Aquila, and this can be also a way to enrich our cooperation then. And this is the list of the PhD programs that we have in the 7 departments. As you see, they cover the different areas that I mentioned at the very beginning. Well, more in, we already have many cooperation at the international level, and as for, I was mentioning before, students that in the past enrolled to our course from Taiwan, in particular the Erasmus Mundus joint programs that the university is offering are an important case where we can offer nice scholarships to the students that want to come and study in L'Aquila. There are also scholarships offered by our university. Sorry that I missed one page before. I think in this list of the international programs we offer scholarships from the university offered directly by the University of L'Aquila. So in addition to the one that you mentioned from the Italian government, it is open an application for in selecting international students to come and study with us. In particular, let me say that we offer completely free waiver for the fees to the students coming from your country. So this is something that can be important for the students. They don't have to pay anything to come and study with us, because it is a way for us to attract international students to have the free waiver for them. That is somehow the contrary of what happened in many countries in Europe, but our university we decided to do that in the last, starting from 2 years ago. So I am ready to interact with the Taiwanese institutions in order to try to do bilateral cooperation. Well, I will not take more time for the details on this. If you want, we can share also. I can share with you also these few slides in order to inform the institutions in Taiwan about us. So thank you for the attention. I know that today you have a quite long scientific part of the meeting. So I am ready for future speech with the representative of the embassies and with the colleagues from Taiwan. And thank you for this time.
Well, thank you, Bruno. If there are no questions for you and for Dr. Kuo? No? Okay. So I think this is a very good background we can start our cooperation from and try to go further. So I hope there will be opportunity to meet in person and try to go further along this line. Okay. So I thank you both for this nice introduction. And we now move on to the scientific program. We open the scientific session of the symposium. And we are going to start with Dr. Chih-Wei Luo from National Yang Ming Chiao Tang University, who will be talking about in situ visualization of activating monolayer molybdenum sulfide catalyst during hydrogen evolution reaction using ultrafast time resolved liquid cell microscopy. Please, Dr. Luo.
Thank you. So let me share my slides first. So can you see my slide?
Yes. Yes. Okay. Fine. Please go ahead.
Okay. Thank you. Yeah. Okay. Yeah. Thanks, Chair, for the introduction. Good morning for Italian friends, and good afternoon for the Taiwanese friends. Okay. So yeah. Thank the organizer to invite me to share my our recent work in the monolayer MOS2 catalyst during the HER, and we use the in situ measuring method to see the dynamics of a carrier on MOS2. Okay, so as you may know, the first hydrogen car called Mirai has been announced in 2014 by Toyota Japan. And the first hydrogen power Olympics has been realized in Tokyo this year. And recently, European Commission is also planning to achieve zero carbon emission via fuel hydrogen by 2050 and develop the hydrogen economy. So from this, we know the hydrogen is very important for the green energy recently. So I think up to now, the platinum is the common material for the water electrolysis catalyst because it has a highly catalytic activity. But however, because the scarcity and the high cost limited the large-scale development and applications. So that's why we need the alternative catalyst. And from this volcano curve, we can see MOS2 is a kind of a good candidate to be the catalyst because MOS2 has a lower Gibbs energy, which is close to the platinum. However, for the hydrogen evolution reaction, the mechanism is still unclear. For example, how the electron transfer from this catalyst material to the hydrogen ion and then from the hydrogen gas. I think this is quite difficult because the electron transfer time scale is very fast, typically in a picosecond time scale. So that's why we need the developer to develop a novel operational technique by using the time-resolved liquid cell microscopy to study the carrier dynamics during HER. Okay. Yeah. So let me briefly introduce the MOS2. As you know, this is the kind of MOS2 lattice structure, which is a kind of layer structure. So you can easily reduce the to produce the monolayer MOS2 by mechanical exfoliation. And this is the typical band structure of bulk MOS2, which is a kind of indirect band gap. But if you reduce the number of MOS2 layer, the band structure will gradually change from this indirect band gap to the direct band gap. For example, for the monolayer MOS2, and for this case, the band gap is around 1.9 eV. Okay, so we can easily to excite this the carrier from valence band to the conduction band by the visible laser. Okay, and so this is the typical HER device in this study, and as you can see here, we have the MOS2 single flat, which is prepared by the CVD deposition. And this single flat MOS2 is prepared by my colleague, Professor Zhang Wenhao. And as you can see here, we deposit the gold electrode at the one corner of this single flat, which is carried out by the Professor Chih-Wei Luo from the National Taiwan University. And in order to protect the electrode and define the HER area, we use the photoresist to cover on the electrode and the sapphire substrate. And as you can see here, this area, we can feed the electrolyte into this area, which is the hyperchloric acid in this study. And we also use the O-ring and a piece of gas to confine the electrolyte and to define the reaction area. And in order to study the carrier dynamics on this single flat MOS2 in space, we combine this kind of laser scanning microscope with the standard two-color pump space microscopy, which developed by the Dr. Yumin Zhang in National Taiwan University. And so with this tool, we can further mapping the carrier dynamics at the low H site within this single fret, okay, with the spatial resolution of around 1.5 micrometer. Okay. And okay, so this is a typical IV curve for our HER device. And as you can see here, the onset of this IV curve is around minus 0.2 volt. So which means below this onset voltage, we call the HER-on region, and above this onset voltage, we call the HER-off region. And the inside show you the PL spectrum for this blue curve is from this point at the 0.3 volt. And if we go to the minus 0.3 volt, as you can see, the PL spectrum become very small and has a redshift. Okay, yeah. And then we carry out the Pump-Pro measurement at this 0.3 volt, and you can see this is the spectrum. The Pump-Pro spectrum show you a very slow relaxation process, and the signal is also small. But if we go to the minus 0.3 volts, you can see the signal of the Pump-Pro spectrum become very large and decay very fast and following the slow decay process. And for in order to clearly see this relaxation process, we plot a semi-log plot as this inside. As you can see, here we can see very fast relaxation process with the relaxation time tau 1 and the amplitude A1. For the slow decay with the longer relaxation time tau 2 and the amplitude is A2. Okay, and here I show you the whole Pump-Pro spectrum from the 0.3 volt through the across the 0 and go to the minus 0.3 volt. So from this spectrum, we can use the double exponential decay function to fit all the spectrum here and to extract the fast component and the slow component. And here I can show you the A1 component, which is the fast relaxation process. The amplitude of this process gradually increase as decreasing the potential bias. And on the contrary, the A2 component, which is from the slow component, will gradually increase as increasing the bias. So from this, we can get the idea for the A1 is related to the triome from the PL, and the A2 is related to the acetone. Okay, so now let me show you the mapping on the MOS2 surface. As you can see, this is the MOS2 surface, and for the positive bias, because the absorption of the anion on the surface of MOS2, so we see a lot of blue color on this surface. This blue color is indicated the acetone, so which means we have a lot of acetone on the surface at 0 picosecond. But if we go to the negative bias, because the absorption of cation, as you can see here, the hydrogen ion here, and then we see a lot of trione, which is the red color here. So this is at the 0 picosecond. And for the 0 bias, you see the almost half blue and half red color on the surface. And now let's see the video. you can see as the time increase from 0 to 5, 7, 8 picosecond, you still see a lot of blue color cover whole area of this MS2. But let's see this zero BIOS, and also we can see the negative BIOS. So as you can see, the red color almost disappear around the 10 picosecond, but the blue color can survive until 20 picosecond. So from this mapping, time-dependent mapping, we can know the S trion maybe is a good indicator for the her-on state, okay, for this her device. Okay, and now let me show you the snapshot for this acetone and the trion distribution on the MO2 surface. And so this is the positive BIOS and zero BIOS, and here is the negative BIOS. By integration the blue color on this surface and also the red color on the MO2 surface, we can have this time evolution curve for the acetone and the trion. As you can see, for the positive BIOS, the acetone dominated the whole relaxation process, and the trion is very small and very fast. But if we go to the zero BIOS, the acetone, the population of acetone and trion almost the half, 50%. But if we go to the negative BIOS, we will see the trion will dominate the relaxation process within the 10 picosecond. So this means the trion, because from the previous slide, we know trion could be an indicator for the her on state. So that means the hydrogen gas generation within the 10 picosecond. Okay. Yeah. So here, let me use this cartoon to show you the carrier relaxation process and the her mechanisms. So from this figure, for the positive BIOS, because the anion sit on the surface of this MOS2, and so this anion will block this fast relaxation channel. So that's why we can only see the slow relaxation process from this Pompro curve. And because this channel closed, the MOS2 become the inert, and then this host device will be turned off. So that means we cannot generate the hydrogen gas for this case. But if we go to the negative BIOS, the her device will be turned on, because we can find a lot of cation on the surface of MO2, which is a hydrogen ion, which can further reopen the fast relaxation process. So as you can see here, the red curve shows the fast relaxation and also the slow relaxation process. Yeah. So okay. So let me summarize my my talk here. So in this study, we successfully carry out the study of in situ ultra-fast carrier dynamics in MO2 during her, and using the Pompro spectroscopy with spatial resolution. And second, the several picosecond relaxation process is suppressed by the electrolyte. And the BIOS applied on the her devices strongly affects the photo-excite carrier dynamics of MO2. And from the Pompro signals, we found that the several picoseconds relaxation component is an indicator for the her efficiency, which also shows the distribution of activation sites during her. Okay, so finally, I would like to thank the financial support from the MOST and TCECM programs. And of course, I would like to thank my board members and the cooperators. Yeah, they contributed a lot for this study. Yeah. Thank you very much for your attention.
Well, thank you, Dr. Luo, for this very interesting talk. So should I speak louder? Okay, sorry. So I just wanted to thank you for this very interesting talk and for showing us this technique on and following, the hydrogen behavior at the top of the MOS2 surface. Let's see if there are questions for you. Can you check if there are? And so on. So there are no questions, so I think we can move to the next talk. Thank you so much. Yes.
Thank you.
And so the next talk, the next speaker will be Andrea Ienco from CNR in Florence, who will tell us about his result regarding in silicon inspired few layer black phosphorus functionalization. So please, Andrea.
Good morning to everybody. I hope you can hear me. Yes.
Yes, nice and clear.
Okay, let's start because we are already a little bit late. Yes, I'll try to stay in my time. So good afternoon to everyone and good morning for us in Italy. Today I will speak about in silico inspired few layer black phosphorus functionalization, and I will show our results from the PhosFan project. But as an introduction, I will use an old 1993 citation from Roald Hoffmann. Roald Hoffmann is a Nobel laureate in chemistry, and he speaks about chemistry, a chemist as masterful at exercising control in 0 dimension. And at that time, there was very few things in 2 or 3 dimensions. We know that 30 years later, we can say that we are really started to exercise control in 2 or in 3 dimensions. And what I will present here is our adventure in the 2D chemical world. It starts with a material, an old material. It was discovered more than 1 century ago in 1930, and it was I will say it was neglected. I don't know. No one cares about black phosphorus until someone realized that it can be exfoliate, and it can be very useful to the materials. In the picture, you will see the group of the PhosFan project that it was a project of Maurizio Peruzzini and NERC project, in which you can recognize some of the Stefan that will speak later. This project has been put together people from the chemist department of CNR, Institute of the CNR, physics and material science from Florence, Pisa and Bologna. And I would like to show you just in the bottom how the interest on black phosphorus and phosphorine will grow up this new discovery, going from few papers from just 0 or few papers for years to up to 700 last year, more than 700. So why this is so interesting, black phosphorus? Because it can exfoliate. It has a puckered surface, and a surface that is highly anisotropic. And when you have anisotropic, you can have interesting properties depending on the orientation. The band gap is increasing when you pass from the bulk to the one layer. It was thought what could be very interesting materials for optoelectronics and electronics in general. The only problem that he has high sensitivity toward atmospheric oxygen and moisture, so it will be very difficult to work with. And that it was one of the problems that we face experimentally. Just to give you a few overview of the project, you can have our review, general review on the project in this paper that is in the Padlet. And we have some high pressure study, but today what I will talk about are the theoretical computational analysis and that inspire our covalent and non-covalent functionalization. There are a lot of more, but you can check here or you can check our papers. Why we thought about functionalization about phosphorus? This was the main idea of our project because phosphorus is used as ligand for transition metal and is very useful for the zero-dimensional chemistry. Phosphorus can bind metals or Lewis acid in general. Lewis acid are molecules that wants to accept electrons through the lone pairs. It was very interesting, and this was one of our first idea is to go and see how the lone pairs of lone pairs, where they are located and where they are pointing. What we saw that the lone pair are not perpendicular to the surface, and they are bended between 20 or 30 degrees, depends more or less, etc. Their geometry are due to the puckered surface of the phosphorene, and this will have several interesting consequences on the functionalization. Just to remind you very fast that it was important for us, it was to consider that lone pairs are just at the bottom of the band, the valence band, so they can be active in the complexation. So we start with Lewis acid, and the most easiest things to do is to look at the boron adduct. So to see how the phosphorene surface or other phosphorus-based molecule, just white phosphorus, just a simple phosphine, or a more phosphine that we has also phosphorus bond. can behave with borane. Just to show you, we have some simulation of a surface of phosphorane with difference coverage of borane, just to show you how it could be look. And we just have the first surprise, and what we saw that in the case is phosphorane, the donor power of the lone pair is really less, is lower than classical phosphine. Having these results, our colleague in the lab start to think of some experiment, and the first things we tried is to functionalize the surface with pyrene boronic derivatives. This was an interesting molecule because they are optical active, and we think that we can see very easily the functionalization with the optical microscope, for instance. Unfortunately, our calculation gave the results that what we'll have only non-covalent functionalization with the carbon, with the organic part that will stay just up, will be coordinate on the phosphorine. The good news and the good results that with this functionalization, with this kind of functionalization, we can improve the stability of the phosphorine of the few layers black phosphorus a lot. This is for comparison the 2D black phosphorus as prepared and after 3 months, and you can see that from the Raman shift we cannot see any difference after 6 months. So this was not we was looking for, but still it was a very nice results. Interesting. This year's another group from Valiant group, they just did what we predict. So they show that Lewis acid. This is different kind of Lewis acid, but still this is DDA, can really protect and tune the surface of black phosphorus as we predict. At least we was very, very proud of this result that we inspire. About metal fragment, why we was trying metal fragment? Because from our history, I am from a chemistry institute that is mainly devoted to the study of the metal coordination, and so for us it was really simple to think about metal functionalization. We just think to different kind of metal fragment that we can use, and the most easier choice was the octahedral fragment, and just removing several ligands from this ML6, you can see that we have a fragment with just 5 ligands, with 4 and with 3. What we found that only 3 ML3 fragments can have the right geometry, the right ability to interact with with the surface, and we did some simulation very fast, and this is an interesting thing that we expect in a way that this coordination is not symmetrical, but depending on the surface, we have two molybdenum phosphorus that are longer, a little bit longer, and one it is a little bit shorter. This is a consequence, as you can imagine, of the different orientation, and here is you can see very well from the lone pairs on the surface. We go on and we try to just the simplest fragments and ML1, and as a representative we simulate the gold chloride. We also try to generate gold chloride fragments, and unfortunately, experimentally, we was not able to archive the functionalization we planned, but we obtained a phosphorine sheet decorated with gold nanoparticles. And still we have some other property, and this is reported in this paper that we published this year. But the most interesting results with this idea, we can just do a coordination of ML2 fragment, and experimentally we thought that the starting point was to use this complex that is a dimer of palladium with chlorine and two allyl groups. We thought that in solution this could cleave and coordinate in this way to the phosphorine surface. This was our starting point, but chemistry and reality is much interesting that we can predict. So what we had at the beginning, we saw that the functionalization seems to work because it was possible to carry out the functionalization in very mild condition at room temperature or at 40 degrees. The flakes on the microscope was looks great. It looks as usually with the same morphology. There was another point that was very interesting for us. There was no palladium nanoparticles on the surface, and it was not detected either by TEM, either from X-ray spectroscopy. But we just have some trouble. The surface, the content of palladium was too high for just only the surface functionalization. There was no chlorine atoms. The oxidation state, instead of the expected, the palladium 2 was palladium 0 from XPS and Xenex experiments. And again, carbon 13 solid state NMR told us that was no carbon on the materials. So what happened? And this was we use again simulation, and the results of our mystery was that two palladium atoms goes inside the flakes, and they make just a dimer. And this result was really in the simulation, the structure simulation and the EXAFS measurement simulation from the experimental data was in agreement. And so what we obtained instead, the surface functionalization was a interlayer functionalization that can work in several for other purpose. I am just at the end. I hope you will enjoy our journey in this 2D world. Just to show your take-home message, this is strange for an online conference because we are already at home in a certain way, so you don't need any train to go home or plane and so on. Phosphorine is can be decorated with the Lewis acid. This is really a possibility. Phosphorine metal bond are weaker, as are weaker the decoration, the phosphorine Lewis acid bond. And what we found at the end of a journey is unexpected results of a very interested dipalladium units that can be further explored in as a new materials in the work of phosphorine. Just to thanks all my colleagues and to show this is a painting in a palace in Florence. It is called the Palazzo Vecchio. It's as I know, is one of the oldest representation of the research group. You can see here the professor. This is the researchers, the students, and if you look very carefully here, there is another student that is writing the paper or the thesis. And I am finished, so I can, I can interrupt my condivision. So if there are some questions, I'm here. We are not listening to you. Your microphone is off. I am not listening. Why?
Okay, can you hear me?
Yes, now yes.
Now, thank you. So thank you for your very interesting talk. I think we don't have much time for questions. I'll probably just one if there is one. Is there? No. So I thank you again, Dr. Yanko. Then we move on with the next speaker, who is Yi-Chun Chen from National Cheng Kung University. And he will be speaking about optical and non-volatile control of multiferroic orderings in complex oxide. Please, Dr. Chen. Okay.
Okay, can you see my slide?
Sure.
Okay, thank you for the introduction. And good morning and good afternoon for friends in Italy and Taiwan. I'm Yi-Chun Chen from National Cheng Kung University. First, I would like to thank the organizer for hosting this nice symposium. It's my pleasure to have this opportunity to share our recent work here. This study is about the optical control of multiferric orderings in complex oxides. Multiferrics are material with more than 2 ferric ordering parameters, such as electric, magnetic, and elastic ordering, etc. And because of this ordered structure, they usually show non-volatile memory properties like the ferromagnetic or ferroelectric hysteresis. In complex oxides, due to the strong interplay between the spin, orbital, charge, and lattice, the ordering parameters are coupled together. Moreover, because of the cross-energy scale of the coupling mechanisms, physical properties in complex oxides are sensitive to external stimuli. It means that you can use one external field to control one ordering parameter, and through the coupling mechanism, you may also change another ordering parameters. For example, you can use electric field to change magnetic ordering or vice versa, which opens more degrees of freedom for novel device applications. Previous studies have shown modulating the multiferric orderings by electric or magnetic or strength field. But how about by light? In today's talk, I would like to present the findings in one complex oxide system. This is the strand multiferric bismuth ferrite epitaxial film. Bismuth ferrite multiferric BFO is a room temperature multiferric. It has a high Curie temperature and high near temperature. It's a G-type antiferromagnetic with the magnetic ordering plane lying on the 111 plane and with the ferroelectric easy axis perpendicular to the plane. When the ferroelectric easy axis is switched by the external fields, it will also rotate the orientation of the antiferromagnetic plane. So the electric control of magnetic ordering in this kind of system is possible. When BFO film is grown on a substrate and under a compressive strain, the material system is even more interesting. It will undergo a phase transition from a rhombohedral-like monoclinic phase to a tetragonal-like monoclinic phase. And with a suitable strain, a mixed state with the coexistence of both phases is stable and at a room temperature. The tetragonal-like phase has higher C/A ratio, so we will call it TBFO, and we will call the rhombohedral-like phase RBFO. This is the topography image of the mixed phase sample. The strip, this dark area, the strip is the R-like BFO embedded in the matrix of the T-like BFO. And unlike TBFO, which is antiferromagnetic, we can see the R-like BFO has a non-canted magnetic moment along the strip. When a CW laser beam of about 50 milliwatt was focused on the mixed phase surface, we can see a non-volatile change of the film topography. The laser light spot size is about 2 micrometer in diameter. This is the topography before and after the laser illumination. Because the energy difference between this RBFO and the TBFO is small, this result shows the incident light can provide enough energy to switch the phase. To further investigate this mechanism of optical switching, we use piezo response force microscope to examine the polarization direction of the ferroelectric domain. The phase of the piezo response oscillation with the external AC voltage will tell us the vertical direction of the ferroelectric polarization. And also for the implant component, which is depend on the tilting of the cantilever, the phase of this signal will give us the information about the implant polarization component relative to the cantilever direction. So the whole technique is what we call the three-dimensional vector PFM. This is the PFN image of the light-induced domain. The polarization orientation of the domain analyzed by the vector PFN is illustrated by the arrows. The interesting thing is the light-induced domain pattern is ordered, and the phenomenon is repeatable. When we change the laser polarization direction, or even change the laser from the linear to circular polarization, the resultant domain patterns are still the same, although I didn't show here, but it always looks like this. It means there must be some other mechanism to break the spatial symmetry and result in this ordered domain. We use Raman spectroscopy to examine the phase transition underlying. Previous study has shown TBF4 has a phase transition around 150 Celsius degree, which can be seen from the change of the Raman peak around 350 wave number. Similar to the transition with the temperature, when we change the laser power up to the critical power to switch the domain, we can find similar features. Based on this, we conclude the laser illumination can cause local heating and result in phase transition. The X-ray data also prove the crystal phase transition of TBF4 around the 150 Celsius degree. However, if you uniformly heat the sample to 150 degree and then cool down to the room temperature, the resultant domain patterns now are randomly distributed, not in an ordered way. Therefore, the light-induced switching must have some deterministic mechanism to cause the ordered ferroelectric domain. The most possible mechanism to break the isotropic spatial symmetry should be the light-induced strain. The thermal expansion due to the local heating by laser causes a large strain gradient. In this case, the flexoelectric effect needs to be considered. The flexoelectric field is a high-order term, and it will induce electric polarization in the position with large strain gradient. This is the result of phase field simulation. By including the flexoelectric field, the result is just as the experimental observation. In the experimental surface potential image, we also see a ring-shaped charged accumulation, which is another evidence of the flexoelectric effect. Combining these steps, we can achieve light-controlled multiferric ordering. And also, due to the magnetoelectric coupling in multiferric BFO, when the ordered ferroelectric domain is created by light, the correlated ordered magnetic domain can also be found on the switched region. Moreover, the domain pattern can also be controlled by different laser writing paths, which changes the strain distribution and also determine the ordered domain structure. This is another example of local manipulation of physical properties. In these three states, we shine a laser spot at a different location. So at the same point, we can switch it from the TBF4 to mixed phase and again to TBF4. And another spot is from mixed to T to mixed. So we can easily manipulate these two locations, the piezo response hysteresis, the change of the hysteresis. When a nanosecond laser pulse is used instead of the CW laser, the resultant phase distribution is quite different. Unlike the CW laser, which switches the phase of TBF4 in the laser spot center and also changes the mixed phase strip along the spot edge, the single nanosecond pulse only switches the phase in the center and without alternating the mixed phase strip on its edge. Moreover, the surface potential in the by the CW laser shows a ring-shaped charge accumulation. We also didn't see any a similar effect on the fast laser pulse. The laser heating effect was simulated by the final element method. By considering the thermal expansion, the results show that in CW laser case, the T-like phase was induced in the region of maximum strain, while the mixed phase strip was induced in the location of maximum strain gradient. And for the narrow second pulse illumination, the strain gradient only reached a maximum value in a very short period. And when it reached a critical value, the duration is only about 40 nanoseconds. This results indicates the nucleation time for the transition from the T-like to the R-like BFO needs to be longer than 40 nanoseconds. This figure shows the illumination experiment using single ultra-fast laser pulses about 50 femtoseconds. We can see the non-volatile phase transition are also observed. And from the Pampro experiment, which is supported by Professor Ruo Ziwei, the sound velocity of the light induced by the strain pulse can be calculated from the reflectivity oscillation. And in this phase system, we found the transient strain is generated at about 5 picoseconds after the optical pumping. And after about 80 picoseconds, the strain pulse generated on the surface of BFO will transport to the interface between BFO and the LAO. This result indicates the photo-induced phase transition in the mixed phase BFO can be conducted in picosecond time scale. This is the summary of the light-induced mechanism within different time scale. For long writing time, it's thermal-induced strain effect, while for ultra-short, ultra-fast light pulse is the acoustic strain pulse to switch the phase to the T-like BFO. And by using the narrow-second pulse laser writing, unnatural and sizable T-like BFO region can be created in the highly strained BFO film. The domain is formed in the ordered pattern. Again, the XLD image shows the correlated antiferromagnetic ordering with the ferroelectric domain pattern. The mixed phase region can be recreated by using CW laser. Therefore, our work demonstrates a purely optical control of the multivariate ordering. In conclusion, in complex oxides, due to the interplay between the spin orbital charge and the lattice degrees of freedom, we can use the laser light to create the ordered domain structure and perform the non-volatile control through the important intermediary of locally induced strain. In the future, the optical control layer can be working as a template to provide various boundary conditions. And by combining it with another layer of complex oxide film or low-dimensional material or other functional material, we hope more interesting physical phenomena can be manipulated. I would like to thank my collaborators for their contribution to this work. I also hope to have the opportunity to establish a cooperation link with the research group in Italy in the future. Thank you for your attention.
Thank you so much, Dr. Chen. Very interesting results. Let's see if there are questions. We may host just one. I don't see any, so I think we can move on. And so the next talk will be given by thank you, Mr. Chen, by Dr. Silvia Picozzi from CNR in Chieti. And she will tell us about spin-orbit coupling in functional 2D ferroics. Please, Silvia.
Hello, can you see the screen?
Sure.
Okay, yeah.
Please go ahead.
Yeah, thanks so much for the introduction, and thanks so much to the organizer for inviting me here. So today I'll give a talk on basically the exotic spin texture that we found in recently two-dimensional magnet. And this will be the focus of the talk. I will, in the first part, I'll give a very brief introduction on spin-orbit coupling in general. So we are basically working in Chieti on the Adriatic coast, so about the same latitude as Rome, but on the other coast. And I lead a very small group. So here, in particular, you see Danila Moroso and Paolo Barone, whom I would like to thank because they are mainly the author of what I will show today. So we basically tackle several classes of material, including oxide and organic, in hybrid organic and organic materials. And we are basically a density functional theory group. But also we benefit a lot from symmetry analysis consideration and modern Hamiltonian studies that complement our ab initio results. So our focus is basically starting from electronic structure theory in the aim of understanding really the microscopic mechanism of what is behind the phenomena that we are investigating. Because of course, if we understand the microscopic mechanism, then we can optimize for several, aims, and eventually do some materials design. I mean, I would say that in the group, we mainly tackle the coupling between different phenomena. So for many years, we tackled the coupling between ferroelectric and ferromagnet, much as we have seen in the previous talk in antiferroics. Then we moved to the study of the coupling between ferroelectricity and spin-orbit coupling through the Rashba effect in Rashba ferroelectrics. And very recently, we moved to the coupling between magnetism and topology by Taki Skirner, which is what I will show today. So spin-orbit coupling, very brief introduction. So it's a relativistic interaction, and it actually tells us about the coupling between spin and orbital momentum. So it actually links the real space coordinate and spin coordinate. And it is important in both non-magnetic solid, actually many of the topologically non-trivial phenomena in non-magnetic solids, such as non-magnetic topological insulator or Dirac materials. Spin-orbit coupling is really playing a relevant role, as much as in Rashba and Dresselhaus effect. And it's of course relevant in magnetic solid, because I mean the basic property of magnetic material, which is also magnetic anisotropy, is actually rooted on spin-orbit coupling. But it also gives rise to more exotic interactions, such as the Leszczyński-Moria interaction and anisotropic exchange that I will show today. Okay, so 2D magnets. There is a lot of interest since 2017 towards this class of material. They were found to be ferromagnetic even in the monolayer limit, the prototype being chromium 3, but there is a lot to understand. And if we start, talk on 2D magnets, then we cannot avoid citing this Mermin-Wagner theorem, which actually states that if we have only a kind of isotropic interaction, such as Heisenberg Hamiltonian, then there cannot be any long-range order in two-dimensional material. So, considering this Mermin-Wagner theorem, we understand even more how important is spin-orbit coupling, because spin-orbit coupling gives anisotropy and therefore allows to reach the long-range ordering even in 2D magnets. A very brief details about the materials that we study. So they are basically van der Waals material of nickel, with nickel with halides, so chloride, bromide, and iodine. They are basically the nickel atom, the magnetic atom, are arranged in a triangular lattice, and nickel is surrounded by an octahedral cage of the halogen atom, and they are edge-shaped octahedron. So if we look at the electron filling, then nickel is basically the 8, so we expect like a strong magnetic moment of 2 Bohr magneton. And then the other thing to note is that if we move from chlorine to bromine to iodine, then spin orbit increases as we go from chloride to iodine. So we expect larger spin orbit coupling related to the anion in iodide compared to chloride. So these materials were actually investigated in the bulk form for many years in the 80s. And already at that time, it was suggested that they would show some complex magnetism, non-collinear with complex spin spirals. So a couple of recalls on the kind of interaction that we considered. So we first need to recall what frustration in magnet is. So frustration is what? Is a situation in which I cannot satisfy, or the system cannot satisfy at the same time all interactions that are present. So the typical example is an antiferromagnetic coupling on a triangle. So if I try to place, two spin in an antiferromagnetic way, and then what is the third spin doing? If it's, pointing up, then this interaction is happy, but this one is not. And if I place it down, then this interaction is happy, but this one is not. So in the end, the system tries to find the compromise, usually in a very complex way. So here, like 120 degrees. So the frustration is actually tightly linked to the kind of lattice that we have. So there are certain geometrical arrangement of the transition metal atom that are prone to show frustration, such as the triangular lattice, the Kagome, and in 3D, the pyrochlore lattice. But even if I have a simple system, a spin chain, with the first nearest neighbor interaction, which is ferromagnetic, and the second nearest neighbor, which is antiferromagnetic, then it depends. If I have strong anisotropy, so like easy spin, then the system tries to reach the ground state being up, up, down, down spin chain. But if the spin are, they don't show a strong anisotropy, so they can be treated in Heisenberg or close to Heisenberg way, then the ground state is a spiral. So this tells us that having a strong antiferromagnetic J2 is prone to give non-collinearity, even in a simple chain. So now let's try to characterize our system. So by density functional theory, we can basically map our results, our total energy results on a Heisenberg Hamiltonian, and we can extract the exchange coupling. So what we get is a strong ferromagnetic J1, a negligible J2, second nearest neighbor interaction, and a strong antiferromagnetic J3. So if I now try to place my spin on my triangular lattice, first shell is ferromagnetic, no problem. Second shell, we need to satisfy this antiferromagnetic coupling. So already here, we see that we expect some non-collinearity, right? Because this interaction is satisfied, but this one is not. So in our system, because of the strong frustration, exchange frustration, we already expect some non-collinearity. But let's move on to another kind of frustration. So we learned on our courses of magnetism that Heisenberg is the paradigmatic Hamiltonian. Heisenberg tells us, that there is a coupling, there is an isotropic coupling between spin at site I and spin at site J. But actually, more generally, one should treat the coupling through a tensor form. So we shouldn't have just one exchange parameter coupling, but we should have a tensor. So even mathematically, if I take a 3x3 matrix, I can always decompose it in a trace-like term, and then I can decompose the rest in an anti-symmetric and a symmetric term, mathematically. But this mathematical decomposition can actually be mapped onto something, having a physical meaning. So this isotropic term is the Heisenberg term. This anti-symmetric is what is called Zeroshinsky-Moria interaction. And then there is this other term, which is a symmetric term, and it's generally labeled as an anisotropic exchange. So what this interaction tries to do? Heisenberg tells us whether two spin want to be parallel or anti-parallel, but it's the same if they are parallel like this or parallel like this or parallel like this. It's completely isotropic. Cellulose-Moria is a cross product. So cross product tells us, that the spin want to count. It's a zero term for parallel spin, and there is also a sign given by the Cellulose-Moria vector, which tells us whether the spin want to come, let's say, clockwise or counterclockwise. This anisotropic exchange is also something which tells us the preferred direction along which the spin wants to lie. So it's similar to single ion anisotropy. However, it's a two-sided term, but tells us also whether the spin, wants to lie in this direction or that direction. Both Cellulose-Moria and anisotropic exchange are actually driven by spin-orbit coupling, so they are relevant for heavy compounds. And in our system, in the nickel halide, there's inversion symmetry. So from the symmetry point of view, if you have inversion symmetry, Cellulose-Moria is zero. Therefore, this term is zero, and we are only left with this term, which is by symmetry given by three different off-diagonal term, and only one non-zero, diagonal term, and only one non-zero off-diagonal term. So let's try now to characterize this anisotropic exchange tensor. Nickel chloride. Nickel chloride, we basically have a purely Heisenberg decomposition, right? So there's no off-diagonal term, and all the diagonal are actually the same. If we move to something slightly more heavy, bromide, we start seeing some changes in the diagonal term, and the rise in the emergence of a small off-diagonal term. And if we move to iodine, strong spin-orbit coupling, then the JXX is very different from JYY to JZZ, and there is also a strong, relatively strong, about a quarter of the average J of the diagonal part, which is on the off-diagonal part. So this is also a sort of frustration in the system. So now, having extracted the parameter from TFT, we can actually perform Monte Carlo simulation using a Hamiltonian, which contains the anisotropic exchange plus single ion anisotropy, and we can basically try to guess the finite temperature properties and the ground state that we get. So nickel bromide. Nickel bromide, we see a temperature, an ordering temperature of 20 Kelvin, very low, not unexpected, because we have a lot of frustration, which brings the temperature down. And then what do we see? So here the notation is that the black arrow actually shows the projection on the spin on the plane, and the color tells us the out-of-plane spin component. So here, basically, what you should imagine is a complex helix that rotates in this direction. And this is not unexpected, because we have a frustration given by exchange J3 over J1. So we expected some non-collinearity, some spin spiral. So nothing unexpected. Very unexpected is the situation that we got for nickel iodide. We don't see any spin spiral. We see more like a lattice, a regular lattice arrangement of some objects. So what are the objects? We went back studying skyrmion. So skyrmions are what? They are basically nanometer-like spin texture, which have a topological origin, and they are characterized by different handedness of the rotation of the spin, let's say from the peripheral area to the center. They can rotate counterclockwise or clockwise. And usually people try to map this two-dimensional arrangement of spin on a sphere. So they wrap basically the two-dimensional spin texture on a sphere. Another quite important thing to notice is that many of the systems showing skyrmions actually have a similar phase diagram. So they start with something like a helix, a spiral, a cycloid at zero magnetic field, and then they, upon application of magnetic field, they move to conical. But there is also a region here at high temperature, and magnetic field in which the skyrmion develops. So how to characterize the topological, the topological character of the skyrmion? One needs basically to calculate this topological charge, which is given by this. In our approach, we don't have a continuous formulation. We have spins located on the different sites. So basically, we estimated the spin chirality. So vector spin chirality is what? It's the cross product of two spin, scalar, the spin of the third spin on the triangular plaquette. So already from here, you see that basically to have a non-zero scalar spin chirality, you need to have non-coplanarity. It's not enough to have non-collinearity, but the three spins have to be non-coplanar, which is actually one of the characteristics of the skirmions. Not only being non-collinear, but also being non-coplanar. So we calculated the topological charge in our system, and we actually found that they show non-topologically trivial behavior. There is a Q equal 2 in our unit cell. So you see Q equals 6 here because we have 3 skirmion in the unit cell. So they are actually higher order anti-skirmion. Anti-skirmion means that the handedness changes if you change the direction. So they might rotate clockwise in a sense, and then at 60 degrees they can rotate counterclockwise, and so on and so forth. This is a topologically non-trivial state without any magnetic field, which is kind of exotic. And it's not driven by Celiosky Moria as most of the skirmions that are present in the literature. The other characteristic is that it's a lattice. We cannot be so precise on the periodicity of the lattice because we commensurate by approach. If you do Monte Carlo, then we have to consider a perfectly commensurate unit cell. But we think that the periodicity should be of the order of 8 times 8. What happens under magnetic field? If we apply a magnetic field, then the system evolves into a more normal skirmion behavior. So these objects have actually a Q equal 1. So they start with Q equal 2, no magnetic field. Upon application of magnetic field, they move to a normal skirmion state. And then if we apply a really strong magnetic field, they go to ferromagnetic state. Okay, so let me move to the conclusion. We found in nickel I2 a higher order anti-skirmion lattice. There's no need for the B field. And it's when we discovered it was the first example of 2D magnets. And the skirmion are actually not driven by Celiosky Moria, but we believe that they are driven by the coexistence of an isotropic spin exchange and also the frustration of the J3 over J1. And there is a topological transition upon application of magnetic field. So with this, I would like to conclude that I welcome any question that you might have.
Thank you, Silvia, for these nice results. Let's see if there are questions. No?
I have a question, sister. I'm Alessandro. Cecilia, it's a very wonderful talk. Actually, I appreciate so much. And I'm wondering if you may have a control of this of the skirmion's appearance and disappearance, for instance, by using a ferromagnetic gate or electrode at the interface with the materials, so with this materials that you mentioned, or if it's if the skirmion lattice, this texture is a kind of intrinsic, state of the matter.
Yeah. So how to induce actually this skirmion? I don't have a simple answer because it's not something that you induce with say a magnetic field or an electric field. So it's hard to do that. We, in principle, so certainly with the magnetic field, you can control it, and actually what we see here, okay, here we have very large magnetic field, but in principle, yeah, with the magnetic field you can control it. Or the other thing that we are maybe thinking is to apply, because okay, along the direction okay, the skyrmion as it is non-polar, which means that it doesn't react to any electric field. However, if you apply, for example, a magnetic field in the plane, this somehow distorts the skyrmion, and the skyrmion would then have an electric polarization. So if we apply, let's say, a magnetic field in the plane, and also or an electric field, then you could, let's say, tune somehow the spin texture, which is actually something that we are currently exploring. But I say now I don't have a simple answer, but it should be, I mean, it should be tunable with a combination of electric and magnetic field, exploiting the coupling of the spin texture with the electric polarization that some of the spin spirals, which actually form a skyrmion, it's just a combination of three spirals in three different directions. So they should be polar, and so as such they should be controllable with electric field. But let's say it is it is hard. It's also not completely clear, and I should say that, whether the ground state is this, because also from DFT we see the skyrmion is actually energetically comparable to another state which is more like a spiral. So, I mean, we believe that this mechanism is there, and certainly if you have strong anisotropic exchange, you might have a skyrmion. Whether you have it as ground state in nickel I2, this I cannot be sure. So I'm basically, you know, proposing the mechanism by which I'm convinced is true, but the material in which you might have it is, let's say, still unknown and not experimentally confirmed.
Thank you so much, actually, also for the very extensive explanation.
Yeah, thanks.
Thank you again, Silvia.
Can I ask a question?
Oh, there is another question. Please go ahead.
Yeah. So these calculations are Monte Carlo simulations are presumably just the ground state or like very low temperature simulations.
Yes.
You tune like a temperature C, because it's possible that you can stabilize the skyrmion liquid. So one thing you can do is measure spin-spin correlation structure factor and the skyrmion structure factor. So you'll see very different behavior, the signatures from your skyrmion crystal. And that's we did see in some of the simulations in one particular model that we studied. But it's a very nice talk and very interesting results. I'll be very interested to.
You're right. I mean, the order that we see might not be there, and also what we actually really I said is that we don't know the periodicity, right? Sometimes we get 8 times 8, sometimes we get more like 7 times 8, sometimes we get more domain-like. So yeah, I mean, the real, as I said, the real ground state is maybe to be explored. Yeah.
How big is your simulation size?
I think we went up to 54 times 54.
Okay.
So generally they're 27 times 27. We went up to 54 times 54. Maybe it's even larger, but not that much. Not that, you know, something to have a completely disordered skyrmion arrangement. So like a skyrmion liquid.
I think I'll be very interested to talk with you offline, and because I think we have some technology we can offer to you.
Okay, sure, would be great. Yeah.
Thank you.
Yeah, you're welcome.
Okay, thanks. I think we can move on. Thank you, Silvia. We can move on to the last talk of this session. Dr. Stefan Heun from NEST, CNR Institute in Scuola Normale in Pisa. Hydrogen storage in titanium functionalized graphene. Please. Good. We can all see the presentation. But we cannot hear you. Dr. Heon, you should switch on the microphone, please.
Okay, now can you hear me?
Now you are, yes, now you are
okay,
with.
Yes, I apologize.
Sure, that's fine. Great.
So, okay,
Please,
so yeah, it's a great pleasure to be here to participate in this meeting today with you. So I would like to spend a few minutes introduction of our lab here in Pisa, and then talk about the activities of my group, and then focus on to hydrogen storage in titanium functionalized graphene. Okay, so the first, we are based in Pisa in Italy, which is world famous for the Leaning Tower. Actually our lab is located in a beautiful medieval building with a long history. Actually in 1810, Napoleon founded here the Scuola Normale Superiore. Today in this building, several research entities are performing their research, and one of those is CNR and Scuola Normale, to which I belong. And so there is a strong biotechnology activities, but also a lot of nanotechnology activities. To support these activities, there is a fully equipped clean room, low temperature magnetotransport, various scanning probe microscopies, electron microscopies, micro Raman, growth activities for 2D materials like graphene and TMDCs, semiconductor nanowire growth by chemical beam epitaxy, and also a strong theoretical activity by DFT. I myself are interested in various aspects of two-dimensional materials, and one is low temperature magnetotransport. So I'm interested in quantum Hall effects in 3-5 quantum wells, in graphene, and very recently also in Josephson junction of various types in 3-5 quantum wells, graphene, black phosphorus. And the idea is to move towards studying superconductive correlations in the quantum Hall regime. In the last 5 years, we have also worked a lot on black phosphorus. Andrea has talked about this, and so I will move right away on to the topic of my talk today, which is on hydrogen storage in graphene. And for the last 10 years or so, we have investigated various aspects of interactions between hydrogen and graphene, one like freestanding, quasi-freestanding monolayer graphene, and chemisorption or physisorption of hydrogen on graphene. And today, actually, I would like to focus on our activities on hydrogen storage in functionalized graphene via physisorption. But there's also a component on chemisorption, and this, as I will explain in a moment. So why hydrogen? We have already heard a talk by Professor Luo that has somewhat motivated this. So this hydrogen life cycle is very interesting because hydrogen can be used in a fuel cell to generate electricity that can be then used, for example, to drive a car or to heat an apartment. And in this cycle, the waste product would be water, which then needs to be split. And we have also heard about this today already to produce new hydrogen. So this is a closed circle that involves hydrogen, oxygen, and water. And in this context, however, the storage of hydrogen in a safe and in a cheap way is a critical issue. That this is no science fiction is actually underlined by the fact that there are already cars, trucks, buses on the road. This kind of research is ongoing since the 70s. And as we heard already, now you can actually buy commercial cars that run on hydrogen. On the right-hand side, you see also a German police now is using hydrogen cars. There is a regular train service in northern Germany that is running on hydrogen. There are planes already in the air running on hydrogen, and Airbus is actually also working on a similar project on hydrogen energy. So this is, I think, putting research on hydrogen in the context. And in fact, as a fuel, hydrogen has many advantages. It has the highest energy to mass ratio that we know. The oxidation of hydrogen actually produces 3 electron volt per per molecule. The waste is non-toxic and clean because the final product would be water. And in this sense, it is also a renewable and unlimited resource and would lead to a reduction in CO2 emission, which is also in terms of the global warming very important, and also would help to reduce our dependency on oil. However, it should be said that hydrogen is not an energy source. It has to be produced by, for example, electrolysis, and in this sense, it is a vector of energy. So to store hydrogen, there are several approaches. Liquid hydrogen, so liquefied hydrogen, might be useful for some applications, but is very costly and unpractical. Today, the method of choice is compressed hydrogen, which, however, involves gas bottles of up to 700 bar, which poses some safety issues. And so the most elegant way to store hydrogen would be in the solid state. So that would allow a very high concentration of hydrogen, but is still under research. All of these storage applications, however, have one common denominator. Actually, it should be a safe way of storing hydrogen, because otherwise acceptance of this technology in society would diminish. So in this context, graphene then has attracted attention because it is lightweight, inexpensive, robust, chemically stable. So all very proper and appealing properties. And it has also a large surface area, which in terms of hydrogen storage is important. Besides, functionalized graphene has been predicted to be able to absorb up to 9 weight% of hydrogen, which makes this very appealing for applications. And you see that the graphene can be functionalized with metals like titanium, which then would be able to store the hydrogen. So this has motivated us, and I'm putting here the pictures of the people who are mainly did the work to study the deposition of titanium on graphene. Here you see the STM and the lead, the electron diffraction pattern of a clean surface. And you see that actually titanium deposited at room temperature tends to form islands. By thermal desorption spectroscopy, we could unequivocally demonstrate that these islands are able to store and to release hydrogen in a reasonable temperature range. You see here desorption occurs at around 200 centigrades. Independent of this method, we also used sensitive calorimetric technique to demonstrate the adsorption of hydrogen. We use a very thin gold film thermometer on which we place the graphene, which is then functionalized by titanium. And in the moment that the hydrogen molecules are offered, the enthalpy of this reaction is releasing an energy, a heat, which actually the increase in temperature can be measured by this very sensitive gold film thermometer. And the sensitivity of this technique actually allows to measure microjoule heat deposition. And with this independent way, it was also possible to demonstrate the adsorption of hydrogen consistently with the thermal desorption spectroscopy. By now, we also understand the processes in detail that are ongoing. So if we consider a titanium-5 cluster at the surface of graphene, it actually turns out that the first hydrogen molecule arriving at this cluster is catalytically split and then chemisorbs. And this, however, leads to a charge transfer to the titanium cluster that reduces the catalytic activity, which then leads to a lower catalytic activity, and the further hydrogen molecules are rather physisorbed. What you also can see is that a titanium-5 cluster can store up to 9 hydrogen molecules. So this is all very promising. One thing that bugged us for a period is the fact that we got these quite large, so nanometer-sized islands. But the idea would be that all the titanium in the bulk of these islands would be wasted for hydrogen storage, and so we were actually thinking about ways to spread the hydrogen, the titanium a little bit more homogeneously on the surface. So why does the titanium actually cluster? This can be seen in this and in other theoretical considerations. So the binding energy of titanium on pristine graphene is actually quite low, which also implies that the titanium is quite mobile. Much higher is the cohesive energy, which means that titanium atoms, once they encounter, they prefer to stick together and form a cluster. However, you see the blue bar, which actually is the binding energy of a titanium atom on a defect in graphene, which is even much higher. And so that implies that if a titanium atom encounters a defect in graphene, it will stick there. And so our approach was to induce the defects by nitrogen sputtering on the graphene surface, and we can do this with actually atomic resolution, so we can count individual defects and so do statistics on how many defects we have at the surface. And finally, the result is shown in this view graph. So if we deposit on a sample that has a very low number of defects, we get this well-known islanding or clustering of the titanium that I have shown before. However, if we pre-treat the surface with a number of defects, you see that we get a totally different appearance. The same amount of titanium has been deposited, but we get many more islands which are actually smaller. And so we estimate that we can, by this engineering of the surface, we estimated that this should actually lead to an increase of about factor 5 in hydrogen uptake. However, it came as a surprise that later, when we performed similar experiments on nanocrystalline graphene, you see here the morphology, that actually the measured hydrogen uptake, and especially here you see these typical peaks at around 200 centigrades, on this kind of surface actually turned out to be unexpectedly lower and surprisingly lower as compared to the untreated surface. And it took us a while to understand why this happens, but actually the reason is that when the titanium atom binds to a defect in graphene, the binding is so strong that this modifies the electronic properties of the titanium and reduces the hydrogen uptake. And that brings me to the electronic properties of the titanium, which actually are very important in this context. And this has motivated us to start a collaboration with our friends from the Taiwanese synchrotron light source, NSRRC. And so Jiahao Chen and Benjamin Wu actually are now working also on titanium functionalized graphene, and they performed angle-resolved photoelectron spectroscopy. You see here the deposition of titanium, and what they actually found is that titanium deposition leads to an N-type doping of graphene. However, what they also found in their ARPAS measurements is that the Fermi level does not shift under titanium deposition, and that might appear to be a contradiction, because usually when you dope graphene, the Fermi level shifts with respect to the Dirac point. However, what they could actually show by ARPAS measurements is that there is a modification in the Fermi velocity that finally leads to a renormalization of the bands, as is shown here. So actually the cone gets a little bit larger, and so you have, at the same energy, you can put more electrons inside. And so that explains the increased carrier concentration, the doping in these films without a change in the energy. And the process, as confirmed by DFT, is actually related to a charge transfer from the titanium to the graphene. So very recently now, we were also interested in hydrogen spillover, which is also quite appealing, in which the hydrogen molecules would arrive at the surface, actually be catalytically split by the titanium. We have already seen and shown that this is possible. But then the idea is that they actually should be able to diffuse onto the graphene and chemisorb on the graphene. And we have first evidence for this by these, again, ARPA spectra, where actually after offering of molecular hydrogen and band gap opening in the graphene is observed, that usually is associated to chemisorption of hydrogen atoms. And so this would indicate that actually really the titanium will be able to split the molecules and lead to induced chemisorption on the surface. So I'm at the end of my talk. I hope I didn't speak too long. I would acknowledge the co-workers in my group. The work was essentially done by Torge Mashoff, Stefano Veronesi, and Yulia Morata. We get graphene from Camilla Coletti's group, and then we have collaborations with Asia, with Hibino-san from NTT in Japan, Takahashi-san from Hokkaido University in Japan, and with Dongmok Wang in Korea. And last but not least, I would like to acknowledge the collaboration with the friends in Taiwan. Benjamin Chung Lin Wu from Tainan, Chia-Hao Chen, who is a researcher at the NSRRC in Hsinchu, and Forrest Chen in Taichung. And with this, I would like to thank you for your attention and be happy to have your questions.
Thank you. And I was thanking you for your talk. Just one question. I mean, in this last mechanism that you were describing, in which titanium is breaking up the hydrogen molecule, then causing hydrogen chemisorption, is this a desirable property of the surface for storage, or is it then becoming too costly to take out hydrogen again when it's needed?
Yeah, that's a good question. So there is, of course, it would cost, if you were to desorb the hydrogen thermally, it would cost very high energies, about 600-700 centigrades to desorb the hydrogen again. We have some ideas and to use the corrugation of the graphene to modify the binding energy so that variation in curvature actually could lead to spontaneous desorption of the hydrogen, chemisorbed hydrogen from the surface. I didn't have time to go into detail here, but if we were able to engineer the curvature of the graphene sheet, it's like a sheet of paper. Let me see if I can show it. So if you can tune the curvature like this,
yeah,
you would be able to induce desorption.
I see. Okay. Thank you. Thank you so much. Well, I'd like to thank, if there are no more questions, thank you again, Dr. Heun. I'd like to thank all the speakers that participated to this first session of the second day of the workshop. And so I think we can just take a 10 minutes break or a coffee break, and then we will be back for the last part of the workshop. Thank you all for now, and let's see in 10 minutes.
Welcome to this second session of the day. We will have 6 different speakers. Let's start with Minn-Tsong Lin from National Taiwan University. He will speak about probing charge orders and hidden topology at atomic scale by cryogenic scanning, transmission electron microscopy, and spectroscopy. So, Minn-Tsong, the stage is yours.
Okay, thank you. So, can you hear me?
Yes, you go ahead.
Okay, thank you. So I like the workshop quite a lot. So made me feel quite happy anyway. But anyway, I changed the title of my talk to this one. So this means that I did not see charge density wave, but I still keep the hope. So and then today I will briefly talk about 2 examples. One is a 1D system coming from Professor Liu Qingsan's crystal. The other one is coming from my colleagues Wei-Ting Chen. And then this is about a 3-dimensional system. Okay, so throughout my career, I found that myself, I only interested in one thing, charge screening in matters. So this is described by the complex dielectric function. So the second term is well known as the Linhart response function. So the long wavelength limit solution of this complex dielectric function actually is this plasmon, which is a charge oscillation pattern under an AC electric field. And then this is a classical representation about our plasmon frequency. And then another limit is the steady limit. And then you have two regimes. One is the long wavelength regime, one is the larger Q regime. So in this long wavelength regime, the solution is the famous Thomas Fermi screening, which means that the electric field or the potential vary very slowly inside the Fermi screening length. Then beyond this length, there is no net electric field anymore. And then when your wave vector is larger, close to the 2 times of your Fermi wave vector, then the solution becomes a very interesting pattern of charge density wave, which is a sinusoidal oscillation of your charge. And then this kind of pattern is very similar to plasmon, but with the 2 different kind of property. This one is static. That one is we can call it dynamic. So using my experimental technique of 1 angstrom electron probe, of course you can see atoms, but if you combine with the electron energy load spectroscopy, actually you can take all the spectroscopy of a given atom, and then this makes this technique has a very fantastic resolution, both in energy resolution and also in real space resolution. And then so using this technique, I already seen a plasmon dispersion, plasmon distribution in real space, and also I have seen this kind of Thomas Fermi screening also in real space at the atomic scale in my career. But I did not really see charge density wave in my career, so this is my personal motivation to do this experiment. But I must correct myself. I am not only interested in charge screening in matrix, but I should say more correctly that I like this topic quite a lot. Anyway, so now let's go to the extreme 1D solution for this linear response function, which is the center for the charge density wave solution. So in a 1D system, the susceptibility can be simplified into this term. So it's easy to recognize that when your Q equal to the 2 times of your Fermi wave vector, the susceptibility would simply diverge, which means that there is an electronic instability in your system. And then this to be screened by this kind of a condensation of a phonon mode, which means that a new structural distortion type will take the place of a screening for this kind of electronic instability. And this behavior is called Kohn anomaly. So this kind of very interesting electron-phonon coupling interaction make the topic of CDW quite an interesting one. And then ever since, people is very interested in looking for the ideal 1D system to find a great physics inside. But actually, in real world, it's not easy to find ideal 1D crystal 1D system. But actually, if you want to understand the physics a little bit more, you need to go back to this pious instability model. So the idea is quite simple. That suppose that we have one row of atom, and then each atom only have field, which means only 1 electron inside. And then you will have a smooth charge module, charge pattern like this one, with a characteristic parabolic dispersion. And then so at a Fermi wave vector, you will simplify that. You just like have a 2 equal energy rod, and then you do have the opportunity of scattering 1 electron from one side to the other side. It's just like a kind of a charge pairing, and then this has a beautiful name of a Fermi surface nesting. So if this do really happens, you will find this kind of a Coulomb interaction, just a attractive force pull the 2 atoms closer, and then you have this kind of atomic displacement pattern. And then concomitantly, you will have this kind of more intense charge at the center of your atom, and then sinusoidal pattern like this way. So if this when this kind of thing happens, then your original atomic displacement pattern and charge pattern will become a sinusoidal pattern of beautiful this kind. And then when this happens, the whole system will gain the energy by opening up a small gap at the cost of the condensation of the phonon mode, which we just talked about, the Kohn anomaly. And then this gap is usually very, very small. And then so this kind of physics is called a weak coupling regime, and then which is typical for a superconductor as well. And then so now we want to see highlight one very interesting thing is that Professor Shan Lue, he really found grow a very interesting idea 1D model system for the CDW, and then which has an exceptionally high charge density wave transition temperature of 33.5 K. And then the report modulation wave vector is along A-axis with a very interesting coupling along C-axis. But we do not want to go to too much detail at the moment. And then, but if you look at this atomic scale resolution imaging, you will really find out one very interesting feature. Actually, the corresponding diffraction pattern tell you that there is no such Q vector modulation simply along the A direction. And then if you look at the atomic resolution image here, if you can, you will also directly find out that the atom doesn't really move along A axis. So this tells us one interesting story that actually the published story about CDW modulation pattern, atomic displacement, and charge modulation pattern of this material actually may not be just as described in this beautiful PRL and PRB paper. And then we are now working on this system way more. And then today we have a very interesting Q-dependent ESN result and also atomic resolution result coming up in the morning. But I did not have time to tell you the details. So allow me to tell you a story next time when we have the opportunity. Now let me bring you to the 2D extreme example of a counterpart of CDW. And then this is usually found in a two-dimensional oxide crystal. We call it a correlated oxide regime. And a typical example is this superconductor. So the Coulomb repulsion force of U is so large that actually all the spin like to stand up in this kind of beautiful anti-ferromagnetic pattern. So now if you perform hole open to the system, actually the hole heat will not tend to move by randomly inside the two-dimensional lattice grid. Instead, they will tend to aggregate along a one-dimensional line. And then this kind of one-dimensional line just looks like so much similar to the CDW. And then the more hole you do, then the more line you will form in the crystal. And then this kind of pattern people call it stripe. And then this kind of stripe, it can be static, which means that the whole line standing at a, the whole line standing at the atomic position O, the whole line can also be delocalized from your atomic position. We call this a dynamic stripe. And then no matter what, your Q modulation wave vector, your Q modulation wave vector will be perpendicular to your stripe direction. And then this is interesting. So now let's put this simple cartoon like this. This is a stripe in the two-dimensional matrix. So your stripe is embedded in this pattern. And then so you will feel that perhaps this look different from the CDW. But if you look from the cross-sectional projection, you will find out that they have a very interesting similarity that they both broke the translational symmetry. So they are both translation symmetry breaking type of a lattice modulation and also charge modulation. And then the question is that how to find out this kind of stripe experimentally in real material systems such as this cuprate and nickelate system. So the answer is very simple. You need to work very hard to find out where it is. So then then you will find out interesting thing. The two examples, they have almost the same crystal structure, but the modulation pattern is different. One is along A axis, one is along the lattice diagonal. So this makes the whole search for the Q vector very painful. So my interest is that is there no way to simplify this kind of search for Q modulation wave vectors? So if yes, what may be the guidance? And then the second question I'd like to address is that actually in this kind of ideal classical model, the charge and lattice coupling pattern has not been exactly addressed in the past. So I'm thinking about maybe this is a good topic for me to dig in. So then let's talk about the symmetry guidance for this kind of search for a Q vector. So actually, if you want to think about this kind of physics, you must go back to the classical physics of a Landau phase transition. So indeed, if the system has an order parameter at low temperature, then we, of course, will have a symmetry breaking from high symmetry to low symmetry on the occurrence of the order parameter. But Landau did not tell us how to go from high symmetry to the low symmetry. But very fortunately, these two experts in the world, the great expert in the symmetry, they work out a Gaussian radical measure to gauge where is the order parameter, symmetry and direction, and then the whole series called the isotropic subgroup. And then this idea behind is very straightforward. So actually, for each crystal system, you have your K vector, and then at each K vector, they decompose what may be the irreducible representation, and then the order parameter and the symmetry behind. So by example, if you have a phonon minimum here, means that your crystal structure is not stable at S point, then you can break down what's the detail inside. By example, there should be order parameter along the AA direction. So now let's look at the real example. This is the real example of a symmetry breaking from the tetragonal one to the orthorhombic one, and then the corresponding phonon calculation. So there should be a phonon instability at the S point with the symmetry direction along AA. Now, if you look at the crystal, and then this is a 45-degree rotation compared to the parent tetragonal one, and then this is a 110 projection, which means the 45. And then indeed, you see an order parameter indeed onset along this 1-1 direction by new kind of arterial distortion. And then because of the degeneracy of this kind of AA vector, you can have a fold pattern inside your crystal. This is what we call it fold domain. And then now if we put together with the interesting model of a spontaneous symmetry breaking in quantum system, then you will find something interesting similarly in the two different concepts. Okay, so here is the goldstone potential. So supposedly we stand at the top point of the potential. Of course, we like to go to the lower energy point. So if there is no any symmetry operation at the lower energy point, then of course your order parameter space will be homogeneous, which just like that I go to some place which has no constraint on the symmetry operation. And then ideal system would be a free speed. So, but if now you have a rotational symmetry breaking like this one, by example, a 4-4 symmetry breaking like this one, then when we go to the lower the potential bottom, you will have this kind of symmetry breaking pattern, forming a kind of 4-4 topology. So then if you put together this one and this one, you will find out they look so similar. So it seems that the domain in Landau physics and then the topology in this kind of quantum spontaneous symmetry breaking has some similarity. And then can we use the charge order or charge density wave symmetry breaking translational symmetry breaking model to test whether this kind of a domain topology similarity does exist or not? And then it happened they are running into this crystal, and then this crystal has a report a charge order at this place at 240 with a window of 240 to 260 K. And then so I simply think about it. Can I look at the detail in this guide and then see whether I can try to test the idea I just try to explain to you. So if we look at this symmetry transition pathway, you will immediately find out that actually the report the room temperature symmetry and then low temperature symmetry, actually they do not describe by this Gaussian theoretical method, which is quite universal at the moment. And then so this implies that maybe something happened at the room temperature and also at low temperature. And then my experimental technique, which can cover this temperature range of 100 to 300 K, may be an ideal tool to tackle the detail inside. So let me just address the room temperature symmetry. Immediately we find out that the symmetry is not rhombohedral, it's rather orthorhombic. And then using the experimental technique called convergent beam electron diffraction, which is a way to sample the phonon dispersion symmetry inside your crystal. And then this is a very powerful way to check the micro distortion of the real symmetry of your sample. Then we find out indeed the symmetry is an orthorhombic one. So follow the Gaussian theoretical method, there should be 6 different kind of domain inside the crystal. And then indeed we see 6 different kind of domain if we consider contrast reversal. Then using the same principle, we go to the low temperature, we find out that the low temperature symmetry is a monoclinic one. And then again, we work out the Gaussian theoretical way. We find out that there should be a order parameter along AC direction. So if you look at this diffraction pattern where you do have an AC vector, you find some very weak spot in between. And then this is a hint that there should be some new order along AC direction. And then according to the Gaussian theoretical method, you should have a 2 domain, as just we experimentally found. Indeed, the domain pattern at low temperature, room temperature, they are different. And then this kind of domain reformation or recrystallization is plain way of the which is observed here. Let's look more about the low temperature AC modulation. So let's just tilt our crystal a little bit. And then we can see this kind of modulation pattern along AC direction more clearly now. And then if we probe the intensity profile along this AC direction, you will find out that there is a very interesting modulation periodicity of 1/6 over here. And then if this 1/6 is coming from a density wave-like modulation, which means that the second harmonic should have very, very weak intensity or vanishing. Because if this is a wave-like modulation, if the second harmonic just means that the 2/3 wavelength, and then in this kind of 2/3 wavelength, you cannot describe a complete wave. So the intensity must be vanishing. So indeed, the second harmonic has a vanishing intensity. So tell us that the first modulation can be a wave-like modulation. And then the wave-like, of course, also describe the stripe. So we cannot tell people that this is a 1/6 modulation wave vector is a CW or a stripe. We don't know. But the interesting point is that while the third harmonic, which is the 1/2, the intensity rises again. And then this tells us one very interesting thing. Maybe there's another order parameter coexisting with this 1/6 order parameter. So let's just narrow down our electron beam down to a few nanometer. So we can pinpoint where you have this kind of a Q vector, this 1/6, and then where you do not have. And then we just pinpoint our electron beam at the two different positions. And then exactly found that actually the bright contrast coming from where you have a 1/6 Q vector. And then the dark region coming from where you only have this kind of 1/2, this kind of a modulation wave vector. So indeed, we find out that there are two other parameters coexisting in this material. One we call it 1/6, the other we call it 1/2. And then this 1/6 we call it tentatively we call it Q. The other guy we call antiphase for convenience. And then so the modulation, the length scale of these two separate order parameters can be estimated directly using the Q vector over here. So it's about 2/10 of angstrom. But if you consider the order parameter space, which has a very similar to a stripe, then the width is the mesoscopy length scale. So you have a very interesting complication about microscopy length scale and then mesoscopy length scale in one single material. And then this is something has not been really pointed out in the past in other material systems. So now let's look at atomic evidence. So now let's go to this room temperature, everything just a square, beautiful, no distortion. And if you go to low temperature, you start to find out that this is where you have your Q1/6 modulation. And then this is the one order parameter length scale, which is 31 angstrom. And then this is where you have antiphase modulation order parameter, the length scale is 10 angstrom. And if you look at the manganese atom inside, you will find out that the manganese atom inside has a very interesting ZZ modulation. And then it changes the phase from position 1 to 2 and then restore to the back to the right phase at position 3 again. But for this guy, the manganese atom just moved to the right, and then this is very different. And then this is, of course, to see this, you need to have very good trained eye. Otherwise, you need to use the measurement way. So let's try to measure the atomic displacement and then the results here. Then trust me one thing, the displacement pattern here simply follows sinusoidal pattern. Not perfectly, but more or less follows sinusoidal pattern. So tell you that this Q order parameter may be a charge density wave. And then for this guy, we don't know what is this. Then that's a simple question to ask. Is this kind of an order parameter, CW-like, can the charge also have a sinusoidal modulation pattern? So we use our atom by atom spectroscopy to measure the spectra. And then this kind of spectra we call energy low spectra, which is very similar to X-ray associated spectra. And then so from going to the left to the right along this blue atom, manganese atom, we see slight red shift. And then for the light blue atom, we see slight blue shift, which means that for the row 1 atom, manganese atom, you have a slightly this kind of a charge going down a little bit, and then the other are going up. So if you plot out where the various characteristic of these different manganese atom, you'll find out that actually this is not a sinusoidal pattern. So, but simultaneously, the atomic displacement is a sinusoidal pattern. So let's borrow the beautiful name of charge density wave, but we twist it to we call it charge density modulation order parameter because it's not exactly CW. But if you do the same thing for this green order parameter, we call it antiphase 1, you'll find out very interesting thing is that actually you do not have this kind of a charge modulation, but instead you have a further gap in your by 0.3 eV. It's just like that. The CDM order parameter is a relatively more conductive one, and then the AP or antiphase order parameter is a relatively more insulating one. And then if you now put together all the information, then it's a very interesting. So this is the mesoscopy pattern of what it looks like. And then so here, the blue one is where you have a CDM order parameter. And the green one where you have an AP order parameter. And then remember again, no matter which order parameter, they are both translation symmetry breaking one. Now if we look at the translation symmetry breaking example in this kind of quantum instability system, then the good example is a symmetric one. And then this is the translation symmetry breaking a topological pattern. And then if you look at the topological pattern, you will find out that this is the symmetric charge order. And then you will have this kind of characteristic topology with the distance between your stripe inversely proportional to your Q vector. And then you have a topological dislocation look like this guy. And then if you compare to this kind of microscopic landscape topology to your mesoscopic topology, you find out that yes, when they are all translation symmetry breaking system, they could have a very similar topological landscape. But of course, the order parameter detail inside are different. So this kind of thing is just very mysterious for us, and we do not understand why. So in the beginning, we think that can the strength inside be a factor? So if we look at the Adami scale imaging of the boundary between these two order parameters, you'll find out that there is no visible distortion. So it cannot be a distortion problem, a strength problem. Then, but if you supposedly this antiphase one is a more positive one, and then the area ratio of a 4 versus 1 have a very interesting correspondence to your quarter whole doping of your nominal chemical formula. So this just implies that there is another degree of freedom behind, highlighting the similarity between the two different phases, which maybe you have some kind of electrostatic landscape pattern here, also address the similarity here. But honestly speaking, we do not really understand why. And then for this, we suffer a lot from the whole rebuttal the process. So anyway, if we apply the same cool theoretical concept to the original two system, the two-dimensional one, this guy and this guy, you can exactly predict that there should be an order parameter along A0 and then along the lattice diagonal, just as what experimentally has been proposed. Okay, so now this is the end of my talk, and then I just want to tell you that. So now we are trying to use the same thing to do to characterize the ideal 1D system, and then to find is there any universal character in this kind of translation symmetry breaking physical system. Okay, many thanks for your attention.
Thank you, Min-Wen. I have firstly a curiosity regarding the energy resolution of your Hills spectra. You know that currently there are many efforts in order to improve the energy resolution in Hills coupled with transmission electron microscopy, with some attempts which already reached 15 millielectron volt. Can you comment on it, on the impact of the improved resolution in your activity?
Oh, actually, yeah, you hit the right point. So for 15 millielectron volts, you need to be a rich man, and then so I'm a relatively a poor man. So the energy resolution I can have is this. So for atomic resolution spectroscopy, the energy resolution is only 1 eV. It's very bad. So,
yes.
But for momentum-dependent years, then the best energy resolution we can have is 0.2 eV, which is still bad. But if you use a 0.2 eV energy resolution for Q-dependent years, you still can find some interesting system you can do. So, by example, we have been working on graphene, monolayer graphene.
Yes.
Yeah, and then so now we are trying to apply the idea to CUTE and then other CW system. So of course, I love to have a millivolts energy resolution possibility, but for this, I will collaborate with my friends in Kyoto University. They do have the facility of about few tenths of a millielectron volt, not 15 millielectron volt, definitely.
And what about low loss Hills? The low energy excitation can be interesting for you.
Yeah. Now we are pushing the limit. So the lowest we can do now is about 0.8, 0.9 eV, and then we see some interesting thing already. And then, but it's not publishable at the moment because we need to deal with the momentum, some momentum detail inside. And yesterday I quickly went through your nice paper with Professor Shan Lue. I like it a lot. So yeah, I think we can have a lot of interesting conversation in the future.
Yes. It will be very interesting.
Yeah.
So let's meet even beyond the conference. Now we are a bit in delay, so if I would ask participant to do question to Ming-Wen by mail, and let's start with Christian Martella from CNR, Institute of Microsystem and Microelectronics in Agrate Brianza, who will present artificial shape engineering of molybdenum disulfide layers. Christian, now the stage is yours. Go ahead.
Thank you very much, Chairman. Thank you to the organizing committee for the opportunity of giving this talk in this very nice and exciting symposium. I hope that this will be the chance to start a fruitful collaboration with the Taiwan community. So before starting the talk, let me introduce myself. I'm Christian Martella, and me with the CNR and the Institute of Microelectronics and Microsystem, and together with Alessandro Molle that is in the audience, we are in the unit of Agrate Brianza, which is located in the north part of Italy, near the Milan city, metropole, in the north of Italy. Here we have two, let's say, main directions in the study, in the topic of the 2D materials. The one that was described by Alessandro Molle yesterday in his talk, based on Xin, the monoelemental 2D materials. We deal with silicon, tin, phosphorus, tellurium. And the other direction is on transition metal dichalcogenides. Here, we focus more specifically on the growth of molybdenum disulfide, molybdenum ditelluride, and tungsten disulfide. Let me mention only one thing is that we are really interested in how to engineer the physical properties of this material. For example, by introducing in the process of the chemical vapor deposition some strategies to tune, for example, the photoluminescence, the optoelectronic properties of this material, photoluminescence, mobility, electromobility, exciton populations, and electrostatic properties. But today, I would like to have a view to give you an edge on another kind of activity that we do in this field. Then we already know, we all know that the class of 2D materials is flatland, that where the main exotic properties derive from the fact that we have a quantum confinement in the direction orthogonal to the plane, and it's quite general to have an analogy of these 2D materials with paper sheets. Going further with this analogy, we know that paper can be, let's say, can have some shape transformation of paper sheets in order to introduce complex curved shapes, or to reduce it in stripes, for example. And it is what we try to do. And these nice pictures show you that we are able to bend or to create stripes of these materials. In particular, these are images of molybdenum disulfide layers. And in a minute, I'm going to show you how we approach this topic. The motivation are countless to introduce such shape transformation in 2D materials. We already have an hint of this in the previous talk delivered by Stefano, where the curvature in graphene have an impact, for example, in the hydrogen absorption. But in other motivation can be to tailor the optoelectronic properties of the materials at the local scale, as I can mention, for example, a boosting of the electron mobility in MOS2 layers when they are carved at the nanometer scale, or the possibility to tune the emission of photons in wrinkled MOS2, for example. Our goal is to introduce this shape transformation in the transition metal decalcogenites, starting from in a deterministic way and starting from the early stage of their formation in a chemical vapor deposition approach. To do this, we started to use pre-patterned substrates in the chemical vapor deposition equipment that we have, but we had our results were not as expected. As you can nicely see in these SEM images, when you use the pre-patterned substrate as is in a CVD, what happens for the growth of MOS2 is that MOS2 form in the form of platelets, which are randomly oriented on the surface. It seems not to have any kind of relation with the pattern features of the substrate, and in some cases these platelets grow also in the out of plane of the substrate. You can see it grows vertically. Therefore, we developed two approaches in order to address this problem and to try to have molybdenum disulfide sheets that conformally replicates the substrate features of the pattern. In the same CVD equipment, we started with one approach where we start from molybdenum oxide precursor pre-deposited on the pre-patterned substrate, and we tried a sulfurization transformation of this molybdenum pre-patterned film. And the second approach was to pre-functionalize the patterned substrate with some kind of molecular seeding promoters, like the PTIs shown here, that is known to promote the 2D growth of molybdenum disulfide layers in CVD and in general of the TMDs due to the reduction of the interfacial energy at the surface of the substrate. So in the first approach, we have we used two kinds of patterned substrate. One that is a self-organized pre-patterned substrate obtained by ion beam sputtering, and where we pre-deposited the molybdenum films for the sulfurization. And the other pattern was a lithographic generated pattern, very regular. We can see from the transmission electron microscope cross-section here that after the sulfurization, the MOS2 layers conformally replicates the patterns of the pattern features of the substrate, and following the two different profiles. But in this case, what we observed is that the molybdenum disulfide layers were grown in the with granular structures that was inherited by the pre-deposited molybdenum precursor. In the second approach, the one in which we functionalized the surface of the patterned substrate, and we started from molybdenum and sulfur atoms, we obtained these nice results where from these SEM images, you can see that we are able to obtain the typical triangular domains of MOS2, of few MOS2 layers, which adapt to the local pattern. And this is shown at different magnification and with different patterns. But you can have a more compelling evidence of this fact in these high-resolution transmission electron microscope images and in this sketch, where you see the triangular MOS2 monolayer or bilayer adapting on the pattern. It's very, very interesting to see here that thanks to the Perlin functionalization of the substrate, we are able to have a conformal growth of the MOS2 layers. In this case, we have a free MOS2 layers. Here, what we are looking at are the molybdenum atoms in the bright parts of the image that bend at angles that exceed 100 degrees, and also at radius of curvature less than 3 nanometer. And they bend without rupture and without detachment from the substrate. So now here I would like to give you an overview on how these banded and MOS2 layers with this shape transformation are different or have different physical properties compared to the flat case by looking at several properties like the phonon distribution, the electronic properties at the local scale, or also the excitonic resonances, and at the end, how also when they are coupled with plasmons, with plasmonic materials, they can create an hybrid material where the response is no more the optical response is no more the one of the MOS2 layers and the plasmon layers as a sum, but is a kind of hybrid response. So let's start with the phonon properties, since the Raman spectroscopy can give us a deeper insight into the properties of this material. In the case of the rippled MOS2, the MOS2 grown on the rippled substrate, we performed micro-Raman analysis of the two characteristic phonon mode, the E12G mode and the A1G mode, that are respectively the in-plane and out-of-plane modes of MOS2. And it is very clear from these two polar plots here that the morphological modification induced by the pattern is responsible also for an anisotropic phonon response of the material. In particular, when the laser polarization of the probe is oriented orthogonal, that is this 90 degree here, orthogonal to the main axis of the rippled MOS2, we have an amplification of the Raman modes, while when the laser polarization is along the direction of this ripples modulation, this MOS2 ripples modulation, the phonon modes have the minimum of their intensity. This is also confirmed by this micro-Raman mapping of the E2G frequency map and A1G frequency map, where we can see that the position of these Raman peaks changes in the different morphological position of the sample. In particular, the frequency position of the rippled MOS2 are more or less the same of the flat case with a zero shift when we are on the crest of this modulation, while we have a huge negative shift where we are in the valley of the modulation. the origin of this shift for the E12G and A1G mode, the physical origin for this shift can be very different, as we know. In the in-plane mode, these are mainly related to the accumulation of strain in the material, while in the A1G mode, this frequency shift is mainly related to a kind of local charge distribution or local doping. And this brings me to a second characterization of this material in order to test or to study what are the electronic properties of this material at the local scale and how they are impacted by the modification of the shape from flat to rippled. And we performed a Kelvin probe force microscopy on this system. This technique is able to map at the local scale the surface potential of the material compared to the potential of the conductive tip of the AFM. And by using a calibration with some standard reference, we can also transform this information in the local electronic work function of the material. It is very interesting to note that we observed also in the potential map modulation that is in registry with the morphological modification of the MOS2 topography, but more importantly is when we compare the work function distribution that we have in this sample with that of registered for a flat MOS2 sample. The work function of the flat MOS2 sample that is quite symmetrical is now modified with some extra components that are at lower and higher work function due to the local transformation. So let's move also to the other point, that is the optical properties of this material, of this rippled MOS2. We have also observed that this we have a different excitonic properties of the layers, and in particular we correlated the modification observed in the optical response at the excitonic frequencies with the change of the permittivity, the electrostatic permittivity of the material due to the local curvature of the layers. We did this also from a theoretical point of view. I don't have time to go in such details, but I want to show here that we are able, by tuning the curvature of these layers, of the MOS2 layers, and we tune these by modifying the pre-patterned substrate used for the growth. By tuning the local curvature of the pattern, we observe a giant optical dichroism in the extinction spectra of the MOS2 layers compared to the flat MOS2 case for two orthogonal polarization of the illumination light. And also, we can modify the photoluminescence emission of the sample. And so we modify the excitonic population and recombination of the material. Another interesting result that we have, and is related to the excitonic properties of the shape modified MOS2 layers, is when we probe the temporal decay of the exciton resonance by pump and probe spectroscopy, what we observe is that, again, compared to a flat MOS2 obtained with the same approach but on a flat substrate, we observe a dichroic behavior, in particular around the exciton, the C exciton of the material, where we observe that the dynamic of the C exciton resonance is dramatically affected by the polarization of the incident probe, and that this is due to the different coupling of the carrier with the phonon scattering into the material. We have a faster depolarization of the material. And also, we used this kind of platform that we have. The one is in the rippled MOS2 and the one in the striped MOS2, to show that we can create also the hybrid system where the optical and excitonic properties of the MOS2 layers can be coupled with some mode into the substrate that in this case act as a Wegite, and we can make some create some hybrid mode that have a strange dispersion relation with the incident, depending on the incident of the light. So we can engineer the optical response by of these material, as it was a kind of metamaterials, and also we can have an improvement of the photon absorption, and this will be important, for example, in view of photon harvesting for, say, energetic or energy application. At last, to save time, I will not go too much in the detail of these measurements that are the pump and probe measurements, but I would like to give the on-take message here. That is, when you use the MOS2, the rippled MOS2 layers in combination with the with a plasmonic metal nanostructure, you obtain here a response that is not the sum of the simple sum of the response for the plasmonic nanostructure and the MOS2 ripples, but is some kind of hybrid response that is due to the hot carrier injection from the plasmon resonances into the MOS2 layers. So to conclude, I showed our approach to the shape transformation in MOS2 layers, and we believe that this can be a way to manipulate or to engineer the properties of these materials in two ways: by modifying their shape profile, but also by combining different layers of this transition method like chalcogenide, or by creating van der Waals ether structure on this platform of morphological modified sample. So let me conclude by thanking you for your attention and my collaborators.
Thank you very much, Christian, for this nice talk. Can I start with a short question on the prospect for plasmonics of these artificially shaped two-dimensional layers? What do you think?
Do you want to? Can you repeat the question? Sorry.
The prospect for plasmonics of two-dimensional materials artificially shaped.
Our goal was to prove that it's possible to use the plasmonic nanostructures as let's say, a reservoir of charges that can be injected inside the MOS2 layers by taking advantage of the so-called hot electrons generated by the plasmonic resonances. In this context, this can be, for example, beneficial for increasing the photons absorbed by the MOS2 layers that is a semiconductors, and so maybe to improve the photo conversion efficiency if we think to the MOS2 layers as active material in, let's say, some photovoltaic system, for example, or if we can think about MOS2 layers as the active material of photodetectors. So the main message is to combine the two platforms, the plasmonic system and the semiconductor MOS2 with the shape transformation to modify and improve their performances in the photon detection and harvesting.
Another short question regarding the chemical stability of molybdenum disulfide once it is artificially shaped. Is the stability different compared to the planar case? Have you tried with XPS to find molybdenum oxide features?
Thank you very much for the question. It's quite very interesting. We believe that the stability is comparable to that of the flat case. And this is made clear by the fact that we checked after months or I would say several months, both by Raman spectroscopy, and we didn't find any kind of modification of the Raman response, and also, as you suggested, by the X-ray photoelectron spectroscopy, and seems not to have a modification of the chemical coordination.
Okay. We are a bit in delay, so I would ask other participants to send messages to Alessandro Molle and Cristian Martella for their activity, and so we can move to the next speaker, Professor Efrem Curcio from University of Calabria. He will talk about photothermal membrane technology from resource recovery from brine. So we have a pre-recorded video, but Efrem is also here.
Still alive, so in case of
ciao, Efrem.
Good evening to a Taiwanese colleague. It's a very pleasure to stay with you today. Thank you for your invitation. Sustainable management of resources plays a central role in the Agenda 2030 and in the New Horizon Europe program. Pressure on resources will increase in the coming years, driven by the increasing global population, industrialization, increasing demand from developing countries, and the transition to climate neutrality. As a result, the global materials demand will double to about 170 billion tons in 40 years. European Union is highly dependent on the import of several metal ores from international market, with severe implications for the feasibility of a sustained and sustainable industrial development in crucial sectors such as chemicals, automotive, construction, aerospace, energy. Problematic political relationships with governance of countries where minerals extraction take place, in conjunction with excessively high import reliance, push towards the necessity to implement innovative technological approaches to secure undistorted access to raw materials. In 2008, the European Commission launched the Raw Materials Initiative, and one of the priority actions was to establish and regularly update a list of critical raw materials at EU level. Among the critical raw materials identified last year, there is lithium as new entry, and others identified on the basis of their economic importance and supply risk. Today, EU pushed towards the necessity to implement innovative technological approaches for the production of raw materials. Since June 2020, our research group is part of a C4Value project, funded within Horizon 2020 program, aiming at developing radical innovations to recover minerals and metals from desalination brine. Targets are magnesium, boron, and trace elements such as lithium, scandium, gallium, vanadium, indium, rubidium, and molybdenum. With more than 18,000 of industrial installations operating worldwide, about 8 million cubic meters per day of drinking water produced, more than $15 billion of market value growing at annual rate of 9%, desalination is today the most reliable technological answer to the increasing demand of water. Desalination industry is dominated by membrane technology. Reverse osmosis accounts for more than 60% of the global capacity and almost totality of new contracted plants. Despite this success, membrane desalination still faces some critical issues. Water recovery factor is limited to about 50% as a consequence of osmotic phenomena and concentration polarization. This means that for each cubic meter of seawater treated by reverse osmosis, around a half cubic meter of desalted water and a half cubic meter of concentrate, usually referred as brine, are produced. On the other hand, it's worth consider that brine contains about 3.5% of dissolved salts with prevalence of sodium and chloride ions, significant presence of magnesium, listed as critical raw material by European Union, and other trace elements potentially extractable such as lithium, rubidium, cobalt, molybdenum, and so on. The extraction of trace minerals is facilitated if it occurs from highly concentrated solutions. Membrane distillation, operated as a standalone unit or downstream reverse osmosis stage, is an emerging hybrid thermal membrane operation driven by a temperature gradient having the potential to reach up to 85–90% water recovery, coherently with zero liquid discharge paradigm, as opposed to conventional pressure-driven membrane operations. In membrane distillation, there is no filtration or transport in liquid phase. Water evaporation from seawater takes place at the interface of a microporous hydrophobic membrane. Here, water vapor diffuses across the porous membrane, while non-volatile components, such as dissolved salts, are totally rejected. Low operative temperature difference, around 30–40 Celsius degree, allow a feasible distillate flux in the order of 1.5 liters per square meters per hour, offering the possibility to exploit renewable energy sources such as solar, geothermal, and so on. Experimental investigations also demonstrated the possibility to dehydrate brines up to supersaturation for some dissolved salts such as sodium chloride, potassium chloride, and epsomite. This opened the way to the innovative concept of membrane crystallization. With respect to conventional crystallization methods, membrane crystallization guarantees an excellent control of both supersaturation profile and heterogeneous nucleation rate promoted at the membrane surface. Lithium production has been increasing, driven by the exponential market demand. Currently, lithium carbonate equivalent is around 400 kilotons per year, expected to double in 5 years. 45% of lithium is extracted today from salt lakes brines. In Chile, one of the main worldwide LCE producers, lithium is extracted from Atacama Salt Lake by a series of solar evaporation ponds where different compounds are fractionated by crystallization, promoted by solar and wind evaporation. Besides environmental impact on aquifers due to concentrated harmful elements, additional issues are the high residence time, 1–2 years depending on local weather conditions, and consequent high requirement of pond volume and area, and low control of natural evaporation rate. Here we proposed a multi-stage fractionation process based on membrane distillation crystallization for the production of lithium-enriched salt lakes brine. The measured transmembrane water flux in the range of 0.5–3.5 kilograms per square meters per hour, with average feed temperature in the range of 30–50 Celsius degree, is at least 5–10 times higher than current evaporation rates in salt lakes. Thermodynamic simulations predicted a potential water recovery of about 95% after sequential fractionation of halite, sylvinite, and K-kernelite. Application of membrane distillation at large scale is hindered by a relatively low thermal efficiency due to temperature polarization. This phenomenon refers to a decrease of feed temperature at the membrane interface, and it is intrinsically related to the latent heat flux of the evaporating water. As a result, the driving force to mass transfer decreases. To overcome this limitation, 5 years ago we developed the concept of photothermal membrane distillation by exploiting the ability of metal nanoparticles to efficiently release heat under optical excitation. In a pioneering study, we incorporated silver nanoparticles in PVDF membranes. Under ultraviolet irradiation, we observed an enhanced water vapor flux up to 9 and 11-fold in vacuum membrane distillation fed with pure water and 0.5 molar sodium chloride solution mimicking seawater salinity, respectively. In order to mitigate limitations related to the high cost of precious metal nanoparticles and to the high energy demand of ultraviolet radiation, we have also checked the feasibility of carbon-based materials under solar illumination. For instance, infrared camera images you see in this slide show that membranes functionalized with vertically aligned graphene under sunlight exposure exhibited a significant increase of interface temperature up to 50 Celsius degree. In general, energy management is a crucial aspect in desalination. Starting from the pioneering investigations of Loeb and Surirayan, who fabricated the first asymmetric membranes made of cellulose acetate in the late 70s, the specific energy consumption of seawater reverse osmosis systems decreased from more than 12 kilowatt-hour per cubic of desalted water down to the current 3-4 kilowatt-hour per cubic meter. This important achievement, that is the main reason of the success of membrane technology over traditional evaporative processes, was driven by groundbreaking innovations in materials, with the introduction of thin film composite membranes, and in processes, with the use of energy recovery devices. However, energy consumption is still far from the thermodynamic value of 1.1 kilowatt-hour per cubic meter predicted for 0.5 molar sodium chloride solution at 50% recovery factor. The energy of a pressurized brine is today recovered as electricity in Pelton turbines, or used to pressurize the feed stream by pressure exchangers. In addition, highly concentrated brines possess a significant chemical potential in the form of Gibbs-free energy of mixing that can be converted in salinity gradient power, a promising source of renewable energy, usually referred as blue energy. A theoretically available amount of energy generated by mixing 1 cubic meter of diluted and 1 cubic meter of concentrated sodium chloride solutions is in the order of kilojoules, depending on the extent of the concentration gradient. Taking into account the flow rate and the average salinity of major rivers flowing into seas and oceans, a global potential of about 2,000 terawatt-hour per year has been estimated. Together with pressure-retarded osmosis, reverse electrodialysis is one of the best assessed membrane technology to harvest salinity gradient power. Our interest in this technology originated from the participation to the project RePower, funded by European Union within the 7th Framework Programme. In reverse electrodialysis, cation exchange membranes having negatively fixed charges in their polymeric structure, thus being able to repulse anions and transfer cations, and anion exchange membranes are alternatively stacked in a plate and frame module. Spacers interposed between each membrane couple forms adjacent compartments fed with low and high salinity solutions. Under a concentration gradient, ions with opposite charges diffuse in opposite directions. This segregation of charges is converted at the electrodes in an electric potential difference, open circuit voltage, theoretically defined by Nernst-Planck equation, where alpha is the perm selectivity of ion exchange membranes. In a recent study, we integrated light harvesting self-heating membranes and salinity gradient reverse electrodialysis for light to heat to power conversion. Novel photothermal membranes were prepared by immobilizing silver nanoparticles on the top layer of polyvinylidene fluoride support and tested in a sweep gas membrane distillation. The retentate stream, obtained as a byproduct of photothermal membrane distillation, was fed to reverse electrodialysis unit for generation of blue energy. Electrical power measurements were carried out at a different brine concentration. The maximum open circuit voltage, 1.3 volt, was measured for 4 molar sodium chloride brine, and this value is about 50% higher than that recorded with 1 molar NaCl, comparable to the salinity of brine discharged from reverse osmosis plants operated at 50% water recovery factor. The rise of harvested power at higher brine concentration from 0.13 to 0.9 watt per square meters membrane pair is mainly due to the reduction of ohmic resistances in a high concentration compartment. Practical implementation of RED strongly depends on the development of a new generation of ion exchange membranes with improved perm selectivity in a hypersaline environment and with low electrical resistance. Electrochemical impedance spectroscopy analysis demonstrated that the extent of membrane resistance largely prevails on both electrical double layer and diffusion boundary layer resistances. In addition, the negative impact on the resistance of cation exchange membranes of multivalent ions and in particular of magnesium, the second most abundant cation in seawater, drastically reduces the gross power density that can be extracted when operating with natural feeds. To increase the reliability of water energy resources nexus approach, based on the integration of emerging photothermal evaporative and salinity gradient technologies, further advancement is needed in the development of new photothermal membranes with stable properties in hypersaline solutions for efficient sunlight-driven evaporation, and in the development of new ion exchange membranes with high perm selectivity, low electrical resistance, and low cost. Thank you for your kind attention.
Thank you very much, Efrem, for this nice presentation. I really think that this could be one of the possible new direction of the Italy-Taiwan collaboration. As a matter of fact, it is possible to fabricate nanocomposite membranes starting from functional inks based on a few layers of bulk crystal that could be grown by our Taiwanese partners. Yesterday we had a presentation by Shan Lue, another chairman of this symposium, on the growth and characterization of high quality crystals of topological phases of matter or van der Waals semiconductors. And I also think that photothermal membrane distillation is a suitable playground to meet condensed matter physics with chemical engineering, thanks to the thermoplasmonic effects in nanoscale thermal hotspots. In this session, we have also a talk by Professor Kuo-Lung Tung, and I hope that there could be also an interaction with the Taiwanese School on Membrane Technology. So in the program of this symposium, we have searched a top-level expert as Professor Tung. So, Professor Tung, can you comment on Efrem's talk?
Let me first say that is a great pleasure to stay in touch with Taiwanese colleagues. We have a long time collaboration on membrane technology, but in general, I think that membranes offer the opportunity to scale up the wonderful systems that you are developing at, let's say, laboratory scale or in general low scale, possibility again to scale up even to large-scale industrial applications in terms of photothermal membranes, desalination, yes, but also even beyond this, other application related to energy exploitation.
Thank you very much. And I enjoy your talk very much. I have a quick questions for your talk. You mentioned about the photothermal. I'm also working on that. But you know, we also facing the problem about the membrane fouling. So because we need a UV or sunlight, yeah, for the photothermal membrane. So how to prevent fouling on it during the operation?
The battle against fouling is one of the hardest in membrane technology. Basically, this is intrinsic to membrane operation, such as corrosion is intrinsic to, I don't know, other equipments, industrial equipments. The question is, from my point of view, is that fouling has to be controlled, prevented maybe not, but controlled with good pre-treatment stage. In fact, what we are proposing is to, for instance, operate our photothermal membrane distillation stage not as a standalone unit, but eventually on the brine of reverse osmosis, assuming that water that is entering in reverse osmosis has been already pretreated against fouling, against colloidal fouling, and many other issues. So I think that the good integration between pretreatment and, of course, membrane stage can help to better control the fouling problems.
Okay, thank you very much.
In general, concerning photothermal materials, most of them show properties, anti-fouling properties. Using silver nanoparticles, but also other carbon-based nanoparticles, graphenes, and so on, show some anti-fouling properties, at least against biofouling. This is the most aggressive one when treating natural waters.
Yeah, I'm also working on that and I suffer from that very tough challenge. Okay, thank you very much. Yeah.
Thank you very much. to both Efrem and Professor Yu-Lun. I hope that there could be the possibility to start a collaboration between Taiwan and Italy on membrane technology, and this workshop should try to push on this direction. And so now we will continue with Professor Yu-Lun Tung, and we thank again Efrem for his high-level lecture on photothermal membrane technology. Professor Tung from National Taiwan University will talk about omniphobic photothermal nanocomposite membranes for direct solar membrane distillation. So it is an excellent matching with the previous talk. The stage is yours.
Okay, thank you very much. Thank you very much for your introduction. I'm so happy to be invited and to have the same topic with the previous speakers on the photothermal membrane and applications. So today I will talk about the same topic, and I will skip some introduction because the previous speaker already gave a very comprehensive introduction about membrane distillation. And today my focus will be on the omniphobic. Yeah, what does the omniphobic mean in the membrane distillation? And before start my talk, I will introduce you. This work was cooperated with Professor Chih-Wei Lee. Yeah, she is from the Rice University, and she is one of the pioneers in the photothermal membrane development. So here shows I've been to Italy many times, and this is in 2015, I think. Yeah, this is Ravello, right? Ravello or Ravello?
Ravello.
Okay. Yeah.
Near to Salerno. I recognize Professor Enrico Trioli.
Costiera Amalfitana, questo Trioli.
So he invited me to join this and have a panel discussion about the membrane distillation. Yeah, I think many Italian outstanding scholars also attend this conference. I enjoyed that very much.
Yeah, we met there.
Yeah, sure. I introduce you a brief introduce about myself. I'm now the Deputy Director of the Water Innovation Low Carbon Environmental Research Center. The abbreviation is the WINER Center. And I also now a fellow of the International Water Association. And also I was invited since this year be the editor of the Separation Purification Technology Journal. So this is not really from for the materials experts. This is for membrane or separation expertise scholars. Yeah, and so I also invite you to submit your quality papers to our journal and also the Journal Membrane Science. And I also serve as the council member of the Filtration Society UK since 2008 to 2012. So I traveled to Europe before the COVID-19 pandemic. I travel more than 10 times per year to Europe, many different countries. Okay, so here is the logo of our WINER Center in NTU. And what does it mean?
Innovation.
Yes.
Environmental.
Oh, I'm sorry, I have a pre-code. Yeah, just skip that. So here is the center was the inauguration ceremony was in the 2020 year January. But after the opening of this center, yeah, everything stopped. Yeah, because of the COVID-19 pandemic. And we have 18 key members from environmental engineering, chemical engineering, and also civil engineering and materials engineering. So I'm now the deputy director of the center. So why we have the center in 2020 is because our president found the ranking of the water research around the world. Our university was the only one in the top 40. And the top 1, top 2 is from the Singapore, NTU, and NUS. And our university ranked 26. So our president and our dean of the College of Engineering fully support us to form the Water Research Center in NTU. So here is the list. So here is the building for our environmental engineering research, especially for the water and the carbon capture. So in this center, we already developed some technology. Yeah, here is for river water. I show you. That was
Rivers
featured
surrounding the
by
city
the
of
Discovery
Taipei
Channel.
contain high levels of pollution and bacteria. In these murky waters lie chemicals from nearby agricultural and industrial parks, and even pathogens from wastewater treatment. Professor Alan Tung is testing this portable filtration unit to see if it is able to screen out the smallest of these microorganisms, and indeed leave behind only clean, pure drinking water.
I drink it. Yeah, this is from river water. Yeah, so that was featured by Discovery Channel in 2015. Yeah, the technology just only need gravity driven only. So it's only good for river water, but for seawater, it's not possible. So we have to look for different technologies. So membrane distillation is one of the potential option after the reverse osmosis. But as mentioned from the previous speakers, there are many challenges for the membrane distillation being be applied in the real in the field. So three key problems. One is the temperature polarization, because we need, as mentioned, we need hot stream, and in the other side of the membrane, we can capture the vapor and try to condense the water, and then we can have a very high quality water here. But the feed water, when the water contact the membrane, the temperature drop very fast. This is the temperature polarization problem. And the other one is the surface weighting and the surfactant, because in the industrial water, many surfactants. So the surfactant will weight the membrane surface and cause many contaminants or ions penetrate through the membranes, make the membrane distillation fail. And the other one is the low energy efficiency. So how to overcome these three main problems? I and my colleagues, we propose a nanophotonics enabled solar membrane distillation. Yeah, the same as previous speakers. But Professor Lee, she blend the carbon black in the polyvinyl alcohol membrane, and this carbon can absorb the solar irradiations. So this is a very good idea, because when we have the hot field in the traditional membrane distillation operation, the stream will cool down along the channel. But if we combine and blend the carbon into the membrane surface, then that membrane surface can absorb the sun radiation, and then can heat the feed stream and keep the feed stream hot or even higher than at the inlet. So here shows the traditional membrane distillation, but with the nano technology, nanophotonics enable the solar or nanoparticle inside. Yeah, we can increase the temperature and without the power input. But still have a problem is the weighting. Yeah, so if the surface has been weighted by the surfactants or covered by contaminants and or some oils, and then the surface still cannot absorb the sun radiation and will be covered by some dirts. So how to combine the omniphobic and the photothermal? Yeah, was the challenge. And this was mentioned in the Nature Nanotechnology Journal in 2018. And in this talk, yeah, I will introduce to you my group and Professor Lee's group from Rice University. We move the carbon from the membrane plane to the surface and change the surface morphology and then we can obtain the omniphobic surface properties. So how to do it? I will introduce to you. Yeah, this is the idea about the omniphobic membrane surface. Yeah, we can have the reentrant structures and by coated with some nanoparticle on it. So here shows the ZNO zinc oxide nanoparticle. And then in order to make sure the surface is hydrophobic, and then we graft some fluoro materials on the nanoparticle. So here we publish some works on the omniphobic. And the first paper is now still the high side paper in the desalination journal. Yeah, this is the first one. We developed the omniphobic surface properties for the direct contact membrane distillation. So here shows the traditional PTFE membrane. The membrane is hydrophobic, but not omniphobic. So it only can repel water only, but it's failed for oil, ethanol, decant, and some other surfactants. So if we make the surface with some reentrant structures, so we can prevent the weighting of the membrane surface from oil, ethanol, or decant. And how to do it is here we show the first trial on the glass fiber because it is flat and also cheap. So we graft some and the ZNO zinc oxide particles on it. So you can see from the SEM pictures, and then graft some fluoropolymer on it. Yeah, then we can obtain the omniphobic surface. And the particle size is around 100 nanometer or smaller. So here you can see the surface properties, surface structures, and the testing showed the surface is omniphobic, not only hydrophobic. So we tried different concentration of the surfactants in the feed, and we found a very promising result. Here I will show you. So here shows the first, yeah, this is only hydrophobic, but after coated with the nanoparticles, the zinc oxide on it, and we can obtain a very omniphobic surface properties. So we combine that and into this photothermal surface. So we coat the surface with some carbon nanoparticle on it instead of a blend in the PVA membrane. So this is the idea. Yeah, we move all the carbon nanoparticles out and graft on the surface. So then the surface can prevent the migrate of the surfactant into the membrane pore. And here, because of the carbon nanoparticle can absorb the sun radiation, so you can see the temperature, the feed temperature increased. Yeah, and toward the membrane surface, different from the traditional one. Yeah, this is here has a abrupt decrease of the temperature gradient. So in our previous work, we compare nanoparticle or nanorod or the nanosheet, which one is better? Yeah, for the membrane surface modification. So here we have a different trial. And in our another work, we coated on the hollow fiber instead of a flat sheet glass fiber. So here we try nanorod and a nanoparticle, different morphology. And here shows some SEM nanorod, nanoparticle, and we enlarge the membrane surface and zoom out to let you see. Yeah, the surface property and the pore size was not fully covered if we can precisely control the amount of the nanoparticle on it. So you can see the pictures. Yeah, just show you something about that. And after coated with some nanoparticle, you can see from the AFM, the surface roughness increased compared to the previous pristine membrane. So here shows the schematic diagram about the coated surface. So here is the pore size and the particle size. Yeah, so the particle size also around 200 nanometer. and the pore size also about 200 nanometer. But after covered, the pore sizes still keep very similar, not reduced very much. So here you can see the original pristine is 207, and then it's 201.9. So, and we also mapping the zinc metal, and we found that it's a very uniformly distributed on it. So here shows the result. We increase the SDS surfactant gradually from 0 to 2 minimum mm, and then here shows the nano rod, yeah, that can sustain for around 12 hours and then fail, yeah, because the surface property without the very obvious re-entry structures. But if we cross the nanoparticle on it, and then we can continuously keep a very stable flux and a very high flux here. So here shows some our modules and long-term stability testing, and the rejection is almost 100% to reject the nano the sodium chloride. And compared to the literature, yeah, for our work, the flux is high, and our membrane can prevent the weighting with a very extremely high surfactant concentration compared to all of the papers published reported in the literature. So compared to different substrate backing materials, glass fiber is not so well controlled. The pore size is not well defined, well controlled. And here shows the hollow fiber. So the hollow fiber can prevent the weighting under the very high concentration of the surfactant, but the glass fiber cannot, just only reach 0.3. So in our following work, we use some hollow fiber, yeah, to make the photothermal surface property here. So for the photothermal membrane, as I mentioned, yeah, we not only blend the nanoparticles in the polymer, but also we grow the nanoparticle on the surface. So you can see, yeah, the surface can have some nanoparticle on it by gravity. So we try different concentration of a carbon nanoparticle, 0, 0.05, 0.2, and 1%. So here shows the contact angle. Yeah, with the coating, the contact angle keep a very high, and also without omniphobic coating and without the carbon nanoparticles on the surface, when we try the ethanol, the surface weighted immediately. And after we coated with the carbon nanoparticles on it, yeah, it can prevent weighting. Yeah, and the surface angle is still capable about 100. Yeah, even under the ethanol circumstance. So here shows the different concentration, and you can image the 1% carbon black on the surface maybe is too heavy loaded. So the pore was fully covered. So here shows some AFM images, and we can measure the surface roughness. And then we try to have a different infrared thermometer or sunlight. So you can see, yeah, with 100% carbon black coating, the surface can temperature can increase from 20 to 48 something. Yeah, if coated with 0.2, we can reach to, I'm sorry, here is my big picture here. I can see that. But for 0.05, it's around 35. Okay, so of course, as this figure show, increase the concentration of carbon black is better. Yeah, but after testing with the membrane distillation with the sunlight on it, you can see 0.2% of the carbon black particle coating is the best. And if you further increase the concentration of the carbon black, Yeah, because the surface was fully covered by the nanoparticle and the flux reduced very obviously. So we keep this concentration, and also the flux is also promising. Yeah, not so high as a typical membrane distillation membrane, but it still can be accepted for the field applications. So here is some image, and also we try different concentration of the surfactant. So from here, you can see all the flux keep very stable, but for the PVDF pristine membrane without the surface modification, yeah, the flux, yeah, increase obviously. It's because of the failure. The membrane was weighted, yeah, by the surfactant. But if we modify the surface with the omniphobic property coated with the carbon black nanoparticle on it, we can still keep it very stable. Even the surfactant concentration higher reach to 0.4. So that means this idea is promising, yeah, for the surface to be omniphobic and the photothermal function, the property. So we compare the energy efficiency here. The traditional DCMD membrane, the energy efficiency lower than 30%. But for the carbon black nanoparticle coated membrane, it can reach 71%. So it's an energy efficiency membrane. So here is also some comparison, yeah, with the omniphobic and the photothermal integrated membrane. The surface, the energy efficiency is high, and also the membrane can prevent weighted with the very high surfactant concentration. So that's our results, and some conclusion here is the same as I mentioned. By combine with the omniphobic and the photothermal, we can overcome the three big challenges like the temperature concentration, polarization, and also the surface weighting and the energy efficiency. So we can also think about other way, yeah, not only by sunlight, by electromagnetics, some other external field can also enhance and the performance to reduce the energy consumption. And at the last, I would like to also invite you. Yeah, maybe you cannot come here, but can by virtual meeting like this way. We are doing. Yeah, in 2022, I will organize the conference. Here, as you can see, this conference originally should be in the 2020. Yeah, so we move 2 years later here. But next year, I think it's still a big challenge. So we already decided to have a hybrid of way to do that. And the conference already 30 years. So we will celebrate the 30 years anniversary for that. And welcome all of you to come to Taiwan or online to join the conference. This conference is the International Conference on Inorganic Membranes. And I will be the chair. And I welcome all of you. And thank you very much for your kind attention.
Thank you very much for the very nice presentation. I will start with a short question. What do you think about the exploitation of thermoplasmonic effects in nanomaterials with plasmonic resonances in the visible? In your platform, how this could improve the efficiency? The microphone. Please, the microphone.
I didn't hear about you. Could you please repeat again?
What do you think about the exploitation of thermoplasmonic effects in nanomaterials in the surface layer with plasmonic resonances in the visible? This is one of the activities which is planned for the Italy-Taiwan collaboration, and it could be interesting also for you to find new materials to be used used in the surface layer with plasmonic resonances matching with the visible. So to match the sunlight radiation spectrum.
Yeah, of course. Yeah, if we materials expertise from like all of you, yeah, we can provide some new materials with a high efficiency about the absorption of the sunlight. Also, as I mentioned, how to prevent the fouling. Yeah, the material anti-fouling is also very important. I heard some presentation before yesterday. Yeah, about the service self-cleaning or something like that. Yeah, that will be helpful. And to make this kind of photothermal membranes to be applied in the real field for seawater desalination. Yeah.
One of the goals is also to carry out a band structure engineering in order to get the dielectric function with optimize the response in the visible region of the electromagnetic spectrum. And we will also try to get materials with optical anisotropy with additional plasmonic resonances, so as to get the highest absorption as possible. So I hope that we could keep in contact with you for a collaboration with Italy.
I'm also looking forward to, yeah. Thank you.
If there are only short questions because we are a bit on a delay. Yes, okay.
Alan, please, concerning the incorporation of zinc oxide or carbon black nanoparticles on the surface of the membranes, of course, this will have an impact on the conductivity, thermal conductivity of the membrane.
Yes.
Risk to decrease the thermal efficiency. Did you, I mean, you make tests only on direct contact membrane distillation, or you are going to consider different configuration? For instance, I don't know, air gap membrane distillation that probably in this case will you will even increase even more the thermal efficiency, because in air gap the conductivity is less aggressive.
Yeah. Thank you very much for your suggestions. Yeah, I will try it. Yeah, we still not try a different configuration like a VMD or air gap. Yeah, I think that will be also helpful. Yeah, for different kind of operations of MD. Yeah, thank you.
Thanks.
Thank you, Yu-Lun and Efrem. So let's move to the next speaker now, Despina Fragouli from Istituto Italiano di Tecnologia. She will talk about functional and hydrophilic polymer nanocomposite for water technologies. She comes from the Smart Materials Department of Italian Institute of Technology. Despina, now the stage is yours. You can share.
Hello, can you see?
Yes, go ahead.
Okay. Thank you very much, Antonio, for the introduction, and thank you also as organizers for the invitation and giving me the opportunity to participate to this very interesting symposium. Today I'm going to talk to you a little bit on materials that are different from crystalline materials. There are polymers. We are using polymers in our group, and we are combining them with various components that could be. There are also crystalline composite nanoparticles. Sorry. In order to use these materials for different applications. So first of all, allow me to introduce the center where I work. It is the Italian Institute of Technology. It's a foundation that was born 15 years ago. Today, there is a central research laboratory, which is in Genova, and then there are different other satellite research centers all over Italy. Each of it has specific targets to develop, but all the Italian Institute of Technology is focused on transferring scientific knowledge towards towards industry. So up to now, we're about 1,900 people, and we're coming from all over the world. Now, focusing a little bit on the group where I am working, is called the Smart Materials, and it is about 40 people. All of us, we're having a mission to generate new knowledge and advance the state of the art. We are working in 5 different research lines. The first one has to do with the development of sustainable biocomposites. So we are developing polymer-based materials that are coming from agricultural waste, from animal waste, and we are proposing this type of materials as alternatives to the synthetic polymers that are existing and they are widely used. Then we are developing also materials for water treatment, for smart packaging, for biomedical applications, but also for flexible electronics. And then we have another part of the group which is working on industrial projects. So actually these are projects sponsored by companies where people in our group are working in strong collaboration with the specific companies for resolving some of their problems or developing new solutions that they need. So here are some examples. We are developing in collaboration with companies some biodegradable food packaging materials or some antiviral coatings. And also we are working in more advanced applications such as thermal interface materials or innovative sail-making technologies. Going further to the water treatment part, where I am responsible, we are developing porous materials that are able to clean water from hazardous pollutants or to recover fresh water from unconventional sources. So in this part, for example, we are working on adsorbents, which means that we are combining polymers with fillers, with micro or nanoparticles. Here I show you some examples where we are combining polymers with spent coffee grounds or orange peel powder, so some agro wastes, in order to develop foams that can be used for water remediation, such as removal of heavy metal ions or some organic pollutants. But of course, in this part, we are working also with some nanocrystalline materials that are more advanced and have a specific functions. Then we are working on photocatalytic degradation of organic pollutants through the development of some polymer-based fibrous composites, which are combined with semiconductor nanoparticles. And here we are mostly focused on trying to find solutions for daylight photocatalysis, which could be the most appropriate for a realistic application in the water treatment. Then we're working also on the development of 3D filters in order to remove or to filter water and decontaminate it from oil, but also from other pollutants. And then we have another recent part of our research is focused on the photothermal seawater desalination. So we are developing 3D polymer-based composites with specific porosity, hydrophilicity, but also efficiency to convert light into heat in order to use them for photothermal desalination. So today I'm going to give you 2 examples of the materials that we're developing, focused on filters and photothermal seawater desalination, in order to somehow give some ideas or some some ideas for collaboration, because these parts could be very in these types of applications. It would be very interesting to explore novel and new fillers into our polymers in order to enhance the process and the property, the performance. So going to the before going to the examples, I would like to tell you that in these two examples that I'm going to show you, we are having as a basic polymer component the hydrogels. Hydrogels, we choose to work with hydrogels as a polymer matrix because they have very good and very high water affinity. So hydrogels are interacting with water and moisture, and they absorb a lot of it. And it's something that we would like to have in these applications that I will propose to you. The water that is entrapped into the hydrogels can be present in 3 different states: the free water, intermediate water, and the bound water. And this is also another very important point, especially for the photothermal desalination with these 3D materials that we're developing. And I will explain to you later on why. And then we have also the fact that the hydrogels can interact and with different pollutants and separate pollutants from water with different functions. So through the mesh sieving, charge repulsion, the Donan exclusion, or ion sorption properties. So here, just to show you how a hydrogel would is interacting with the water. So when water is wetting the material, it is swelling very much. So this gives the opportunity to the polymer chains to interact with the water and whatever this water transfers into the material, so some pollutants. Now going to the first example, I'm going to talk to you about functional porous polymer composites for photothermal desalination. In order to make the material, we need to have, for this application, a hydrophilic material that is very porous. It can float on water, and also, of course, a material that can transform solar light into heat and keep it into its structure. For this reason, we choose to work with a combination of 2 polymers, the waterborne polyurethane and the polysodium acrylate hydrogel. And this is our matrix, our polymer matrix, and then we need a solar absorber. And for this application, we are using expanded graphite, which is a material of very high porosity and also that can absorb and entrap light into its structure. As you can see here, expanded graphite is in the forms of grains. And these grains, if we see them closer, they are composed of graphene sheets that are interlinked together in order to form this 3D structure. This material resembles like a very small foams, and it has very high porosity. As you can see here, the same weight of expanded graphite, graphene, and multi-wall carbon nanotubes occupy completely different volume into the vial. And what we do is we mix these grains together with polymers, and then upon curing, we arrive to this type of material. This material is a very light system and very porous, containing pores of different size scales. So seeing it better, we can see that we have the porosity due to the presence of the internal porosity, of the expanded graphite. So we can identify the sheets that are composing the grain. And then we have bigger pores that are due to the empty voids that are left between the grains of the graphene of the expanded graphite, and also some pores that are formed due to the polymer skeleton. So this material is hydrophilic, but since it is so porous, it can float on water. And then when we irradiate it with solar light, we see that it enhances its temperature and is localized only onto the material. Going closer to see the importance of the hydrogel in this composition of this type of material, we can see that if we have the three-component system, so expanded graphite, the hydrogel, and the polyurethane, we have a material that can absorb the water, and it has a water absorption capacity of about 6 grams of water per gram of foam. On the contrary, without the hydrogel in the composition, we have a completely different performance. This material can absorb can absorb humidity. So you see that by increasing the relative humidity percentage, the material entraps more humidity into its structure. And on the top, this material keeps the water into its structure, and it is somehow interacting very strong with it. This can be shown by this example here. So the water-saturated material, after applying 500 grams of weight onto its structure, it still it loses a minimum amount of water. So this means that we have a very strong interaction of the water and, with the hydrogel into its structure. This can be further explored by trying to identify the water states or the states in which the water is present into the system. And we see that the system has a very high amount of intermediate water and of polymer-bound water, but while the free water is less. And this is also, as I said before, this is attributed to the hydrogel component, because without the hydrogel, we have a completely different situation. Now, which are the differences between these three states of water? The bound water is the water molecules that are bound strongly on the surface or on the hydrophilic sides of the polymer chains. Then we have the intermediate water, where the water molecules are interacting a little bit with weaker interactions, but still are interacting with the polymer chains. While the free water is when the water molecules are interacting between them and they don't have any interaction with the polymer chains, so they behave or they have the properties of the bulk water. The presence of bound and intermediate water into a composite or into a foam is very important for the application for photothermal desalination, because these water states need less energy input in order to be evaporate, to change state and to go towards evaporation. So they need a lower vaporization enthalpy. This means that by lower energy input, which means lower temperature increase into the system, this water can be easily escape with the form of the vapor. So going to the experiment for the photothermal experiment, we see that when we put our foam onto a surface of water, salty water, so seawater, and we irradiate it with one sun, what happens is that the evaporation starts occurring due to the increase of the temperature into the material, And we see that we have a solar evaporation rate, which is pretty high, of about 1.9. While the solar to vapor conversion efficiency was calculated to be about 93%. By analyzing the distillate, so what comes out from the foam in the form of vapor, which we collect, we see that it does not contain, or it contains a very small amount of salts compared to the water that is in the source. So we can conclude that this material can be a good candidate for photothermal desalination applications. Then having in mind also that this material can entrap humidity, another alternative way to collect water is through the collection of humidity overnight, or let's say with less when no sunlight exists, and then through the solar irradiation to cause the evaporation of this humidity in order to collect water from the air. So this was the first example of material where we could use some very efficient or important materials from novel crystalline materials for this application. And then we have another example that I will show you that has to do with the development of hydrophilic porous polymer composites for multi-component oil-water separation, and this is through gravity-driven filtration. So again, here, in order to select the components, we need a material that absorbs water, but underwater is having oleophobic properties, and ideally super oleophobic properties. We need a material that has appropriate surface chemistry in order to interact also with other pollutants. So we can separate oil from water, but also clean the water from other possible pollutants that could exist. We need a 3D porous material that has a highly interconnected network. And then another function that we would like to introduce is self-cleaning properties. So this means that we would like to have a material that can be reutilized for a lot of times after the remediation process. And for this reason, we introduce to the system photocatalytic properties. So again, the materials that we use are the polysodium acrylate in the form of cryogel, which is a 3D porous framework with high water absorption properties. And as a filler, we choose to work with graphitic carbonitride nanosheets, which have photocatalytic properties under visible light irradiation, but also is a filler that can interact efficiently with different pollutants and also give to the system mechanical stability. So by combining these two materials, we can arrive to a system that can simultaneously remove oil and organic pollutants from water through gravity-driven filtration. So carbonitride nanosheets are non-toxic and metal-free materials. They have a high thermal, chemical, and mechanical stability. They are very porous, and they have also they can respond to they can be photocatalysts under visible light irradiation. So we introduce the graphitic carbonitride nanosheets into the polymer in order to form the cryogels that we are having. And as you can see, by introducing a small amount of this, so 1% per weight with respect to the polymer, we do not affect the morphology of the hydrogel. The thing that we affect is the swelling degree of the hydrogel. So in the presence of the graphitic carbonitride, the material swells less, and this is due to the fact that these fillers somehow are are disturbing the polymer chains. They cannot, they do not leave them free to to swell as much as they would like in the presence of water. And then the very important fact is that the presence of the graphite carbonitride affects the underwater holophobicity. So here we see that the underwater oil contact angle is slightly higher, but most importantly, it becomes less sticky. So the oil can slide away in lower angles of tilting. So this means that this material becomes underwater super holophobic, and this is an ideal wetting property for gravity-driven filtration through water and oil. Then the other effect of the graphite carbonitride in our system is that this causes the enhancement of the absorption capacity towards organic pollutants. Here we check the methylene blue, which is a dye and is a model molecule that we usually use in order to evaluate the efficiency of to be used as an organic pollutant adsorber. And we see that the presence of the graphite carbonitride enhances the absorption capacity of the PSA. So we have a better performance system. And then we go to see what is happening when we have a multi-component oil-water separation. What we see is that when we mix oil, methylene blue and water, and then we pass it through the filter, we are somehow we are having oil rejection efficiency of about almost 100%. We have a methylene blue adsorption efficiency of about above 98%, so about 99%. And here you can see how this could look. So by mixing it, all the components together and passing it through the filter, the water that is collected is clean, while the oil remains above the surface of the filter, and the methylene blue is entrapped into the material. So the additional property that we would like to explore is to clean this filter and reuse it for a second and third round. And this can be done, as you can see here, by the first trials by solar or visible light irradiation. Then we take advantage of the photocatalytic properties of the graphite carbonitride. And what happens is that the filter is somehow cleaned, and then this can be used for a second cycle. So these are all from me. I hope I gave you some ideas for collaboration. I would be really glad to work and with new materials, new fillers for our polymer systems in order to use them for water treatment applications. Thank you very much for your attention.
Thank you very much for having accepted to do this talk for us in this workshop. And it is a great news that you find complementary expertise in previous talks of this subsection to start a collaboration with Taiwanese partners and with Efrem. Just a comment. I know that it is just a part of the broad activities of your group at the Italian Institute of Technologies due to the focus on materials of this specific workshop on emergent crystalline materials. Can you briefly introduce the other activities of the Smart Materials group on green transition and sustainable growth, which you had just the time to mention due to reduce the length of your talk?
Yes. So the other activities of the Smart Materials group, one that could be very well fitted also with emergent crystalline materials that we are discussing, are the soft electronics that we are using, a combination of polymers, again, polymers in the form of natural-based polymers mostly, which we combine with conductive fillers. We work mostly with graphene and carbon-based materials, but of course it could be very interesting to check and to work also with other crystalline materials that could give better performances. And this, we are using them for developing soft electronics that then are going to be applied directly to the robotics group that we have in the Italian Institute of Technology. So we have a strong collaboration with the robotics groups in order to try to develop electronic systems that can be directly used by them. But of course, the difference is that they are very much more light and much more sustainable, let's say, compared to the ones that they are using so far. Another very important part is the food packaging. In this, we are developing, for example, some sensors or colorimetric indicators in order to detect food spoilage. And so we are exploring interactions of materials with biogenic amines or other gas components that are coming during the spoiling of food. And again, here it could be very interesting to see or to control if there are materials that can interact well with this type of gases for gas sensing or for indicating the presence of gases through, for example, optical modification of the system. So these are the most important parts. Then, of course, we have the general biocomposite development, where we are trying again to propose specifically engineered bio-based natural polymer systems that can somehow replace, hopefully, the already used so far synthetic polymer components for different applications that could be envisioned.
Thank you very much. I think that one of the direction of the outlook of Italian-Taiwanese cooperation is just the technology transfer of the expertise and the information that we get from innovative materials synthesized from the Taiwanese side. And so I think that Italian Institute of Technology, which is the leading Italian institute in this field, could give a very big contribution to for technology transfer of this interdisciplinary knowledge that we are developing. So thank you very much, and and now let's move to the last speaker. Professor Chih-Wei Luo from National Cheng Kung University.
Yes, okay, thank you.
She will discuss about structural analysis of crystalline metal chalcogenides. So the stage is yours.
Yes. So okay, also, can we start? Yes, okay. Thank you. Thank you, the chairman, Professor Li-Qing San, the invitation from him for me to introduce our work in this very special symposium about the crystalline material. Crystalline material actually is our expertise, but in different way from the aspect of chemistry. Okay. So I'm Guifang Xu from the Department of Chemistry and National Cheng Kung University. In this talk, I will present a couple series of mental chalcogenides those we have studied in this year. Before that, I would like to introduce because one of the most important equipment is single crystal X-ray diffractometer. I think most of the solid-state chemists are able to work on this, work on the crystal structure determinations by this crystallography. In last years, we have updated a new system of the crystal X-ray diffractometer. The advantage of this system is we equipped with the micro-focus X-ray source. That is particularly designed for the crystallography because with to avoid the loss of X-ray flux, so therefore can enhance a great intensity for the tiny crystal. That's the very important improvement. And another important features is the collections of data. Let me see here. Another important feature is the collection of data on this detector. Because the collection rate is improved, the so-called, I'm not very familiar with this mathematics, but the so-called this technique is called mixed mode detection. That means we can distinguish the strong and the weak intensity we can integrate the strong and the weak intensity on the same time, but keep in a very high resolution. This is very important for the crystal, especially for the solid-state physics, when the structure with the severe disordering problem. So sometimes you will observe some superlattice, and this superlattice will cause a very small diffraction spot. If this diffraction spot is lost it's mixed with the strong intense peak, then we will lose the correct information of the symmetry for this crystal. So this we are very excited. We can update this very great equipment to help all kind of crystal. Therefore, due to this updated equipment, so the crystal size that we use can be small as 20 micrometer in each dimensions. So the crystal we use is very different to the Professor Lu Qian-San. The crystal we use, I think the largest crystal we grow is about maybe the maximum can be reached 100 micrometer. That's the limit by our solid-state chemistries. Okay, so here are the crystal that we grow in our lab, and this one is the solid-state chemistry lab. So we have a high vacuum system to seal the closed tube for the reactions, because the reaction for the mental crystallize need a high vacuum. And here all kind of small furnace for the student to do all kind of try and error experiment based on the materials they are target. Okay, so let's go to our early work. This is our early work, and we have cooperated with many groups, like Professor Condensed at Northwestern and Professor Zhang Yuming at Taiwan University, because our expertise is crystallography, so all kind of physical property need help from the other groups. So here is a very interesting series of solid-state solutions. I can say that this series of solid-state solutions. Has the potential application as nonlinear optical material, especially in the infrared optical range, because mental crystals are transparent in the infrared optical range. The particular thing is this framework is very flexible. It's flexible to accommodate all kind of mental center. Therefore, we can adjust the bandgap of this series of material, because the bandgap of this material are very important for their application at the spectral wavelengths. Because if the wavelength is the energy of the wavelength is too strong, we are damaging the crystal due for the crystal with narrow bandgap. Okay, so from the at that time, we did a lot of work about the crystallography, because we are not very confident to publish these structures only by the single crystal. Just as I mentioned before, the structure of this crystal is very flexible. I think the the reason can be ascribed to very severe disordering phenomena occurring around some position. So this model is provided by our crystallography, but the situation is too complicated. We need more evidence to prove this kind of disordering. Therefore, fortunately we got a high resolution electron microscopy. We observed the image of the diffusion path of this position, and the periodicity is the same between the crystal model we construct and also the model observed from the electron microscopy image. So see, this is our early work, and so we did a substitution between the mental cation, the alkaline, or do the solid solution of the halide, the xenon calcium line, and also tune the very tiny ratios between the silver and the tin. And this is interesting. We can see as the delta value as small as like 0.13 increase to 0.31, increase to 0.33, the material display complete different color. That means they belong to different bandgap material. So that's how the important crystallography can contribute this work, because this composition only can be determined by the crystallography. They can to obtain the correct compositions. They help to the further synthesis of pure phase, because we need the sample prepared in the quantity to measure their physical property. Okay, so this is our early work about the nonlinear optical material. On the other hand, the previous topic is about study solutions to derive so many members applied with modified physical property. Another interesting structure is homologous series. We also can obtain many members from the homologous series. This technique is popular and quite often applied in the field of thermoelectric, like the late bismuth selenide, this kind of compound. But we use the manganese ions, the combination of manganese and the gadolinium. We found a series of homologous structures, and this structure belong to the limonite member. This is a well-known mineral compound. And the most important thing is the combination of these two magnetic ions. We can crystallize the first time the member belongs to the 5, the N equals to 5. Let me introduce a little bit about the Li-ion members. The value here, 33, 44, and the 55, that denotes the number of polyhedron here arranged in the adjacent slab. Okay, the number here denote the polyhedron arranged in the adjacent slabs. So since these 3 members belongs to the homologous series, we can see homologous series means all the crystal symmetry of the 3 members remain the same as the orthorhombic C and Cm. They remain the same symmetries, but the dimension of the C-axis, will increase with the increasing thickness of the slab. Okay, so we can plot here the C dimension of the 3 members here from 15, 19, 22. They increase linearly with the increased number of N, the additions another thickness of a polyhedron. So this is a very, I think it's a very interesting topic in crystallography, especially with the shape of this crystal. The shape of this crystal also consistent with the dimension of this cell constant. Okay, So this is the second series we have found in the lab and have a very interesting crystallography insights there. Of course, we also studied their physical property. So for the first member, we have found the magnetic ordering temperatures occurring around 10 Kelvin. When the member increased to the number 5, the magnetic ordering temperature raised to 70 Kelvin. From the unit cell, including more magnetic ions that can explain the stronger interactions for this compound. But also we examine the detailed crystallographic data. For example, the distance between two metal ions. We can see the distance gradually shrinkage to the member, the third member with the thickness left. So this evidence also can assist the explanation for this magnetic ordering phenomena. Okay, that's how we enjoy this work. Furthermore, this work we just published in last year. Okay, we found a very non-central symmetry and the magnetic silent framework. The topology of this framework looks like a Peruzzini structure, but actually it's not. But sometimes the stacking of a polyhedra will result in a similar outlook, a similar topology. Okay, so this framework is magnetic silent, but this magnetic silent framework traps a magnetic molecule, iron-cinnamide. This is a very famous one in the last few years. Okay. So with the help of another professor who is an expertise in magnetic molecule, we found these dimers still perform magnetic interactions at low temperature. We can see the ordering starting at 19 Kelvin around here. Okay. Therefore, we are thinking about, since this framework belongs to a non-central symmetry. Without the symmetry center, it is possible to use the second harmonic generations to sense or to detect the change of magnetic spin together with electric carriers, like the traditional dilute magnetic material, manganese telluride. So we cooperate with Professor Zhang at Songkang University, South Korea. He just built up a system, OPO, and he used this laser source, try to measure the second harmonic generation at low temperature. It's very lucky, not lucky. It's very obvious. We found an abrupt transitions around 20 Kelvin. This temperature is quite close to the this one, quite close to the temperature for magnetic ordering. Okay, but the problem is how we to explain. The problem is how we explain this increasing intensity in the temperature range, between the temperature range start from 200 Kelvin. This we cannot. It's very hard to explain this increased intensity. So we are thinking about maybe due to the volume, due to the shrinkage caused by the low temperature, the polyhedra will be more distorted. As we know, if the polyhedra more distorted, the dipole moment will affect which SHG intensity. So we observe. So we try to collect the crystal data at low temperature. At that time, we only collected 200 Kelvin. It's obvious that we obtain the slight change of cell constant ABC and observe a small volume for the unit cell. So that also help to assist to explain the distortion of polyhedra and the low temperature, and they also affect the dipole moment and then affect which second harmonic generations. Okay, So this is interesting material that we have studied in last year. Okay, so currently we have worked with the Professor Chen, Professor Zhang, because we also found an interesting framework, and this framework maybe can provide the explanation of a defect complex or the vacancy defect from the X-ray model, because most of the determination of vacancy or the vacancies or antisites are from the luminescent property or by the X-ray, EXF, this kind of other techniques. And we hope we can provide the average structural model from single crystal to contribute some kind to this field of research. Because as the literature says, the formation of this defect complex will stabilize the structure, and we also can observe this phenomena in our new compound. Okay, so here I would like to thank you the cooperation with Professor Zhang at Taiwan University, and also Professor Jen at South Korea, Sogang University. They help us to measure all kinds of optical properties. Also, Professor Yang, we cooperate with the magnetic measurement. And also, the most important is the National Synchrotron Radiation Research Center, because sometimes we still need the powder X-ray data to explain this very complicated or high symmetry structure. Okay, thank you.
Thank you very much for this nice presentation. I will start with a question regarding one of the last slides on copper selenium-4 and indium selenium-4. You said that there are some structural defects. Firstly, I think that they will be selenium vacancies, isn't it? Another question is if you have checked the presence of indium oxide in this crystal as contamination due to the interaction with environmental gases. I think that by means of X-ray photoelectron spectroscopy, you could find some traces of indium oxide or even selenium oxide in both the copper and indium based alloys.
Okay. To the first question, I think, yes, you said it's possible the selenium vacancy, but I think this because I will say that it's a copper vacancy or an indium copper antisat vacancy because I skip many detail about the X-ray determinations. Because we solve the crystal structure, we need to derive a formula keeping charge neutrality. Charge balance. We need to charge balance the formula. So we found this position is essential, is necessary to be filled with the cation, this kind of vacancy, to maintain the charge neutrality of the formula. Okay, so this is kind of model explained by the X-ray because we have the reason that we have to satisfy the charge neutrality of the formula. Okay. Like the vacancy selenium, this kind of thing, I think it's most often most occurs in the polymer, right, or thin film, this kind of material. But here is the crystalline material. It's different situations. So this can be also here. You can see here's the literature reported in this year: copper indium 3 selenium 5 or copper indium 5 selenium 8. This material is produced. Caused by the presence of this defect pair.
Thank you very much for your complete reply. Now we are quite late, so we thank you again. And you was the last speaker of these 2 days symposium. So I see also Professor Shan Lue and Professor Cao connected, so they could open their video for the concluding remarks. If Professor Cao would like to give us some comments for the conclusion, and then I will give also some comments from the Italian side. The audio is not working. Please restart the mic. Restart the. I see also Professor Shan Lue. Check the microphone and open again.
Can you hear me now? Okay.
Yes.
It's very nice to see there's already a lot of collaboration between the Italian and Taiwan researchers. We hope that with the platform of TCCM, we can further these collaborations. And there's a lot of researchers in Taiwan who's not yet aware of this collaboration. And I think next time, if it's possible, we can have a physical meeting either in Italy or in Taiwan. And there'll be a lot of people who are interested in this kind of collaboration. And so if you have any questions or you have any proposals, you can talk to Chin-san, and we hang out a lot. So he can tell me, and I can work with the Ministry of Science and Technology to better enhance the collaboration. And thank you very much for a very successful workshop. Thank you.
Thank you. Chin-san, would you like to add some comments? It is.
Okay, I want to thank all participants to make this symposium succeed. And in particular, I want to thank you, Professor Antonio Politano, for the contribution to the promotion of the cooperation between Italy and Taiwan. I hope that we have tight relationship, not only in the scientific activities, but also in friendship between both countries. For me, Italy was the first country in Europe I visited about 18 years old. 18 years ago. So, and I promised to arrange delegation to visit Italy if the COVID-19 pandemic become not so bad. And I believe the Taiwanese people should be very happy to enjoy the excellent wine in Italy. And also, Italian delegates are welcome to visit Taiwan for any reason, not just for the academic exchange, but also for the good Taiwanese food and the beautiful scenery in Taiwan. Okay, thank you.
Thank you. Thank you. So now we are at the end of these 2 days of intriguing and interesting scientific talks by Italian and Taiwanese scientists working on advanced materials. This meeting was co-organized by University of L'Aquila, the Ministry of Science and Technology of Taiwan, the Taiwan Consortium of Emergent Crystalline Materials, the Representative Office of Taipei in Rome, the Italian Economic, Trade and Cultural Promotion Office in Taipei, and the Italian-Taiwan Scientific Exchange Association. Let me thank the chairman of the various sessions, Maurizio Peruzzini, Carlo Rizza, and Alessandra Continenza, connected now, who also supported the organization of the workshop and the selection of the highly reputed invited speakers. I acknowledge Maurizio Cironi for the high quality of the WebEx and the YouTube broadcasting, and moreover Melanie Fang-Yung Kuo, whose support was really crucial to organize this meeting. I also thank to brilliant PhD student of University of L'Aquila, Dario Mastripolito and Daniele Capista, for the nice organization of the meeting in all its parts. Moreover, the whole organizing committee thank the director of University of L'Aquila, Edoardo Alesse, the delegate for internationalization, Professor Bruno Rubino, and the director of the Department of Physical and Chemical Sciences, Luca Lozzi, for their speeches during the conference and their continuous support for this initiative. The work by Shan Lue and Shan Lue in Thailand was also decisive for the outcome of this initiative, and in general for the whole Italy-Taiwan collaboration on advanced materials. And finally, I thank once again Ambassadors Lee and Giglio for having supported this initiative from the very first moment, and for their efforts to bridge Italy to Taiwan, also in science and technology. The whole organizing committee look forward to continuing the collaboration with their representative office in Rome and Taipei, respectively, as well as with the recently established Italy-Taiwan Scientific Exchange Association, presented here yesterday by Stefano Pelaggi. I thank also the Deputy Ministry, Professor Lin, of Ministry of Science and Technology, for his valuable opening message. It is also useful to know that if you lost some talks, you will find them in YouTube. Similarly, the interactive showroom on Padlet will remain online, even after the end of the workshop. Several topics have been addressed by delegates from both countries: advanced materials and related application in photonics and optoelectronics, energy conversion, water treatment, green technologies for sustainable growth, surface science, semiconductor industry, and nanotechnology. We had the participation of invited speakers of highly reputed institutions of both countries, leaders in their respective scientific field. We hope that this event could further stimulate bilateral cooperation with new collaboration and international projects. However, there are already some deliverables that I'm really proud to share with you. We found an agreement for signing a memorandum of understanding for a joint lab on innovative semiconductors. Within the joint lab project, research activity will be jointly carried out by Italian and Taiwanese researchers who intend to share their skills as well as their research facilities. The joint lab will be a meeting place, both physical and virtual, having new improved characteristics if compared to the original single structure or affiliation. The joint lab will be located in L'Aquila for the Italian side and in Tainan for the Taiwanese side, but it is open to all Italian and Taiwanese scientists working on advanced materials. Now I will read the first two articles of the Memorandum of Understanding, where we we report the research areas of interest for this joint laboratory. The Article 1, Purpose. The purpose of this agreement is to further strengthen cooperation in scientific research between Italy and Taiwan. The parties, on a basis of equality and mutual benefit, will cooperate in the following, but not limited to these, scientific areas: innovative semiconductors and sustainable manufacturing, advanced materials for optical communication and three-dimensional sensing application, nanomaterials for sustainable energy, and topological materials for optoelectronics and photonics. The second article, a form of collaboration, the parties will cooperate as a general principle through the following joint activities: joint laboratories, mobility of early stage researcher, exchange of know-how, as we already do, the access to research facilities, and data sharing. I am really excited for this remarkable deliverable for our 2 days of journey through science and technology in Italy and Taiwan. Ladies and gentlemen, before the lights are definitely turned off, I have the pleasant task of thanking each one of you connected in these 2 days on WebEx or YouTube for their valuable presence. See you soon in Taiwan or in Italy for starting a new exciting scientific collaboration, or even just virtually. So, ciao.
Thank you.
Ciao.
Bye.
And grazie.
Sì, classic.